Hello everyone and welcome to this machine learning full course by Intellipaat. With AI advancing, machine learning is rapidly becoming a must-have skill for the future careers. Recently, Times of India even reported that machine learning and generative AI are unlocking untapped potential in data analytics, speeding up insights for businesses and creating new opportunities instead of replacing the old jobs. And for students and professionals, the shift is clear. ML is no longer optional, it's foundational. And as businesses generate more data every day, the ability to extract insights from it has never been more valuable. And the demand reflects the shift clearly. According to Times of India, India is expected to require close to 1 million skilled AI professionals by 2026 in the areas driven by data and machine learning, with the roles such as machine learning engineer, data scientist, and AI specialist already offering salaries that go beyond 20 LPA for the professionals with the right skills. And while many people just talk about machine learning, only a few truly understand how it works. I mean, most know how to use the tools, but very few know how to build, train, and evaluate ML models. And that growing difference between demand and expertise, that's the skill gap. And that's exactly why Intellipaat has designed this machine learning full course, where we will start from fundamentals covering core concepts like supervised and unsupervised learning, regression, classification, clustering, and model evaluation, and gradually moving into advanced techniques. You will also learn how algorithms actually learn from data, how to fine-tune models, and how to apply machine learning to solve real-world problems. So without any further ado, let's get started. I went through hundreds of courses, watched countless tutorials, and compared the most popular learning paths for machine learning. And you know what I found? Everyone says something different. Some tell you to start with Python, others throw complex math at you right away. It's no wonder so many to learn the right things in the right order. And to help make your journey easier, I took a deep dive into how some of the top universities in the world, like Stanford, MIT, and Oxford, actually teach machine learning. I studied their course structures, the topics they prioritize, and how they build your understanding step by step. Based on that, I've created a simple and well structured roadmap just for you. This roadmap will guide you on where to begin, what topics to focus on, and it even includes free resources to help you start learning the smart way. Alright, so without wasting any time, let's get started with the very first step in your machine learning journey, that is to build a strong foundation in math. And by strong foundation, I don't mean you need to be an expert in every topic, rather, you just need to be comfortable with a few key areas. Start with linear algebra, which deals with vectors and matrices. These are used in almost every machine learning algorithm, so understanding how they work is essential. Then move on to calculus. It helps you understand how models learn and improve, especially when it comes to concepts like derivatives and gradients, which are used in model optimization. Next, focus on basic statistics. It will help you understand your data, compare results, and measure how well your models are performing. Finally, learn some probability. This is important for understanding how models make predictions, especially in classification problems. If you're looking for resources, there are free courses by MIT on all these topics. But if you want to learn these concepts in one place and in a simpler manner, I'd recommend the 6-hour Statistics for Data Science full course by Intellipaat. This free course will equip you with all the fundamentals of stats needed for machine learning algorithms. Step 2. Learn programming with Python. After building your math foundation, the next step is to learn programming, and Python is the best place to start. Python is simple, beginner-friendly, and widely used in data science and machine learning. Its clean syntax makes it easy to learn even if you're new to coding. So you can begin with the basics like variables, loops, functions, and object-oriented programming. These are the building blocks that will help you write clear and efficient code. Once you're comfortable with Python fundamentals, start learning the most important libraries for data science and machine learning. First is NumPy. This helps you work with numbers and arrays. Then comes Pandas, which is great for organizing and analyzing data. Matplotlib and Seaborn help you create graphs and charts to visualize your data. To get started, Google offers a free Python class that's perfect for beginners. And if you want to learn the libraries I mentioned, I have created full course on YouTube or on Intellipaat's channel. Step 3. Get started with supervised learning. Once you're comfortable with Python, it's time to step into the world of machine learning, starting with supervised learning. This is the most common type of machine learning, where the model learns from labeled data. In simple terms, the data you feed into the model already has the answers, and the model learns to predict those answers for new data. You'll start with basic algorithms like linear regression and logistic regression. These help you solve simple prediction problems like predicting a number or classifying data into categories. After that, you learn about regularization techniques such as L1 or lasso and L2 or ridge, which are used to avoid overfitting and improve your model's performance. Another important part of this step is model selection. You'll need to understand how to balance bias and variance to choose the best performing model for your data. And then you also need to learn how to evaluate your model. Evaluation can be done on some key metrics like mean squared error, MSE, which is for regression problems, and accuracy, precision, recall, and F1 score for classification problems. These metrics tell you how well your model is doing and help you compare different models effectively. To learn these topics, I'm going to tell you guys about the free resource after the next step of our roadmap. So step 4, explore advanced supervised learning techniques. Once you're confident with the basics, it's time to move one step further and explore some advanced machine learning algorithms. These models are more powerful and can handle complex problems better. Start with naive Bayes, a simple but effective algorithm that's great for working with text data like detecting spam emails or classifying news articles. It's fast, easy to understand, and works surprisingly well in many real-world tasks. Next, learn about support vector machines or SVMs. These models are especially useful when you're working with data that has many features. SVMs try to find the best possible boundary between different classes, which makes them very effective for classification tasks. You'll also come across decision trees, which are known for being easy to interpret. They work like a flowchart, making decisions based on conditions in the data. While simple on their own, they become much more powerful when combined in ensemble methods like random forest and gradient boosting. These techniques combine multiple decision trees to improve accuracy and reduce errors. You can check out UMBC's Supervised Learning course on edX. Here, every topic is explained with clear visuals and simple language, making even the hardest ideas easy to grasp. Step 5. Understand unsupervised learning. Unlike supervised learning, where models learn from labeled data, unsupervised learning is all about finding hidden patterns in unlabeled data. This means the model tries to make sense of the data without being told what the correct output should be. It's useful for tasks like clustering, customer segmentation, and simplifying large data sets. A good place to start is with clustering algorithms. Begin with k-means clustering, which groups similar data points together based on their features. Then explore hierarchical clustering, which builds clusters step by step, either by merging or splitting groups based on how close they are to each other. After clustering, move on to dimensionality reduction techniques. These methods help you reduce the number of features in your data while keeping the most important information. Start with principal component analysis or PCA and factor analysis, both of which are commonly used to simplify complex datasets and improve model performance. You'll also come across more advanced tools like Gaussian mixture models, GMM, and the expectation maximization algorithm. These are useful when you want your model to work with probabilities and uncertainty. To dive into these topics, you can check out Stanford's CS229 lecture series, or if you like UMBC's course on supervised learning, they also have a similarly structured course on unsupervised learning. Step 6. Dive into neural networks and deep learning. This is where machine learning gets really exciting. Neural networks are the backbone of modern AI, and deep learning models are capable of solving problems that were impossible just a few years ago. Start by learning how basic neural networks work. Understand perceptrons, activation functions, and the backpropagation algorithm. Once you're confident, move into deep learning concepts like CNNs for image tasks and RNNs for sequence-based data. You can also explore autoencoders for representation learning and more advanced models like retrieval augmented generation or RAG, which are used in model language models. Some amazing resources here include IBM's Deep Learning with TensorFlow and Keras course. There's also a free book called Deep Learning with PyTorch if you want a more technical deep dive. Step 7. Explore advanced topics in AI. At this stage, you can branch out into specialized domains within AI. If you enjoy working with language, natural language processing might be the perfect fit. You'll learn about tokenization, sequence modeling, and state-of-the-art models like BERT and transformers. If you're interested in decision making and robotics, reinforcement learning is another exciting area. You'll explore Markov decision processes, Q learning, and policy gradients, basically teaching agents how to learn through experience. You can also look into learning theory to understand what makes models generalize well. And finally, it's important to learn about AI ethics, how to build responsible models that are fair, interpretable, and aligned with human values. Stanford's CS224N for NLP, David Silver's reinforcement learning lectures on YouTube, and Mozilla's ethics in AI initiatives are all great free resources to guide you here. Step 8, work on real projects. The best way to learn is by building. Start with simple regression and classification projects using open datasets from platforms like Kaggle or the UCI machine learning repository. As your confidence grows, start working on more complex projects like image classifiers, sentiment analysis tools, or even reinforcement learning agents that can play games. Document everything on GitHub, share your work on LinkedIn, and maybe even write blogs about what you've learned. This not only solidifies your understanding, but it also helps you stand out when applying for jobs. So, this was the 8-step roadmap to get started on with your journey in machine learning. If you guys found it helpful, do hit the thumbs up button. Just a quick info, guys. Intellipaat offers an advanced certification in machine learning and AI in collaboration with Microsoft. Through this course, you can learn all the important concepts of Python, machine learning, deep learning, NLP, computer vision, and much more. The course features live classes with IIT faculty and industry experts, campus immersion at iHub IIT Roorkee, and includes certification from both Intellipaat, Microsoft, and iHub Divya Sampark IIT Roorkee. With this course, we have already helped thousands of professionals successfully transition into careers in AI, ML, and data science. You can check out the testimonials on our Achievers channel. The link is given in the description below. With the 24/7 support, placement assistance, and EMI payment options, this course can definitely set your career on the right track in the field of machine learning and AI. So visit our course page link given in the below description and take the first step towards your career growth in ML and AI.
Today we are going to discuss or start the concept. In today's session, first I'll give you a basic idea about what machine learning is, how does it work, and then we will start our today of machine learning, which is known as linear regression algorithm. Okay, so uh, till this point, you all must have heard about there is something called machine learning, and it is used for predicting something. Okay, but how does it take with you? I will be explaining to you how exactly this concept work. Okay, now before I start this topic, again, I will just say to all of you that do not expect to understand everything in one go. If you're doing that, just you're going to disappoint yourself. Give it time. Try to understand the overview of the concept in the first time when you are studying it. Then when you revise it, you will understand it very well. Okay, 100% you will understand. But in one go, in one live session, if you try to understand everything, it's not possible, right? So take it light now. So very first thing, what do we mean by machine learning, and why does it even matter for us? Okay, what is the importance of studying machine learning? See, there are two things. First, there is normal software engineering. There is one thing which is software engineering for you. Now, in this case, what happens? You have some rules in front of you that if I'm making this application, okay, if I'm making an application and there is this button in that application. Now, if someone clicks on this button, what will happen? What should happen? You have that idea, right? You know this thing, and on the basis of that, you will put the functionality into this button, right? Such as if you click on add to cart button, what is going to happen? That product will be added into your cart. If you click on buy button, what will happen? It will take you to the payment page where you enter your address, your payment style, all of that will be done. Okay, in software engineering, you know exactly what you have to do. You know exactly what are the set of logics you have to write, that when this should be done, then this is what user can expect. When they will click on this, then this is what they can expect. Okay, you have set of rules which are fixed. Because as a software engineer, what you are making websites, you are making Android applications, you are making iOS applications. So in all those cases, whenever you are building something, you know what will happen. If suppose you made a bank application, uh, then a user logs into their bank account, what are the information they will see, what are the things they will be able to do with their bank account in their bank application. You have all those things in your mind, those requirements, and you are going to build that thing. So in this case, in the software engineering, you have set of fixed rules using, right. So here you have set of rules using which application runs. Application runs. Now in this case, you're not going to build something about which you do not know what it is supposed to do. You are not going to put a button about which you do not know what it is supposed to do, right? So software engineering is about that. But when you come to machine learning, what is different in machine learning is here also you think you have to build some application, you have to build some uh, feature into the app, okay, which should do something. But the thing is, what it should do, that is not fixed. Okay, I'll give you example of that. But here the things are that whatever that feature is supposed to do is dependent upon many inputs or many factors. And that is the kind of thing you do in machine learning. So in machine learning, what you do, you have input, okay? Then you know what kind of output is expected, what we have to achieve. So you have input and you know what you have to achieve. What you will do, you will give this both information, input and output, to machine learning, and machine learning will give you the information about what to do and how to do. Okay, so there are some scenarios where we are not able to find out what we should do because it is too complicated for humans to understand what to do. So in that case, you have inputs, you give it, and you have output, that this kind of output we expect. You give it to machine learning and it will tell you what to do and how to do that. So the difference between software engineering and machine learning, because machine learning is also engineering here. Whenever you hear about machine learning, it is called as machine learning engineering. And the person who works on machine learning, they are called as machine learning engineers. Like the people who work on data science, they are called data scientists. And if you work on machine learning, just specifically machine learning, so you will be called machine learning engineers. Okay, so this is also engineering, this is also engineering. So what is different in that? In software engineering, you know what has to be done, means what are the steps to be taken to get to that output. But in machine learning, you're solving those kind of problems where you know that this kind of output I want, but how to get to that output, what are the steps going to be taken to get to that output, that I am not sure, that I do not know. So what is that uh, problem? So let's understand about that. Say suppose you have to make um an machine learning application for loan approval. Suppose you are working for a bank, you are a data scientist who is working for HDFC or Axis Bank or ICICI, any bank, and you have to build a loan approval system. Now, what the loan approval system has to do? The loan approval system has to look at the financial information of a customer and they have to decide, they have to predict whether this customer is a suitable customer for giving loan or not. This customer should be given a loan or not. Now, see, in this case, when we are building a machine learning application for this loan approval, see, there are two things. One, I can just directly build a set of rules that this should be followed, and if this is not followed, then you won't get the result. Okay. So in this case, suppose according to the software engineering approach, what we did, we made some hard and fast rules, such as if someone's monthly income, if someone's monthly income is greater than 50,000 Indian rupee, right? If someone's monthly income is greater than 50,000 rupee, Indian rupee, then only we will give them the loan. Apart from that, another condition I've written is if their employment type should be permanent, they should have a permanent job, then only we will give them the loan, not to um, self-employed, not to freelancers. We are going to give loan to only those people who have a permanent job. Then suppose we are going to give, yes, age of applicant. Age should be means greater than, right, age should be greater than equal to 25 and less than equal to say 50. Only these people will be getting the loan. Now, CIBIL score I mentioned, suppose CIBIL score is there, and I mentioned that they should have a CIBIL score of more than equal to 750. Correct. And then other things like number of dependents. Number of dependent means uh, how many people I have to feed if I'm earning. So if suppose I have a family of four and I'm the only one earning, so I have three other dependents on me. Okay. So it is saying that the number of dependents should be less than equal to three on a person. Then only a loan will be given. Because if a person has to take care of many people, then they will not be left with that much money that they can return the loan back. Okay. So suppose these are some of the hard and fast rules that we have made, fixed rules that we have made. And according to these rules, we will reject a person or reject a loan approval or accept a loan approval. Now, these are very hard and fast rules. Now, suppose tomorrow a person comes, let's say Priya, right? Tomorrow a person comes, Priya, and what she has submitted her all the information that the bank was asking, like monthly income, employment type, all these things. So let's say her monthly income is 49,900, and let's say employment type is permanent, like we need it. Then her age is say 32. Her CIBIL score. So CIBIL score is a credit score which is given from 0 to 900, right? And the higher the better. So her CIBIL score is, let's say, 800, and number of dependents on this person is 2, right? So let's say Priya is an applicant who wants a loan, and the information that we are asking, see, apart from this we can have lot of other information also, like what kind of loan is she asking. Is she asking for home loan, personal loan, car loan? Okay, what type of loan, for what tenure, how long she is asking the loan for, 10 years, 5 years, 20 years. Then does she have any running loan or not? Okay, means if she is asking for a home loan, does she have any other loan which is currently going on? We can have lot of other conditions also. Just for an idea, for keeping it simple, I've just mentioned some of the things that the bank will check to decide whether they should give loan to that or not. Now let's say we have made a software using all these rules, right? Using all these rules, we have made the software. According to that, if give all these details to the software and I want the software to tell me whether she should be accepted, means her loan application should be accepted or rejected. So what do you think will happen in such a scenario? Right. You see, these are our conditions that we have, fixed rules that we have put into a software. And if I have Priya, so what will happen according to that? Will her loan application be rejected or accepted? Right. So you can see the first condition was that the loan, the monthly income has to be more than 50,000. That's a rule I have written in my software, in that software. But on this case, on this side, you see that the monthly income is 49,900, just short of 100 rupees, or you can say 101 rupees. Then her income would have been more than 50,000. Then she would have got the loan. But see, apart from this condition, you see all other conditions which are there is properly met by Priya, right? All the other conditions are being met, but only the case is that one condition is not being met, right? The loan, the monthly income. But do you think it is logical to reject this loan application just because she's short of 100 rupees? Does it make sense for a bank? Because see, all other criteria she is fulfilling very well. So does it make sense to reject her? No, right? It is not logical to just reject if she has 100 rupee less than what we were asking for the monthly income, because 100 rupee difference won't make such a big difference. So if a person would have seen her loan, her application, they would have accepted that, right? But the thing is, we have made a software, and see, a software is once built, the software can't change itself. If you have written this logic, like if else condition you have written, right? Yes, if a software is going to reject that. And you see, can a software change its logic automatically? No. Because in a software, you write the conditions, you write the code. Software cannot change its code automatically. That is never going to happen. You know that, right? And you see, because you write, say, you are writing the code using Python and you have written if monthly income greater than 50,000 and employment type is equal to that and age is equal to this and CIBIL score like that. So you have written a if condition. Automatically, if condition will never change until you change it automatically. Right, but you have built a software at one point and you are going to use that software for let's say 3 months, 4 months, 6 months, and then you will change it or update it after 4 months, 6 months, let's say. But till that time, a lot of applications will be rejected just because of these small differences. Okay, now, so the thing is, what we can do to make it better, right? What we can do to make it better. So what we can do is we can instead bring machine learning here. Okay, we can instead bring machine learning. So what will machine learning do? Machine learning is capable of learning the rules and patterns much better than humans can do manually. Okay, so see, machine learning is what? Like I said, one by one, you will understand everything. Just I'm taking you to the story one by one so that it will become more easy to understand why we even care about machine learning. See, machine learning is nothing but a set of mathematical calculations, or you can say a collection of mathematical calculations and formulas using which you identify what is the relationship present in the data. Okay, so it will help us to identify what should be those rules and what should be those patterns which we should use to predict anything. So here we were predicting whether Priya should be given a loan or not. Means what we wanted to predict was that a loan application should be rejected or accepted. This is what we wanted to predict given all these information about Priya. Right. But in this case, because we have written a very fixed rule, a very hard and fast rule, because of that, lot of applications will be rejected if they are also on the boundary line. Just below the boundary line, or if we have, then they will be rejected. Okay, but in the real world, this kind of very rigid rule does not work well in most of the cases. So instead of us humans defining all these rules, like income should be more than 50,000 and all of that, we should let the machine learn from the data, that more and more data that is coming up, that is being collected. We should let machine learning learn from the data, and we should let it tell us that what kind of relationship is there in the data, and according to that relationship we should be rejecting an application or we should be accepting an application. And another benefit is that with machine learning, it's a code which can learn automatically, which can improve itself automatically. I do not have to code the rules for the machine learning to work. So it will learn the relationship present in the data itself, who should be given a loan, who should not be given. It will learn all that patterns and relationships, all the rules itself. And second thing, it will keep updating itself every day, every week, every month, however you set it, it will keep updating itself. Okay, means what I'm saying, if suppose on 30th May, till 30th May, whatever data was there, according to that, machine learning has learned the relationship or learned the rules that these people should be accepted, these people should be rejected. Now, over the next 1 month, 2 month, new data points have come up. New people have applied for the loan and they were accepted, rejected. On the basis of that, machine learning can update its rules automatically. Right? We will run it in such a way that it will run automatically. And as we update the data related to it, it will update the rules automatically. No human has to involve in that process to update those rules. And you can be very sure that whatever rules that machine learning is going to learn will be much better compared to what you can decide yourself. And see, the bigger the data becomes, the more complicated it becomes for humans to decide what exactly that rule should be. Okay, so let's understand that with one more example. Say I have to build an application for house price prediction. Suppose I'm working for a real estate company and I have to do what? I have to build a system or a machine learning system for house price prediction. Means given a house, suppose in a city there is a new house being built, new. It is being built and it will be ready in, let's say, 10 days, 20 days. And our company is a real estate is in real estate business. They have built that building and they have to sell the flats. So at what range they should sell the flats so that the people will be ready to purchase, and also we make good enough profit by selling that. Okay, like win-win situation for both. Otherwise, like if we keep the price too high, then the customers will go and purchase in another society for with another real estate company. They will purchase that. Okay, and our flats will be empty. We won't be able to make money. And if we keep the prices too low, then we won't be able to make enough profit that we have forecasted for us or expected from this. Okay, so we have to predict a very suitable price for that. Now, what we will do for this, you see, can you manually decide the price of the houses? Till some extent, you can say yes, according to the knowledge of the builder, according to knowledge of some person who has been in this for, let's say, 15 years, 20 years. They can predict a suitable price at to some extent, but you see, these prices are very dynamic, and there are a lot of factors in the real world which can change the prices, okay, or which can affect the prices because the market is changing a lot. uh, what is happening in the market overall can change the prices at which a house should be sold. Like recession could be there, or uh, you can say there is a boom in the economy overall, or a lot of people are suddenly trying to purchase a house. There is a, you can say, trend going on that more and more people suddenly want to purchase the houses. So according to some trend going on in the market overall, in a country overall, the prices can change quite frequently on the basis of that. So instead of manually deciding what should be the price of a particular house, given the features of the house, if we use machine learning, that will be much better. For example, see, suppose, and you see what we need to do here. Whenever we have to make a machine learning system for predicting anything in the future, we need to first collect some past data. See, if I want to do house price prediction, I will first collect the details of 100 or 1000 existing houses, suppose. Okay, first I will do what? To learn what should be the rules and patterns and relationship, we will collect the data about 1000 existing houses, for example. The more the better. But for example, say we have 1000 existing houses in an area, and we want to understand what way the prices change. Okay, what uh, dictate the change in the prices, what manipulates, or what you can say impact the prices in this area. So what I will do, I will first study all a lot of existing houses in this case, right? Directly, a machine learning cannot do the prediction of something. It has to first learn. So when we say machine learning, how it is going to learn? From some available data. Whatever available data we have, from this, it is going to learn. Okay, now you see, so suppose I am in Hyderabad, right? Suppose I am in Hyderabad, and city by city, the prices will change. Locality by locality also prices will change. Like in this area, it can be more expensive houses. In another area, it can be less expensive houses in the same city. So the thing is, for whichever area we want to make the prediction system or machine learning system, that area's houses I will take for that. Okay, so it means that if I am building a machine learning system using the data from Hyderabad houses, I will not use that same machine learning system to predict the price of Bangalore or Mumbai or Jaipur, like that. Because in every city, the factors which impact the price of the houses are different. So for whichever city I want to do this prediction, I will make a separate machine learning system for that by taking the data of that particular city. Okay, this you have to remember. You can't use just one model overall for all the cities because there are a lot of factors which will be different in multiple cities. So your learning will also be different about the relationship and the prices. Correct? Yes. So all of that you will see. But suppose now, uh, when we talk about machine learning, you have to first teach machine learning what it has to predict in the future. Okay. So think of machine learning like a child. Okay. Child means a newborn baby. Think of machine learning like a newborn baby. How is that relatable? See, when a child is born for the first time, they have no knowledge of the world as of now, but they are capable of learning anything you give them. Okay, they do not know anything when they are born for the first time. They have no knowledge of the world, but they are capable of learning anything. If you want them to learn economics, you can teach them economics. If you want them to learn engineering, you can teach them engineering. So they are capable of learning anything. Same way, we have our machine learning. So machine learning is designed in such a way that it is capable of learning from any data that you provided. But by default, it does not know anything. Directly, you can't use machine learning for loan approval prediction or house price prediction or car price prediction. Directly, you can't use that machine learning. Okay. So the thing is, you have a machine learning which is very similar to a child. A child does not know anything by default. Machine learning also does not know anything by default. Correct. So they have to be taught. Like a child has to be taught, then they learn something. Same way, a machine learning has to be taught what it is expected from them. So if you want to use machine learning for house price prediction, you have to first train it, you have to first teach it on house prices data. If you have to, uh, if you want to use machine learning for loan approval predictions, loan approval uh, use cases, you have to first teach it, right, on the basis of past data. See, so what I will do now, if I want to predict the house prices, what I will do, I will go to a particular city and I will collect the house details. So in that case, what I will collect? So I have suppose number of rooms, number of floors, then area of the house, right? Then you can say, what are the features? Locality of the house. Is it a posh locality? Is it a normal locality? Then, yes, furnishing status. You can have furnishing status. Correct. Yes. So you can take bunch of other details in that case. Now you see, suppose I am talking about these 5 things. Okay. Suppose you have these 5 things: rooms, floors, area, locality, furnishing status, all of that thing you have. And now you have price. Okay. So if I have to use machine learning, right? If we have to use machine learning for price predictions or something like that, see what we have to do first. We have to first collect the data of available houses or existing houses, because about the existing houses, what we know? So we know this. How many rooms were there? Suppose I have taken 5 houses in a area. So first house had 5 rooms in that, 2 floors in that, a area of let's say 1500 square foot, for example. Locality was a posh locality and it is fully furnished. It is fully furnished. And this house was sold for let's say $90,000, just for example. Okay, so what I'm taking a house which is already sold in the market, and we know what were the features of the house because we can easily see that, and at what price it was sold, we also know that. Same thing, right? Same thing, all these information we have, right? All this information we have, and the different houses have been sold for say $150,000. Then you have $200,000. Okay, then we have $50,000. Then we have, let's say, $80,000, right? You see. So suppose we have all these houses which have already been sold in the market already. In the past, they have been sold. So I know the features of those houses and at what price they have been sold. I know that. Right. Now, what I will do, if I have to train a machine learning system to be able to predict the price, a suitable price, given the feature of the house, what I will do first, I will provide this data to machine learning. Okay. I will provide this data to machine learning, and the entity to which we provide this kind of data is known as machine learning algorithms. Okay, there is something called as machine learning algorithms. What are algorithms? Algorithms are you can say a concept which has already been created for you. And you have to just use those algorithms to predict the prices, okay, or to do future prediction. So there is something called as machine learning algorithm. We are going to study more than 20 algorithms for different use cases, and we will be talking about how each algorithm work. But what is algorithm? Suppose you want to prepare tea, or you want to prepare curry, okay, any dish you want to prepare. So you follow a sequence of steps: step 1, step 2, step 3, step 4. You can't do random steps while building or while making a dish. You can't take random steps, it will not make the dish properly, right? You have to take step 1, step 2, step 3, like that, a sequence of steps you have to take. And that way, if you follow, then you are going to get a proper dish prepared for you. Same way, algorithm means a set of steps, a sequential set of steps that you are going to take for learning purpose. So this algorithm is a predefined, it's a pre-designed thing for you, which you are going to use. You do not have to create an algorithm. It has been already created for you by the researchers. You just are going to study them and you are going to use them, right? And you will see how they work. But algorithm is something which is designed for you already. And when you provide a particular data to an algorithm, it has a sequence of steps that it will take to learn from that data. Now, when I provide this data to machine learning algorithm, what do you think it is going to learn? Right. What I'm trying to make a machine learning system which will be prepared to do prediction. But now think about it, what it is supposed to learn from this data. When we say machine learning is learning from this data, think about what it has to predict in the future and what it will learn. Can we say machine learning will learn the relationship between these to these? Can we say machine learning will learn the relationship between the all the features of the house with the price of the house? Will that? Yes, because you see what it has to learn basically. If I'm saying that I have to teach machine learning something, what exactly I'm trying to teach machine learning? I'm trying to teach that there are some houses which have been already sold, and when their features were this, they were sold at this price. So what I want the machine learning to learn is, if the price was $150,000 of a house at which it was sold, why it was this much price? Was it because it has 3 floors in that? Was it because it had 7 floors in that? Was it because it had 2,500 square feet area in that? Okay. So, what is the reason because of which the price is this much? Okay. Which factor is impacting the price of this house? We want the machine learning to learn, right? Do you think only area or floors will impact the price? Or do you think all these things, locality, furnishing status, area, room, floor, will impact? Yes, obviously, all of them, right? All of them. If there is a feature which has no effect on the price, we won't take that feature. Okay, we won't take that feature if it is not going to have any impact on the price. We will be studying those features which have some impact on the price. So, our machine learning has to learn what? That if this is the price of the house, how much all these features are contributing in predicting the house. As a person, if I just give you these 5 features, can you tell me how much this is impacting the price? How much this is impacting the price? How much this is impacting the price? Can you do that? No. And I have just taken 5 features. Maybe you can do with the 5 features, but you see, uh, you have say 50 features, or you have say 100 features. Will that be any way possible for you to predict the price of the house? Right. If I take 50 features, 100 features, Will that be any way possible for you to predict the price of the house properly or identify the relationship with that? No, right? It will become exponentially difficult for you to manually identify how the price of the house is being modified. But can machine learning algorithm do that? The answer is yes, because it is designed specifically for this. Okay. Machine learning algorithm has been designed specifically to do this thing where we humans can't do a very accurate task. So machine learning, when it sees the data, it will be able to tell us how much each of these features impact the price of the house. Right? It will be able to tell us. So whenever we provide a data to a machine learning algorithm, it is going to learn from that data that what is the relationship. And after learning that relationships present in the data, what it will create something called as a ML model. You see, there are two things. There is one thing called machine learning algorithm, and then there is something called as a machine learning model. These two terms you have to remember for now. Only these two terms, anything else you don't have to remember. You see, so we have machine learning algorithm. Algorithm is what? It's a concept, it's a technique which has been created for you. Okay, algorithm is a technique which has been created for you, which will learn something. But after learning, what it will create? ML model. So when you get this ML model is the output uh, of a training process in machine learning. So to understand that, think of the child example. Suppose we have a child and we provide knowledge to this child. Okay. Let's say we provide knowledge to this child. So after we provide continuous knowledge to this child for 10 years, 20 years, what they will become? They will become graduate. They will become graduate in something after some time. If they continuously gain knowledge over the years, over their life, so they will become graduate in something and they will be ready to work on that thing. Now, suppose this child has studied economics very well. Can they do the task of computer science? Can they do the task of English literature? No. Whatever they have been taught, whatever they have become expert in, they will be able to do that task in the real world very well. Same is the case with machine learning algorithm also. See, you won't forget this. An algorithm, think of it like a child who is capable of learning. It's a concept which is designed for us, and you will see how algorithm look like. It's a concept which is designed for us, which is capable of learning. But if you provide a data of these house prices to this machine learning algorithm, to one machine learning algorithm, it will create a ML model. ML model is like that graduate child. Okay, you see. So in this case, we have this ML model, and what you have here is this is our final product that we wanted. Now, once we got this ML model, what we will do with this? So all the learnings this algorithm has got, from all those learnings, from all the relationships it has learned, it has created this thing which is known as a ML model. Okay, so what we will do with the ML model, or how will the ML model look like? Let me show you one example of that. Okay, let me show you one example. You will understand what is ML model. Say I take a simple data where I take number of rooms and I take the price of the house. Right, you see, suppose I just take a very simple data, number of rooms and the price of the house. Say a house has 4 rooms and it was having a price of $90,000. Okay, don't worry about if you don't understand dollars in this. Just see it is a price. You can take any price in your mind in Indian rupee if you're taking these terms. Say we have 4 rooms and the price is this much at which it was sold. I'm taking only one feature of the house, only rooms. No area, no uh, number of floors, nothing like that. Then suppose I have another house which has 7 rooms and it was having a price of say $140,000, suppose. Okay, now, so this is my data. And what we call this data we call it as a available data or past data. Past data does not mean old data. Past data means that it is available data. Okay, past data means that available data. Correct. You see. So suppose we have um these things, number of rooms and the price of the house. We have all these things. Okay. Now you can think like 4 rooms has a price of say 90 lakh rupees. Then this one has say 1.4 crore rupees in this term, if you want to say. So suppose these are different houses. Then we have five and its price was, let's say, $170,000, let's say something like that, say 1.7 crore. And then three, we have, let's say, 8 rooms and it has certain price, let's say $200,000. Okay, right. So these are the available houses, means they are the houses in which we have already uh, know how many rooms are there and what is the price of those houses. Correct. Now, when we provide it to machine learning, when we provide this data to machine learning algorithm, right? When we provide this data to machine learning algorithm, what it is supposed to do? It will try to learn what is the relationship between this and this. Okay, what is the price of what is the relationship between this and this? Correct. Now, how would it represent this learning? Because whatever it is learning from this data, it has to tell us that learning, only then we can use that. Right? You see, what you want to know. You want to know from this data that given a number of rooms, how its price is impacted. What is the contribution, what is the impact of a particular number of room in determining the price of the house? We want to know that. Then only we can tell that if there are 5 rooms in a city, then this much should be the price. If there are 10 rooms in a city, then this much should be the price. I want to know how much is the impact of a particular room in predicting the price of the house. Now see, in this case, I said when I provide this data to machine learning algorithm, it will create something called as machine learning model. What is the model going to look like? So a machine learning model, when I say, it is nothing but a mathematical equation which will represent the relationship between the input and output. It is going to be a mathematical equation. But see, if you are not comfortable with mathematics, no need to worry about it. Um, there are only one or two formulas that you have to remember, and over the time, you will automatically remember that because you are going to work on it multiple times. So when I say ML model, it is a mathematical equation which will represent the relationship between the input and output of the data. So you see, this feature that we have is called as input column. All the features of the house are known as input columns, and the price thing which we want to predict, this is known as our output column. Okay, output column or target column. And the features of the house are known as input columns. So basically, machine learning is trying to learn the relationship between input and output. But I want to tell you that how this relationship looks like. In what form it will show us the relationship between input and output, that I want to show you. So you see, the first algorithm that we are going to study, linear regression algorithm, starting from today itself, it will represent the relationship in this form: y is equal to mx plus c. Okay. In this form, the relationship between input and output will be represented. Okay, now see. Okay, why the equation like that? Suppose your x, suppose your x is your number of rooms and your y is the price that you want to predict. Okay, x is the number of rooms and y is the price. Can we have this kind of equation, y is equal to x? Will this equation make sense? The answer is no. Okay, this equation will not make sense. Why? Because can I say that if there are 4 rooms, then the house price will also be 4 crore? If there are 5 rooms, then it will be 5 crore. Will that thing will happen? No. Right? Obviously, you can say that we can't have a direct relationship between the rooms and the price. We can't say that if there are 5 rooms, then the price will also be like that much, 5 crore. Direct thing we can't say. Okay. So what we have to write is how much impact the number of rooms have on the price of the house. We have to write this kind of equation. Okay, so what this equation is, this equation can be written as y is our price equal to m into number of rooms, okay, plus a c value. Okay, so we have price is equal to m into number of rooms plus c. But now let's understand a little bit from where the M and C value comes up. I will be teaching that to you from where this will come up. But first understand that the first algorithm that we all are going to study called linear regression algorithm, that will give us the equation in this form. That will represent the relationship between the rooms and the price of the house from the given data in this form, in this kind of form. Now what we have to find out. Yes. So we have to find out the value of M and C, something called as M and something called as C. These two things we have to find out. Because number of rooms I know. I have a house and I have to predict the price of this house. So I know how many rooms are there. Rooms I know. But I have to know, I have to find out, I have to calculate what is the value of M and C in, in this case. But from where am I going to get the value of M and C? I'm going to get this value of M and C from the data. Okay. Anything that I'm going to learn, any relationship that I'm going to learn about the data, that is going to be done from the data itself. So when I study this data, I will be able to find out what should be the value of M and C. Okay. So for a simple idea, let me tell you what M represents, what C represents in simple terms, in non-technical terms. You see, it will turn out or it will change into something like this. We will have 1.12 into number of rooms plus say 0.80. Okay, so you see here something like this we need to find out. It is not a fixed value. I'm just showing you an example that your M and C value will look something like this. But in non-technical terms, what do you think this number is in the context of house prices? Right, because all of this is going to help us predict the price of the house. I just have to enter the number of rooms of different houses into this equation, and this equation will give me the price. So I have to once find out these and these values from the data once. And once I found out these values, I just have to keep changing the number of rooms, and I will just I will keep getting the price of the different houses. But now think about it. What do you think this number and this number represent in the context of house prices? Can I say that this value is the base price of the house? Means if suppose I put this value 0. Okay, you see, if I have this number of rooms, suppose 0, means I do not know the number of rooms of a house. So can I say this C value is how much minimum you have to pay in a city to purchase a house? Can I say it is that value? Means if I forget the number of rooms, how many rooms are there? Can we say that C value is nothing but the minimum price we have to pay to purchase a house in a city? Yes. Because you see, if you have price and if you forget this thing, if you forget this thing even exists, and you have only this number. So what can I say? That at least this much you have to pay, right? At least this much you have to pay to purchase a house in a city. At least this much. But only this much will not be the price of the house, means the price of the house will further increase or decrease on the basis of the features, but at least this much, minimum this much you have to pay. You must have seen starting point of or starting price of 1.8 crore, starting price of 80 lakh. Okay, so what is that starting price that you see? It is saying that without any amenities at all, this much minimum you have to pay. Correct? That is the thing. Now you see, on top of that, whatever number of rooms are there, it will further increase the price of the house. Now, what can this be? What do you think number is? Which is being multiplied with the number of rooms? What do you think that number is? If this is your base price that you have to pay, what do you think this number is? Can we say this is our weightage? How much weightage this particular feature has, this particular number of rooms has in predicting the price of the house? Think about it. Can we say that this is the weightage? How much number of rooms is contributing in predicting the price of the house or determining the price of the house? Can we say that this is the weightage? Okay, if this example seems too simple, suppose I have two features. Let's say I have price of the house and I say things like 1.12 into number of rooms. You see, let me add a few more features of the house. 1.12 into number of rooms. Then let's say 0.89 into say area of the house, and say 0.57 into number of floors in a house, plus say 0.87. Now look at all these numbers. Look at all these numbers. Can we say these are the weightages? Now, does it feel like all these numbers which are multiplied by the features of the house, can we say that these are weightages? How much this is contributing in determining the price? How much this is contributing in determining the price? And how much this is contributing in determining the price? Can we say that is what it is representing? Yes. So our values which are being multiplied with these features of the house, they are nothing but weightages. And you can see that all the features will not have the same weightage. You know that all the features will not have same weightage. Area can have more weightage, floor can have less weightage in predicting the price. So it depends upon locality to locality, area to area, that which feature will have more weightage or more importance in predicting the price of the house. So this particular thing, right, this particular thing that we see here is ML model, machine learning model. Okay, weightage means what? Suppose I have a house which has 4 rooms in that, 2500 square foot area, and 3 floors in that, or say 2 floors in that. Okay, so what will you do? You will say 1.12 into 4 plus 0.89 into 2500 plus 0.57 into 2 plus 0.87. It means your area of the house and your number of rooms and your number of floors is going to be multiplied by those numbers which are weightages, and the higher that number with which they are being multiplied, the more they will impact the price. Understood? Weightage means what? With what number are you going to multiply that? That will determine the price. And why am I writing like this? Because can you say that the price of the house is number of rooms plus area plus floor. Does it make sense? Does it make sense that I add all these three numbers and I get the price of the house? No, right? So you have to see, right? You have to see how you have to multiply the number of rooms, how you have to multiply the area, how much importance that particular feature has in determining the price of the house. You are going to learn that, right? So directly it will not make sense to just add up those numbers, but if you multiply them with a particular weightage, then you know that how much weightage each feature is having in determining the. Yes, so in simple words, if I tell you what is machine learning doing, it is helping us to create this type of equation, right? What is machine learning doing for us? Machine learning will be getting the data from us. What is the data? This type of data. You see, rooms, price, all these information I will give of the existing houses. And what will machine learning be responsible for? Machine learning will be responsible for creating this type of equation for us. And once you get this equation from machine learning, can you identify what is the relationship between different features? Yes. And can you use it for future prediction? Yes. So once you get this equation, you just have to put the value of rooms, value of area, value of floor. You just have to put these three numbers into this equation and you can get the predicted price. Correct. So what I'm trying to tell you, you are going to take a data, you are going to give it to machine learning. Machine learning's main task is to give you this equation. Okay, create this equation for you. Now, this equation will be created once on a particular data. Data to data, it will change. But on a particular data, suppose if I'm working for Hyderabad and if I'm making a model using Hyderabad houses, so in that case, I have to make this equation once from a data, once. It will not be that every single day it will change. No, I have to create it once from all the data that I have. And once this equation is created, now what I have to do? Now I just have to take the houses and see their number of rooms, see their area, see their floors, and I just have to put it into this equation like I have done here. I just have to put those values into this equation, multiply by that particular number, done. Okay, so create that equation and just keep using this equation to get the price of the houses again and again, again and again. You can keep using that. Perfect. So this is the idea about machine learning. And why did we even care about using machine learning? Because I was, if I have more features, say 10 input columns, one output column, or 20 input column, one output column. So the more the number of columns, the more difficult it will become for us to manually identify the relationship between those features. Okay, manually we can't tell how much the rooms have, how much impact the number of rooms have on the price. Manually, it is very difficult for us to identify or determine all these things. But for machine learning, it is extremely easy. And suppose if I manually want to do that, it might take me 1 month. And for machine learning, it will take 1 minute. So even if I can do that manually, it will be extremely difficult for us and it will be very much time consuming. I might find out that relationship if I do a proper research, but it will take 1 month, which the same thing can be done by machine learning in 1 minute. So why will I not use machine learning? Why to waste my 1 month into the same thing which machine learning can do for us instantly? This is where machine learning comes into picture, where we do not know what are the rules and relationship, right? Uh, in such cases, we use machine learning. If I know all the rules and relationship, I'll build a software directly. I'll do the software engineering. But in such cases where I do not know what are the rules and relationships, I will use machine learning because it will help us find out all those rules and relationships from. So before starting our first algorithm, I have to tell you one more thing and then we will move on to that. So there are various types of machine learning that we are going to study. Right. Right. So there is this thing, types of machine learning. What do I mean by types of machine learning? So first type of machine learning is called as supervised learning. Okay. So first one is known as supervised learning. This is our first one. But on what basis we know when to use supervised, what exactly this is? See, very simple. Data with input and output columns. If your data has input and output column both given, output column was our price. Input column was all the features of the house. So if in any data we know or we are given input and output columns both, then we are going to use supervised learning. Okay. Then there are some other data in which you do not have any output column, only input columns are there. So coming to that also. So first scene is we have something called as a supervised learning. And here we will be working with that data where we have input and output, right? And see the output column which is there, it is going to guide the algorithm. It is going to guide the machine learning algorithm, what it has to learn and how it has to learn that. Because output is telling that this is the output you have to be able to predict price of the house or whether the person will be rejected or accepted for the loan application. Output is basically deciding how that learning will be done and what it has to achieve. So equation will be created according to that to achieve that particular output, right? So output is going to do the supervision. Supervision means guide. It will guide the algorithm to learn the relationship in a particular way so that that equation can be able to predict that kind of output. So when outputs are there, we call it as a supervised data or a label data. Output is known as label. Now in supervised, inside supervised, we have two further types. Okay, one is known as regression. Correct. One is known as regression and one is known as classification. Now, what is that? See, these are two things which are present inside supervised learning. But what is this regression? So if your output column, if output column is numerical, okay, if output column is numerical, then it becomes a regression task. It becomes a regression task in supervised learning, such as in the house price prediction, what was our output column? Price column. So price are numerical values, right, that we want to predict. So that becomes a regression data, or on that, on house price data set, I will be applying a regression algorithm. Again, don't worry too much about it. You'll understand every single thing after some time automatically. And then we have classification task. What determines the classification task? So if output column is categorical, categorical, then it becomes a classification task. See, both of them have output column. Both of them have output column. That is why they are a part of supervised, because in supervised learning we have that data which has output column. See, input columns will always be there. The thing is, in some cases output column is there, in some cases output column is not there. Okay, so if output column is there, it will be in supervised learning. But in supervised learning also, depending upon the type of output column, you have two different type of tasks. If your output column is numerical, it becomes a regression task for us. And if our output column is categorical, it becomes a classification task. Categorical means what? That loan approval thing that we were talking about, rejected, accepted, right? Loan should be given or not, or loan application rejected, accepted. Here we are not predicting any number, but here we are predicting rejected or accepted two categories. Okay. Then another thing can be that given a credit card transaction, is it a fraud or not? Is this transaction fraud or not? Okay. Or given a patient's medical condition, is this patient a heart disease patient or not? Or heart disease patient or healthy patient, healthy person? So here we are going to predict the categories, not numbers. Okay. So our output column will also be categorical in the form of yes and no, basically. Right. And in these two cases, we are going to study different algorithms for regression and classification. You will see about that. Then comes the next one, which is known as unsupervised learning. The next one that comes up is known as unsupervised learning. In unsupervised learning, what we have is only input columns, no output column. Only input column, no output column is there in the data. Now what we will do then? Because I have explained to you all the things that there will be input column, there will be output column, and machine learning will learn the relationship between input and output. We have been discussing about that. But what if your output column itself is not there? Then what will you do? So in such cases, we do a very different thing. What we do now, here we do not uh, try to find out the relationship between input and output because output is not there, output column is not there. What we do in this case, we perform a task called as clustering, which is nothing but grouping similar data points. Okay, so in this case, we are going to make groups of the data. So suppose I have been given a data in unsupervised learning and it has only input column, no output column. So for example, I have data of Amazon, right? Suppose I have data of Amazon customers. So Amazon has a lot of customers. What are the things Amazon will know about the customers? The Amazon will know name of the customers, age of the customers, location of the customers or address of the customers, right? What purchases they have done, okay? Purchases they have done, past purchases they have done. These type of things Amazon will know about a customer. Suppose I take four features for example. These things Amazon will know about us. Apart from that, a lot of other things they will know. How much we like to spend, in what range we like to spend, okay, from our previous purchases. So suppose Amazon has the data about the customers and these four information Amazon has about the customers. Now, on the basis of which there is nothing to predict in this. You are not going to predict anything in this out of these four columns. So what else can I do? So I'm going to divide all these customers into various groups. I will divide the people into, let's say, three groups or four groups or five groups. Okay. In simple words, we can divide the customers into one group, which are all the uh, low spenders. Spending wise, low spenders. So all the people who like to spend less than 1000 rupees when they purchase something, they are low spenders. Then we can have mid, or we can say mid-level spenders. If I take one example for now, one feature, the spending habit of a customer. So there are mid-level spenders who like to spend 1000 to 10,000. And these are till 1000. Okay, they are till 1000. Sorry. Now this can be high spenders. They generally spend more than 10,000 rupees. Right. So you see, just on basis of one feature, on the basis of spending habit, I have created three groups. If I bring in other features like age of the customers, location of the customers, city wise, state wise, I can make a lot of groups. Okay, so all the people, if suppose uh, Amazon has say 1 million customers or 10 lakh customers, and what they want to do, they want to identify how many customers are low spenders, how many medium spenders, how many high spenders. So on the basis of this criteria, their spending habit, they will divide those people into multiple groups like these. Okay. And that is what we do in the case of unsupervised learning. In supervised, where we have input, output both, we try to learn the relationship between input and output. Here, in unsupervised learning, we perform clustering. Clustering is a process of making groups and dividing our data into groups. Okay, so all these 1 million people, all these 10 lakh people will be divided in these three groups. All those people who are low spender will be put into this group. All the people who are mid-level spenders, they will be put into this, and they will be put into this grouping of. We understood we will make the groups here and divide our customers into this group. But what is the point of making the group? Yes, there can be multiple things that you can do. Okay, see, one thing we can get to know is how much people like to spend. Okay, see, if suppose there are a lot of people, right? There are a lot of people in this group. So suppose out of all the customers we have, 70% people we have put into this group. Means 70% of our customers are such that they are low spenders. Then 20% customers are such that they are mid-level spenders and 10% only are high spenders. So if this is the case, what we can do to make these into these? Because directly they will not become these customers. So we want that the low spenders should become mid-level spenders. Only then Amazon will make more money. What we can do? So we can improve our recommendation. Okay, we can improve our recommendation that when these people, these low spenders, when they come to Amazon and they are searching for a product, we should show them such type of recommendation that they will like to purchase. Okay, because it is not the case that, right, it is not the case that all these 70% people are incapable of purchasing expensive item. They can purchase, just that they might not have seen anything convincing to purchase any expensive item. But if I show them good offers, good coupons, discounts, and proper products, okay, so they might be able to purchase, they might be ready to purchase some expensive and mid-level products. So the point of making group is to be able to give proper coupons, offers, discounts, recommendations group wise. Okay, same recommendation, same offer, same coupon, we won't give them. So depending upon group wise, we can give different coupons, different discount, different recommendations. Okay, so that is the point of making the groups. Perfect. So these are the two type of learnings I've told you, one without output column, one with output column. And then there are other types of learning also, like self-supervised learning, semi-supervised learning, transfer learning, reinforcement learning. Other types of learnings are also there, which we will understand one by one. Because if I tell you 5, 6 at the same time, you won't remember that. So one by one, as we move forward, I'll keep discussing about more and more. So till this point, whatever I've discussed with all of you, that was introduction to machine learning, basic introduction to machine learning. Now I'm going to take you towards the first algorithm, which is called as linear regression algorithm. Regression. This is our first algorithm which we are studying, and it is a regression algorithm, as from the name itself you can see, which means that it will be used in those cases where output column. Get started with that. First thing, to help you understand how does linear regression work, how does our first machine learning algorithm work, I'll take a simple data for now, and with that I'll explain you its working, and slowly we'll try to make it more advanced. So beginning with this, suppose I have a data in which I have um, area of the house and the price of the house. That equation I was telling you, y is equal to mx plus c, that equation where we were having 0.87 into area, 1.12 into number of floors, all those things that we were writing, that will come up in this first algorithm itself. So how that will come up, why do we write that kind of equation, you will understand each and every point. So starting with this, suppose we have two columns here to begin with, area and price. Area is our input column, it's our input column, and price is our output column. Right? Area is input and price is output column. Now in this case, we have 0, 1, 2, 3, 4. We have multiple houses whose area I know. Say one house has 15 square foot area, 18 square foot area, 4,200 square foot area. These are different houses and they have their prices. And remember this thing, first we teach a machine learning on a particular data, then we can use that for future predictions. So first I will collect the data of those houses whose price and area I know. Both of these things I know because this house has already been sold in the market. Now what I want is the machine learning should learn the relationship between these two things. And then if I tomorrow give a house of let's say 3800 square feet, it should be able to predict this. But directly it won't be able to predict that. First, we have to teach it on available data. Then it will learn the relationships present in that data. Then it will be able to predict the price of the future houses whose inputs I provide. Okay, now also another thing, if I train the machine learning on the basis of one feature, then I can use it to predict the price using that feature only. If I have only used area input column, only one input column to teach the relationship between input and output, I can't use the number of rooms, number of floors in this case. So if I want to use certain features, I have to take the data related to those features also in my training data. Okay. Otherwise, it won't know the relationship and it won't be able to predict that. Because if you have not given the number of rooms, it won't be able to learn the relationship, how much rooms are impacting the price of the house, how much they are contributing. They have not learned. So if they have not learned, how they will be able to predict on the basis of that. Right? So that is the thing. So first, you see, in the process of making our machine learning model, remember machine learning model is our final product that we want. How will that look like? Like that mathematical equation I told you. But to come to that, there is a story which we will see in a simple words, and we will get to know the technicalities. Say I have this data, two columns which are both numerical. Which is the most suitable plot to represent two numerical columns? The scatter plot is always the best plot to represent two numerical columns. Okay, there is a line plot also which can be used in this case, but line plot is better used in that situation where one of the column is time related. Okay, in that case also we have two numerical columns when we make line plot, but in that case one column has to be time related, means one of the columns should be month, year, day, hour, minute, something like that. It should represent some sort of time. And another column can be a numerical column, like month-wise revenue, day-wise revenue, month-wise stock market price, day-wise stock market price. Okay, so two column, but one of them has to be time related. Then we use line plot. But when we talk about two proper numerical columns like that, then we use a scatter plot to visualize. So now I have these 7 dots here, and each dot is representing one house. So say that this is a dot which is representing a house which has this much area and it has this much price. Okay, so this is a dot representing this much area, this much price. Like that, we have 7 houses, for example, whose area I know and price I know. This is visualization. When I'm making this scatter plot on the basis of the data, we are doing data visualization. Now what I want to take this one step further, and I want to apply machine learning on this data to represent the overall relationship between input and output. So what we do in our first algorithm, which is linear regression algorithm, when I say algorithm, remember it is a concept which is created for you, and it has a sequence of steps in which it learns something. And that you will see what are those sequence of steps. So in linear regression algorithm, we need to pass a line through the data such that it is closest to all the data points. So what is learning for us in linear regression? What is ML model for us in linear regression? It's basically a straight line which is passing through the data, which represents the relationship between input and output. So you see now we have all these data points, which was our scatter plot. And using linear regression algorithm, we have to fit a line, a straight line, which is passing through the data. Now, there is a property of this line that this line has to be closest to all the data points, not just any random line which is passing anywhere. Okay, not just any line which is passing from anywhere from the data. The property is such that, right, the property is such that it has to pass closest to all the data points. Right, it has to pass closest to all the data points. And there will be only one line which will be like that, right, which will be like that, which will have which will be closest to all the data points. You can't have two lines which will be closest to all the data points. Only one line will be possible. And you see, this line is known as regression line. Okay, this line is known as a regression line. And this line is basically our ML model. Right. This line is called as a regression line, which is, in simple words, our ML model. So algorithm is linear regression, and what is the ML model linear regression is creating? This straight line. Okay, so the concept of linear regression is very simple. Take a data and make a straight line in such a way that it is passing closest to all the data point. What do I mean by closeness? Why do I talk about closeness? All the things I'll explain. But a line which is passing through the data points and closest to all the dots is going to be our ML model in this case. Okay. Now, yes. Now there can be multiple regression lines. If I make any line passing through the data, they will all be regression lines. So there can be hundreds of regression lines that can be passing through the data, but only one of them will be best. And we call that as a best fit regression line. Okay, so what I'm saying is, if you pass any line through the data, it will be called as a regression line. But there can be multiple lines possible. So you have to find out of all the possible lines, which is the best line. Right? And that best line will be called as best fit regression line. Correct? Best fit regression line. Perfect. So let's see how we will build that. How we see. Now, what is the point of making inequalities? See, the first thing is once we have the regression line passing through the data, suppose once we have created that line which is passing through the data, then we can use the line to make predictions, or we are going to use that particular line to make future predictions. How? You see. So notice on this graph and you will understand this. Right, you see here, or if you look at this, this is our regression line. This straight line that you see here, this is our regression line. Now, once I have made that line, why am I so focused on making this line? What will I achieve with that? So the predictions I was talking about, the future predictions that we have to do, will be done using this line. But why? See, this line represents the relationship between, you see, the line represents, this particular line represents the relationship between this and this. Okay. And when I use this line to make the prediction, so basically I'm using the relationship that I've learned to make the future predictions. Okay. So I'm using the learning to make the future predictions. So this line represents that learning that we have done about the relationship between input and output. But what we will do now, see, all these pink points are those houses. All these pink points, these 7 pink points are those houses whose area I know and price I know. Area I know, price I know. Area I know, price I know. So these are actual houses with actual area and the prices. We know that. Okay, now, so you see, at this point we have this. And what we can do now, we have made a line which is learning the relationship from this given data. What we will do with that now? Now tomorrow, and you see, once you have made this line, it means that your learning has been completed. Creation of this line means that learning part is done. Now what will I do with this line? I will use it for future prediction. So suppose tomorrow I get a house, right? Tomorrow I get a house which has 2500 square feet area, right? We have a house which is having 2500 square feet area. So according to the data which we already have, what should be the suitable price for that? How can we predict the price of this particular house which is having, let's say, 2500 square feet? Can you directly uh, tell what should be the price of this particular house which has 2500 square feet area? You can make a guess, and your guess might be right also, might be wrong also. But what we are going to do now, this line we have created, it has learned the relationship present in the data, and it will help me predict the prices properly. So what will I do now? To predict the price, I will take this data point, touch it on the line, and wherever it is touching, from that, touch it on this y-axis. So you see now, this is a line I have made. What I'm doing with this, this data point I'm touching on the line, and then I'm touching it here, and I get the predicted prices for that. You see, this is the point where it is touching. So what do we get from that? How are we using this line? So I take a new data point, input whose output I do not know. I want to predict that. So I take this house which has this much area. I touch it on the line. Wherever it touches, from then I make a very straight line touching this y-axis. So this is the predicted price for this particular house. Now, did we do this randomly? No. Did we make a guess? No. What we used? We used the learning which this line has done, okay, to make the prediction. How did we make this learning? This learning we have gotten from the data, available data. Correct. So we have got a available data, all these pink dots. From that, we learn the relationship. And then using that relationship, we predicted the price. So where is that relationship? This line is that relationship between input and output. And once we have made this line, you see, I will just take any house and I will get the predicted price according to this. Suppose I have a house here, this much area. I will just touch it on the line and I will get the price. That's it, right? That's it. This is the entire concept of linear regression in simple words. Okay, if you understand this much, this is the main concept of linear regression. Take a data, make a line, and then uh, just keep using that line to make the prediction. That's it. I take a house, touch it on the line, that's it. Okay, this is the main thing. But it is not completed here, right? It is not completed here. What is a problem we will face in this case? One challenge. What will be that one challenge? Yes, twist has to be there, of course, because if this much was the machine learning, then everyone would be able to learn that, and you won't be getting that much of high salary just for learning this much. Okay, yes. So small challenge is there, and we will fix that also very easily. Trust me, we will fix that also. But there is a challenge. What is the challenge? So all of you understand, we are humans, and we humans can see that this line looks like it is passing close to all the data points. But can the algorithm see that this is a line passing through all the data points? Or suppose if I make a line here, will the algorithm know that this one is passing through the data or not? Right? The algorithm cannot see like us. Okay. So this line has to be made by whom? Who has to make this line? You see, this line has to be made by the algorithm. This line that you see here, it is going to be made by the algorithm. I am just going to provide my data. I will just provide data to the algorithm. This line will be made by the algorithm. So the problem here is, a small problem here is that how will line know, or how will the algorithm know that this line is better, this line is better, this line is better, this line is better? How will it know? Okay, suppose you close your eyes. Okay, you close your eyes, and if you close your eyes, how will you know that this line is the best one, or which line out of these is best? How will you know? So you need to have some calculations, and if you know some calculations, then only you can tell that this line is best and this is not best. What will be that calculation? Measure of distance. Okay, so if you notice that the line which is best is closest to all the data points. You see now, suppose if I take this line versus this line, which line is closer to all the data points? This black one. Okay, this black one is closest to all the data points. Okay, and closeness with all the data point is a measure to identify whether this one is. I have these two columns, and I've shared these inputs and these price. And I said that if you just visualize that, if you just plot this data, then you will be using a scatter plot for that, because scatter plot is the best option to represent the relationship between two numerical columns. So you have plotted a scatter plot where there are 7 points and each point represents a row. Okay, so from now onwards, whenever you see a dot being plotted, remember that one dot is representing one row of data. Simple thing. Okay, always remember this in mind. And what each is telling, that this is a house which has this much area and this much price. That is what these dots are telling us. Okay, now once you have this data and you visualize it and you see this scatter plot, this is just a data visualization. But if we talk about the linear regression algorithm, we need to pass a line through the data such that it is closest to all the data points. Okay, so what we need to do in linear regression, a simple thing, a very, very simple thing we have to do, which is we just need to pass a line through the data in a manner that the line is closest to all the data point. Means if I check the distance of the line and all the data point, it should be closest. Means there should be no other line that should be closer to all the points compared to this line. Okay, so I have to take the line in such a manner that the line is closest to all the data point. And how will we check the closeness? I'll tell you those calculations also. That is the main thing. But it is as now. So this is the main concept that linear regression says. So now, if I do that, if I pass a line through the data such that it is closest to all the data point, it will pass somewhat like this. And then we have a line which is known as a regression line. And this is also called as our ML model, because in machine learning, what we have to do, we have a data and we give it to machine learning algorithm. And what we get as a result, ML model. So remember, ML model is that thing which you want to create, because that is your trained product, you can say, that you want to achieve. And once we have this ML model, what we will do, I will keep giving it the house details and it will keep giving me the predicted prices. So once you have created this ML model, once you have to create this ML model and you just keep using that, right? So ML model is this line, and this line will convert into that equation of y is equal to mx plus c, which you will see in few minutes. It is very easy to understand. One by one, we'll try to understand. So our main focus is to make this line. Once we have made this line, our training process is completed. So when we are in this process of teaching this thing or creating this line on the data, this process is known as the training of the machine learning model. Okay, this process of creating this line in linear regression is known as training of the machine learning model. We are training it, we are teaching it on the basis of a given data. Right. Now, once the line is made, why we are focused on the line so much? What we have to do with that? So the next thing is, once we have the regression line passing through the data, we can use the line to make predictions, or we will be using the line to make the predictions. How? So I just take any future input value, means future input means I have a house whose area I know, but price I do not know. I have to predict that. So do a simple thing, just take that dot on this line somewhere, because this line is representing area of the house. Right. So you take that house, put it somewhere, then touch it on the line and then touch it on the y-axis. So this is the predicted price for this particular house. Okay, whatever that number is, we will be getting all those numbers. But for that house, that is the predicted price. Same way, if I have a house which has this much of area, I will just touch it on this and I will just touch it on this and I will get the predicted price of this particular house. So you see, now I have to make this line once and then I just keep using it for multiple inputs and I keep getting the predicted prices through that line. But the thing is, how good the predictions are, how accurate the predictions are, how do we know? We will do all those performance testing also, accuracy testing also, that how accurate the predictions are supposed to be. How do we know that? So if I'm getting the predicted price, it is sure that you are not going to get 100% accuracy. Okay, you can't predict the things with 100% accuracy. So if you have predicted a price of the house, it will be little less or more compared to uh, right. You'll get to know little less, or you'll get little less or little more price compared to what the actual price of the house is. Means in some cases your uh, price can be very accurate that you have predicted, but in most of the cases the price that you have predicted will be little less, little more compared to what it should be. But the thing is, we want that our predicted value should be as close to the actual as possible. Whatever the actual value is going to be, whatever the actual price of this house is going to be, right? So we need to predict its price as close to actual as possible, right? So all of the things we will see that very well. This is the main concept of linear regression. Take a data, make this line. Not just any random line, a line which has a property that it should be closest to all the data point. Once we make this line, then we just take a data point. What is this dot? You see, I'm saying we have a new house that we have built and we need to predict its price. So this dot that I'm making here, I'm saying it as a future input. What do I mean by future input? It is a house that we are building or we have just built it new and we have to predict its price. Okay, so whenever I say future input, remember that I'm talking about something that we have just now got or we are going to get that. Okay, so we will know these values and we have to predict the price of. Now, there is one small problem uh, that we will be talking about. The thing is, but there can be many such lines passing through the data. And each line would give different prediction. Let's see an example using two such lines. I said that you have to pass a line through the data, right? And I also said that it has to be closest to all the data points. But you see, when we talk about this working, who is creating this line for us, right? Who is creating this line for us? This line is going to be created by the machine learning algorithm. Correct? This line is going to be created by machine learning algorithm, not us. Right? Yesterday I told you that when this line is going to be created by machine learning algorithm, will it be able to create your line directly that this is the line which is the best one? Will it be able to create it directly? The answer is no. It has to create that line, but will it be able to create that directly in the first step? No. In one go, it can't create the line that you want. So what is the problem? See, the problem is that you have all your data points like this, and you have to make a line which the best one is going to be passing through the data points such that it is closest to all the points. This is going to be a best line. But does your algorithm know that this is the location where the line has to be created directly? The answer is no, because you see, it can't see like us. Okay, it does not have the capability to see the diagram like us and be able to tell that, okay, now this is closer to all the points, here the line should be. It can't see. So then uh, how would it decide that this is the best line, not this? How would it decide? So understand one thing, what will happen in this process? What will your machine learning algorithm do to find the best line? It will make multiple lines passing through this graph everywhere. It will be making hundreds of lines. Okay, it will make hundreds of lines in this graph, hundreds. And what will it do? It will check what is the distance of this first line from all the data points. What is the distance of the second line from all the data points? What is the distance of this one from all the points? What is the distance of all of this line from all the points? Then same for this, same for this, same for this, same for this, this and this. Suppose it has made 10 lines like that, for example, then it will check which means what is the total distance of all the lines from the data points, right? It will check that. Then what it will do, it will compare the total distances of each lines with each other. And the line which has the least distance, suppose the line number 6 has the smallest distance, the least distance from all the points together. Then it will say that, okay, this is our best line. Okay, this is our best line. So you see, because it cannot see where the best line should be, it will go through this kind of process. It will make multiple lines, and through the calculation of distance, it will be able to tell which line is best. Okay, sounds logical, I hope, because the distance is one of the measures which will help it to identify that this line is closest to all the points or not, or is there any other line which is more closer to the data points. Correct. So what it will do, it will have to make multiple lines and check the distance of all the lines one by one separately, and whichever line has the smallest or the least distance from all the points, that line will be considered to be our best line. Okay, so this is what we are going to do. So that is why I have written here, there can be many such lines passing through the graph overall. We have to finalize one. Our final line will be only one always. But if I'm just saying that we have to make regression lines, we can have multiple regression lines. Any line which I make here in this graph will be called as the regression line. Okay, so the final one will be only one, not two. But there can be multiple lines. And I want to explain to you what is the problem with any other line. What if I'm saying that this is my best one, which is one, but what if I have the second line? Why do I need to search for the line which is closest to all the points? Why can I not just use any line? Okay, what is the problem with that? See, let's understand that problem. Why you can't just use any line? Why you need to search for the perfect one which is closest to all the data points? What is the reason for that? Let's see. So suppose I have two lines which are both passing through the data. One is best, one is not the best. So what will be the problem? Suppose I take this house, and how do you make the prediction using the line? So you touch it on the line and then you touch it on the y-axis, you get that predicted price. So you notice that for this house, if I touch it on this line, second one, and if I touch it here, this is the predicted price of this house according to line number 2. And the thing is, if I touch it on this line, then this is the predicted price of this house according to line number 1. Now, would you like to have two different prices for the same house? Would you want to have uh, two different predicted prices for the same house? No, you do not want that, because it is just adding to the confusion. The more prices you get for the same house, the more confusing it will become for you that which one is the best. So you definitely want one price that is the best or most accurate price predicted uh, for you, and you want to use that. You do not want multiple prices for the same house. So the concept is that our best line is going to give us the most accurate prices, and any other line if you use, that will give you not the best price. Okay, not the accurate price. Only one line is going to give you the most accurate. Now see, as we can observe above, each line gives a different predicted output for the same input. And that is the reason why we cannot just randomly use a line, because if I randomly pick a line and start using that, right, correct? So when we are just randomly picking a line and we are using that, then what will happen? You will get a prediction, but that is not going to be very accurate. So you have to find out the perfect line which will give you the most accurate prediction. Now, so the thing is, so which line to use then for the final prediction? The thing is, then which line we should use? The regression line we use finally is the one which is closest to the data points, since that is the line which has learned the relationship between input and output with least errors. And this line is called as best fit line. So what is written here? So it is saying a simple thing. These lines are saying simple thing, that which line then you will pick finally to use for future predictions. So you will just pick a line which is closest to all the data point. But why this closeness matters, that I'm going to explain you now. I have said that the line should be closest to all the point. That is the line we want. But why? What is the benefit of that? Why am I focused on such a line which is closest to all the data point? So the idea is that the line which is closest to all the data point has learned the relationship between input and output with least errors. Why we are using the machine learning algorithm in the first place? Because if you remember, uh, I was showing you this, that I have a software engineering approach where I have to write the rules myself, right? Where I have to write the rules myself, all these rules. But I want that the machine learning should help me to write the rules. I should not be writing the rules. Because if I am writing the rules, I may be wrong at many places. I may not be able to capture the correct rules in that case. Right. So I want to use machine learning so that machine learning can write the rules for me. And machine learning should not be asking me to write the rules. Correct. So that is the reason, that is one reason why we want the machine learning, why we want to use the machine learning. Okay, because we do not want the rules, or we do not want to know the relationship present in the data. I want the machine learning algorithm to itself identify all the rules and relationships present in the data. Okay. So the line which is closest to all the data point matters to us because that is the only line which has learned the relationship between input and output with least errors. Okay. Any other line if I pick, they have also learned the relationship, but with more errors. They have not learned the relationship present in the data that much accurately compared to this line. Okay, and such a line is known as a best fit line, or you can say best fit regression line. Now, let's understand what do we mean by, and understood this. So what I said here, that why do we care so much about a line which is closest to all the data point? Because a simple thing is that the line which is closest to all the data point has learned the relationship between input and output most accurately. With least error means most accurately. So obviously you want that line which has learned the relationship between input and output most accurately with least errors. Okay. You do not want a line which has learned the relationship with less accuracy or with more errors. You do not want that. So the line which is closest to all the point has learned the relationship present in the data most accurately, and this type of line is known as a best fit regression line. Okay, so it means that all these lines that I made here, they are all called as regression line, all of them. But only one of them is going to be called as best fit regression line. Best fit means that line is learning the patterns most accurately present in the data. Okay, right. Now see, there is a term I have used here, least error. What do I mean by error? What does this error represent? And why am I using that in the first place? Let's see. What do we mean by an error? So I have plotted the data points here. For example, all these pink points are those houses, right? You see, all these pink points are those houses whose prices I know, actual prices I know, right? And you see, the line which I'm making here is trying to understand the relationship which is present in the data. Means relationship between area of the house and the price of the house is being represented by this particular line. Okay, now the line being straight is saying that overall the relationship between area of the house and the price of the house is linear like this. Okay, so our line is supposed to represent the relationship present in the data, present between input column and output column. That is what we want to study, right? So you see, when the line is being made, when the line is being made, it is passing close to data points. Some dot it will touch and some of the dots it will not touch. Okay. So now there is a difference between, or you can say there is a distance between the dot and the line. Okay. This distance we have to understand how much well our line has understood the patterns present in the data. So see that if I have, you see, so there is one line that could pass like this. Touching each and every data point, it is passing like this, right? So now if a line is passing through the data points like this, then it means that your line is trying to learn each and every data point as it is. Okay. Now this can be one line that can be created, touching each and every data point. Okay, because touching in each and every data point means that your line, which is made by the linear regression algorithm, is trying to learn the information present in this data point. Okay, it is trying to learn that if this is a house, what is the exact price of that? It is trying to learn. But you see, this is not the best thing to do. Touching each and every point to learn that is not the best thing to do. Why it is not the best thing to do? Because imagine you have thousands of data points, which is very normal. You will be working with thousands of data points and you have all these. So, right. So what your algorithm has to do? So technically your algorithm has to touch all these points like this, technically. But is it a good thing to do? Let me show you whether it is a good thing to do or not. Because if you see, if it is touching all the data points like this, do you understand any pattern from the data? Do you understand what kind of relationship is present in the data? The answer is no. Okay, if you are touching all the dots like this, technically when we make a machine learning model such as this line, technically it should touch all the data points. But if you go ahead and do that, then you won't understand any type of relationship present in the data. Okay, something like this will be created and you won't understand whether the relationship is linear or it is like having a curve relationship or is it having this type of relationship. You won't get that because it is so random. Okay, and the points can be also connected like this. It can be connected like this depending upon the rows of the data, which will even make it more confusing to understand. Right? This is not any relationship that you would want to know present in the data that you can use further. Okay, this type of things we won't do because it will not make sense to us. And there is another problem here. In this case, if your algorithm is touching all the data points, it is trying to touch all the data points, then what it means that your algorithm is remembering the given data points. It is not understanding the overall pattern present in the data. It is trying to remember the data points. Now, what problem will happen because of that if it tries to remember the data points? It means that tomorrow, if you give a house which is one of these, right, which is exactly same as one of these points, then it will be able to answer it perfectly. But otherwise, if you tomorrow give any point, which is this house, now you see it won't be able to predict the price of this house very well. It will make a very big mistake. It will give you the price of this house very inaccurately. because it has not understood the general pattern present in the data. It was trying to remember all the data points. You do not have to remember the data points, or your algorithm does not have to remember the data points. It has to identify what is the overall relationship present in the data. Then it will be able to make the prediction for this new data point also very well. But if it is touching all the points, if it is remembering all the points, then it won't be able to predict for new points. See, the idea is that suppose you have a student. Now that student is very hardworking and they want to get as much score in their examination as possible. So one thing this student can do is mug up all the answers. Mug up means remember. Ratta marna, what you say, is mug up all the answers of a particular subject. And second thing is try to understand the concept. Understand the concept overall. Now, who will be able to answer most of the new questions? Right. Who will be able to answer new questions very accurately? Right. So it will be second student. Right. Second student will be able to answer new questions very well because this student can only answer those questions which was taught to the student or which the student has remembered by heart. This student will not be able to answer any question properly if it is new. Okay, if you change anything in the question, they won't be able to answer that properly because they do not understand the concept, they just mugged it up. But in the second case, this student has understood the concept, right? This student has taken the approach of understanding the concept. So they will know what this concept is all about. And if you give them new questions, they will be able to answer that. So this is that student, which is your first one, mugging up all your data points, remembering them. And this is your second student who is trying to understand the overall general pattern present in the data so that it can predict any new given points more accurately. Understood this thing? So this we can't do. That is why the next best thing we have to do is we have to represent a simple pattern by making a straight line like this. Okay, now I have made this line which is representing that the relationship between the area of the house and the price of the house is linear. Okay, straight line, linear like that. Now, is it good? If it is good, then how good it is? Let's understand that. So for that, we need to take the help of something called as an error. What is an error? Let me tell you a few more things. But you see, there is this concept called as error, which is going to help us to identify that which line is best. And if this is my best line, then how accurate it is going to be in the future predictions. Error will tell me two things, means how much I can trust this line. If it is giving me any prediction, how accurate it is going to be. And second, the error will also help me to identify which line is best on this particular data. So you see, what is this error? Error is basically a distance between the dot and the line. That distance is called as error. But why? Why is it called as an error? Error in what? Let's see. So I told you that uh, when you make this line, it means that your learning process has been completed. So suppose I have this line here and I want to know how much error it has made. And same thing I will do for multiple lines and then I will compare which line has the least overall error, least total error. So suppose I have made this line here and I do not know whether this one is best one or not. I am in the process of finding that. So I made this line which is passing through the data somewhat like this. Let's see how much total error it has made. But what is error? See, suppose I've got this line here and getting this line means that learning has been done. And this line is representing that learning, that pattern it has understood. So now what I can do, I can take a house which I touch on the line, right, which I touch on the line and I touch it here. And this is the predicted price of this particular house. That is how we keep using the line. Okay. But you see, the simple thing is this. Before using this line, I want to know how much total error it made in the learning process. So for that, what we will do, you see, I will knowingly take a dot here, right? I'm taking a house which has this much area, right? And why exactly here? Because for this particular house, if I'm taking a house somewhere here, you see, for this particular house, I can check something. What I can check, you see, what way I will get the predicted price of this house? By touching on the line, right? When we touch on the line, I will be getting the predicted price of this particular house, which is this much, right? This is the predicted price of the house. And you see, the thing is that for this house, I know the actual price also. What was the actual price of the house? And what is the predicted price of this house? I'm getting both. That is why I took this line. I took this house specifically. Correct. So you now see, this is the actual price of the house. This is the actual price, and this is the predicted price of this house. So now the distance or the difference between the actual and predicted is going to be the error in prediction made by your line. Right. So this line has understood the pattern in the data, but how much error it made, how much mistake it made in understanding this first data point. Are you getting this? What is the error? Error means error in prediction made by the line. When the line has been created, error is nothing but the error in prediction made by the line for the data points. So what I'm doing, I'm taking such a house whose actual price I know, and I can get the predicted price using the line. So how much is the difference between the actual and the predicted? Got it? This is going to give us the error. Same thing I will do for all the other dots that you see. Right? You can see here all these points that you see here, E3, E2, E4, E5, all these errors that you see are nothing but the distance between the dot and the line. Correct. So if I take a house here, you see now for this house, this is the actual price. And for this house, this is the predicted price. This much is the difference between actual and predicted. This difference is what we call as a error in prediction, right? Error in prediction. Now this error in prediction is going to help us, like I said, in two things: to identify which line is making least errors overall, and if this is my best line, then how accurate its future predictions are going to be. Both the things you will get to understand. Okay, so the concept of error you understood. After making a line, we will check these errors. Error is nothing but the distance between line and the dot. Let's see some formulas. Okay, let's see some formulas. Here, we represent some terms. There is one symbol that we use, Y. Y is actual price. Y is an alphabet that we use to represent actual price. Y cap, right? Y cap is used or is used to represent predicted price for that given input. So Y is the actual price, and Y with a cap. You see, Y with a cap, we write it like this. That is the representation of predicted price. Now here I have written EI. EI is the error in prediction. I means what? I means E1, E2, E3. I means it will be replaced by a number which error it is representing. So in simple terms, I can say EY is equal to YI minus YI cap. So what is I here? So if you are writing E1, you will just say that it is y1 minus y1 cap. If you are writing E2, then it will be y2 minus y2 cap. Means the actual price of the second house minus the predicted price of the second house. Actual price of the first house minus the predicted price of the first house, that is the error. E1, E2, E3, and in simple terms you can represent it like that: EI is equal to yi minus yi cap. Now you see here, so error in prediction can be written as predicted minus actual or actual minus predicted, anything you can write. Both is okay. The way you want to represent, some people write predicted minus actual, some people write actual minus predicted. Both is okay. No problem with that. So what we have written here, three symbols: y cap, and ei. Error in prediction. So error is nothing but the difference between the predicted value and the actual value. Okay, now you see, to get the total error made by the line, we add all the errors. Right, what we need to do now, we have to calculate all the errors, which will be different numbers. After that, what you need to do, you need to add all the errors here. Right, we need to add all the errors. So what we were trying to do here, after having all these errors, we do not have to use them individually. We are going to add up all the errors to get total error made by the line. So if I do E1 plus E2 plus E3 plus E4 plus E5, all the errors, if I add it, I will get something called as total error made by the line. Okay. Now, once I do that, I'll get the total error, and I can use this form, this thing for many things, such as the line which has least total error, that is our best line. I can use this concept to find out which line has the least total error. So I can calculate the total error of multiple lines, and I can find out which line has the least total error. Correct. So now that will be our best one. Now you see, there is one small problem in this. What is the problem in this particular calculation of E1 plus E2 plus E3 plus E4 plus E5? What is the problem? See, can I say that some error values will be negative and some error values will be positive? Right. Is it correct to say that some error values will be in negative and some will be in positive? Yes. Why? Because if suppose I take if I take this one, in this case, you see, right, if you talk about this one, in this case, the actual price is this and the predicted price is this. So if I'm taking the formula as predicted minus actual, according to that, what will happen? This E4 will be positive. If I'm taking predicted minus actual, if I would have taken actual minus predicted, then it would have been negative. So the way you take it, it is going to be either positive, negative, no problem. So this is going to be positive error according to this formula that I'm using, predicted minus actual. Because predicted is a higher value and actual is a lower value. You know, the value increases in this direction on y-axis. So that is why this is higher, this is lower. So higher minus lower will give you positive value. But on the other hand, if you look at this E3, in the case of E3, the actual is higher, but the predicted is lower. So this will be negative. E3 will be negative according to this formula. Right. So the problem is some errors will be positive and some will be negative. And if I use this total error formula as of now, what might happen? It might happen that the total error was supposed to come out to be like, let's say 2873. But what happens? Some of the error values cancel out each other and the total error came out to be 150. Okay, because some errors were positive, some were negative, and lot of them cancelled out each other. Some negative, some positive. Like if you have -9 plus 9. So this is negative, this is positive, they will cancel out and it will become 0. So because of this, they can cancel out each other in many of the situations, and you will not get the actual total error being made by the line. You'll get a smaller number. This was the actual error made by the line, and you are getting this much error because some error values cancelled out. So then would you be able to actually identify the correct error made by the line? No. Okay, if they cancel out, then they give you another error, which is not the correct one. So we want to get the actual error made by the line. Correct. So what we do for that? We have to just make some small adjustments into the formula. What adjustments? The adjustment I will make is, instead of just adding all of them directly, we will square them. Okay, we will square them. So I can say E1 square plus E2 square plus E3 square plus E4 square plus E5 square. We'll square them. Okay. So why square them? So squaring a number will make it positive if it was negative. For example, if I take minus 2, into that also, if I take minus 2 and if we do square of that, what it becomes? Plus 4. Okay, if you take a negative number and if you do the square of that, it becomes a positive value. So one thing I can do to make a negative as positive is to square them. But second option is also there. I can take something called as a modulus. This is a concept called as modulus. M-O-D-U-L-U-S, modulus. What does the modulus do? It takes any number and it gives its positive counterpart. It basically converts that into a positive number. So why am I squaring? Why not modulus? So the idea that was given by the people who have created this concept, because this concept has been created for you, you are going to use it as it is, the way it has been created. So why did they pick the squaring? Is they were saying that when we square a number, if it is a bigger number, then its square will also become a very big number. Okay. In the modulus, what happens? The number stays same, does not become smaller or larger. But in the squaring, if you take a number, its square becomes a bigger value. So the logic for picking the square is that they wanted to highlight the bigger errors a lot. Means, if suppose I have the data points like this, right? Suppose I have all the data points like this, and I have got this line. This is closest to the points, but suppose I have another line which is very far away from all the data points. You can see its distance is this much from all the points, which is very far away from all the data points. So what we want is, if the line is making this type of line, we want to highlight this distance a lot. Means I want to highlight that this line is making too much error. It is very far away from that. So then what the linear regression can do, it will make a big adjustment and it will make the second line far away from that, because it is making too much error. So the next line that the linear regression would make to get to the best location is that it will make a big adjustment according to that. The larger the error made by this line, the bigger will be the updation, or the bigger will be the adjustment into that line to make another line. Otherwise, if you just represent the modulus, the error will not look that big and the updation of the second line will be made like this much. So you would need a lot of time to get towards this point. Okay, see, if you're not understanding this, let me give another example. How does the linear regression actually work? Simple idea, you see. Your actual data points are here. You see, your actual data points are somewhere here. And you have to basically reach this location. You have to make a line here. But like I said, linear regression can directly not make this line because it has no idea about where the line is going to be best. It makes multiple lines, and through that it can reach this particular point. So you will be studying about a concept called as gradient descent. You will be studying about a concept called as gradient descent. What is the gradient descent? It is an optimization algorithm which is used with linear regression, right? Gradient descent will or is used with linear regression to optimize it. What is the optimization? Very simple concept. You see, very simple concept. So by default, the linear regression is designed in a way that it will be making very random lines like that anywhere, random lines anywhere. Then it will find out the total error made by all the lines, and it will compare the total error made by all the lines. Okay, one process is that this is how the main concept of linear regression has been designed, that make multiple lines randomly and then find out the total error made by them. And whichever line has the least total error, that is the best one. But you see, doing this waste a lot of time, because when you're randomly making the lines, you might end up making multiple lines, and then you will find out the best one after making many lines. Gradient descent is a optimization algorithm which is used with linear regression, and it says that no, we will not do that kind of random things to find our line. We will start somewhere. Okay, so let's say we start with a line here at x-axis exactly. Then what we will do, we will update this line in this direction, right? We will update this line in this direction slowly, and then we will come to a point where where we will come to this point. And you see, slowly what we have done, we have been able to reach to this point. It is an optimization algorithm. So according to both the approaches, or after seeing both the approaches, which approach do you think is better? Making random lines and then comparing to find out which one is the best, or this one, where I'm going in a very structured manner, I'm updating the line one by one, and moving in this direction, and at one point I find my best line. So which approach is best? This one, right? Where I'm using gradient descent approach to find my best line in an optimal manner. Correct? Optimal manner. Because here you see, you're not randomly making the lines, you're updating them one by one. And after that, at one point, you will come to such a location, which is the location of your best fit line. This is one. So this way, you will be able to find your line faster. Optimization means you are finding the optimal way, the best way to do something. Okay, optimize means to make something efficient. Correct. You see. So gradient descent is this. Gradient descent we will be studying, uh, which is nothing but it optimizes that. It is going to help us find out the best line in a structured manner, not randomly making the lines here and there. So you see the why I was discussing that, because the logic of taking these squares, what they have given is, when we square the errors, so if there is a line that you have made, suppose if you have made the line here, this is very far away from your best location, very far away. So its error will also be represented very high. When you square all the errors made by this first line, the errors will look very large because of squaring them. So what will happen? The updation will also be large. Means instead of making the updation from this line to this line, it will make a bigger updation. Then it will make a bigger updation, and it will quickly reach this point, which is your best line. Okay, when the errors are big, the updations that we will do to reach to that point will also be quick, will be also bigger, and you can reach to your best line quickly. Got it? So this is the general idea which is given, and that is the reason why squaring has been picked. Are you getting the point? Why we pick the squaring instead of taking the modulus value? Because if you square them, the errors look very large, and then we can say that it is making too many errors. Let's optimize it faster to get to that point where we have uh, least errors possible. Okay, so it is just to penalize the large errors as much as possible. So when you square them, you penalize the large errors very much, so that your linear regression does not make such a line which is having very large errors. Now, as we square all the errors, we call it the sum of squared errors. So it is going to give us the total error. We just give it another name to that, which is known as sum squared error or sum of squared errors. Because you are squaring the errors and then you are doing the sum of all of them. So it is known as sum of squared error, SSE. But overall, it is going to give you the total error made. Okay. So all of you now see, very simple concept. What I was explaining to you about the squaring of the errors, why we have done the squaring of the errors in the first place, because we want to find out the total error made by the line. Okay. And why do we want to find out the total error made by line? Right. You see, why we are focused on the total error in the first place is this. Suppose we have all these data points like that, and now we have something like this. You see, we have to reach this point. This is basically our point where we have the least total error. Okay, and least total error means what? Least total error basically means our line is learning the pattern most accurately with least errors. Error in learning or prediction, you can say. So we have to reach this one. But how do we find out this line is the best one? So like I said, you use the concept of errors, the total errors, to find out which line is best. For that, what you will do, I said, you will be making multiple lines like this, multiple lines you will make. And what will you do? You will calculate the total error of this line. You'll calculate the total error of this line. Say this line is the first one, this is second one, this is third one, this is fourth one, this is fifth one, this is sixth one. So what you're doing, you are calculating the total error made by the line, which is nothing but the total distance of a line from all the data points. And then what you do, you compare total error 1 versus total error 2 versus total error 3 versus total error 4. Right. I hope you're getting this point. This should be clear to all of you. Why we were focused on the error thing? Because error is that concept which will help us to identify which is the best line out of multiple. Because uh, the line which has made least total error will be our best line. Okay, because the line which has made least total error has learned the patterns present in the data most accurately with least errors. Correct. This is the concept of total error. But I said that the total error formula is this: E1 plus E2 plus E3 plus E4 plus E5 for 5 points. Then we changed it to E1 square plus E2 square plus E3 square plus E4 square plus E5 square. Why did we do that? To make the negatives to positive. Because in this case, I want to add up all the errors, but the problem is some error will be negative, some will be positive. So they might cancel out each other and the total error might become zero also. So can a line have total error zero? No. it will not be having total error 0 because it is going to be straight line like this. It will have some distance from the data points. It can't be 0. But because the data points cancel out each other, it might happen that the total error of a line is showing 0. That is wrong. It's a wrong representation of the error. So to avoid that cancellation, we use the squaring. Squaring will convert a negative into positive, and we can then add up all the points, all the errors we can add up. So we could have taken modulus also. That also makes a negative as positive. Why did we not take that? So squaring, one example I've given, one more example I want to give you so that you become totally clear with that. Suppose we talk about the actual linear regression working. So the main working of linear regression was like it makes random lines. Without gradient descent, I'm talking about, it used to make random lines. Suppose it made the first line here. Then what will happen when all the errors will be calculated from this line and they will be squared? Then what linear regression will see? Oh, we are making so much error and we are very far away from the data points. So what it will do, it will make the next line with a big updation. It will not update the second line little bit like that. It will make a bigger updation somewhat like this, because it has seen that I am away from the data points too much. The squaring of the errors magnifies the errors. Okay, if there is a error which is too large, it will magnify that. It will show it as a very big error that we have made. So according to that, what linear regression will understand, that we must be very much far away uh, from the data points. That is why our errors are coming so high. So the next line it will try to make will be far away from itself and more closer to the points. Okay, now it will again check the error. Now it is very close to the data point, so these squarings will not be very large. Okay, then your linear regression will understand, okay, now I must be very close to the dots. That is why the error is not that large. So it will make a small updation now. Because if you see, if it makes a large updation here, it will cross your lines. This is your best location, but if you make a very big updation from here, you might cross that. Okay, and you keep going away in this direction. So now it will see that now the errors are not that much, so I'll make a small updation. Now I am even close. The errors are reduced even further. I'll make one more line, small updation. I'll make one more updation. Now you see, slowly, as the errors became smaller, the updation also became smaller and smaller, and now you are able to reach to that place properly. So I hope you are understanding why we use the square, because magnifying the errors will help linear regression understand, okay, I'm very far away from the data points. I should make these kind of bigger updations if I'm very far away, and small updations if I'm not that much. Perfect. So squarings we have done. Now you see, when we do the squaring, there is another problem that comes into picture. Squaring was done to do something. Squaring was done to, yes, manually you never have to do any of these things. Remember, all of you, manually you do not have to do any of these things. Whatever I'm teaching you here, you will be doing all these things with 2 lines of code. Just 2. Not even 3, just 2. All these things. You never have to do any calculation by hand, none of these things by hand. You're just understanding what will happen in the background if you run those 2 lines of code. And we will be seeing all those practical tomorrow itself. You see, but there is one small problem when we do the squaring. If there is a large training data, then sum of squared errors will be a very large value and can't be saved in the memory. So we take the average of SSE. Okay, now we are making another updation into this. So how do we start with? We started with total error, which was E1 plus E2 plus E3 plus E4. plus E5. We start with this. Then we updated that to make it E1 square plus E2 square plus E3 square plus E4 square and E5 square. We updated that to get this equation updated version, which we called as sum squared error. In simple words, it is total error itself with just another name, sum of squared errors. Now we are saying we have to make another updation into this equation. Why? Because imagine you have 500,000 data points, or in Indian terms, you have 5 lakh data points, suppose. Now, if you have 5 lakh data points, then 5 lakh error values will also be there. One error value for each point. You will have 5 lakh error values. And then you are going to add up all the errors. Now, suppose if your line is very much far away from the data points, the errors will be very large. And then you are adding 5 lakh errors which are squared. So the number, the total error, the sum squared error of a line, in that case might become such a number like 4582173104315 something like this. Because you are taking these 5 lakh errors, squaring them, then adding them up. So the total error of a line might become such a, and in every programming language, there is a limit that how big a single number. It's a single number. So how big a single number can be to store them properly in the data, we have limit in every programming language. Correct. So suppose the limit is we can store 10 to the power 8. This much bigger number we can store. This number is even big. Okay. So this was the limit that a single number which is this much big, that much I can store. But if it is bigger than that, I can that. So the problem is here is a explosion of value. The total error of a line becomes so huge that you are not able to even store that. Now imagine that if you are not able to store the errors in memory, will you be able to compare the errors of multiple lines to find out which line has least error? Right? No, because when you store the data, then only you can compare that. If you can't store the errors, how will you compare that? You can't. So then, don't you think your process gets stuck? It will not move forward from the point onwards because no comparison. So how do you know which line is best? You will never be able to find out your line which is best. Correct. So your process will get stuck and it will stop here without even finding out the line. So to avoid that problem, the solution which is given is, let's do this. Let's take all the error which and just divide by the number of data points. Divide by n. N is the number of data point. So if I have 500,000 data points or 5 lakh data points, we will divide the total error. So we are going to do SSE, sum of squared error, divided by n, which is nothing but it is going to give us m, which is known as mean squared error. So we have done the mean of squared errors, average. So you must know this in descriptive statistics, you must have studied what is mean. Add all the values, divide by number of data points. Yes. So that is what we are doing. We are adding it all up and then dividing by the number of data points. That converts it to mean squared error. Okay. This we have done. So once we take this mean squared error, then we have this particular equation in front of us. Right. So now what we are saying? We are saying a simple. Yes. And this is the final form of our total error that we are going to use. Let me show it to you with a diagram what I mean. So I meant to say that we have this line, we have this line, we have this line, we have this line, and we were finding out their total errors like this. Suppose let's take 3 lines. TE1, TE2, and TE3. Suppose we have these three lines and we wanted to find out which is the best one. So earlier we were comparing total errors. Now I said we have a modified version of each of them, which is sum squared error. So instead of total error, we will calculate sum squared error of each line, which is nothing but squaring all the error terms. Now I'm saying let's just make one more updation, which makes it MSE. MSE of, sorry, MSE of 1, MSE of 2, and MSE of 3. So whichever line has the least total error, that line will have least SSE also, that same line will have least MSE also. Just we have changed the formula, concept is same, the things are same. So what happens is, in the normal linear regression concept, we use this MSE to decide which line is best. So line which has least MSE value is the best. But like I said few minutes ago, there is a concept called as gradient descent. Gradient descent is also going to be used by linear regression in some cases. Means we need to make it, it is not by default present in linear regression, but we can use gradient descent with linear regression. In that case, what happens? We modify this formula by one more time. And what we do MSE by 2. Okay, we modify the formula once again, and that makes a cost function. Okay, it is known as cost function. So what we do, one more change that we make is we divide MSE by 2. Why this 2? So this is done for gradient descent. There is a formula in gradient descent. When we will study that, we will see. So if I'm using gradient descent with machine learning, then we do MSE by 2. Correct. And that is the reason we have this 2. And when we do that, then it becomes another formula known as cost function. So when you go to interviews, they will ask generally, what is the cost function of linear regression? So you can say it is MSE by 2. Right? It is that. But now in this PDF, you will see that I have written some, right? I have written something like this, and something like this. What is those things? You need to understand these mathematical representations. So it is nothing but, I'll simplify that for you. You see, so when you were saying the total error, which is E1 plus E2 plus E3 plus E4 plus E5, then you squared them, right? So what you can do now, you can represent it like this also. E1, how will you get it? You will get it y1 minus y1 cap square. E1 square means what? E1 square is coming from y1 minus y1 cap square. Means my first actual output minus the first predicted output. When you subtract that and when you do the squaring of that, then that gives you E1 square. Then to get E2 square, what you do? The second actual output minus the predicted value for the second point, that is your E2 square. Then this is y3 minus y3 cap square. Like that, you will write for all the further points. Now, mathematically, this thing can be written in a shorthand version, short form version. So how do you write? So you say, overall what you are saying is y1 minus y1 cap, y2 minus y2 cap. This thing is changing. Somewhere it is 2, somewhere it is 1. So what we do, we replace it with I. We say yi minus yi cap. This I is changing, but everywhere this thing is overall same. And we do the square of it. And then the value of I is going from, we write it like this, I is equal to 1 to 5. Correct. In this case, since I have 5 error values, so I'm saying I value is going from 1 to 5. Correct. And then what is this symbol? This is known as summation. This is known as summation. So this symbol represents plus. All these plus that you do here, this symbol is representing that. So this bigger formula can be represented in the shorthand version like this. But you will say, why to complicate it? Why to have the shorthand version? Because if you see, if you have 10,000 data points, would you like to represent it like this, or would you like to represent it like this? You would definitely want to represent it like this, the second one, because this one I have to just change from 5 to 1000, and that's it. So here I'm saying that there are 1000 data points, and that is the formula for that. Just this much change. And I can represent 1000 of these summations with this. So that is why this shorthand version is given, so that I can show it for any number of these calculations which are being done. So this is what? This is your sum squared error. This is the mathematical representation of sum squared error. Very easy. But if you say MSE, MSE is what? Yes. MSE is nothing but you take this equation I is equal to 1 to 5 and you say yi minus yi cap square. And what you do in MSE, divide by n. That's it. Right? Divide by n. Overall, this is your SSE. So you take the entire thing, divide by n. That's it. And then the cost function, what I was saying, if you use the cost function, then you will be having this. I is equal to 1 to 5 yi minus yi cap, then square, and n. So this is your MSE. And just if you add 2 here, it becomes a cost function, MSE by 2. That's it. So this is the mathematical representation of that equation, this MSE, SSE cost function that we were talking about. Simple, right? It is nothing complicated. It is just that when you see it like this, it feels complicated, but I've broken it down for you that how is it coming up. Right? So this is also clear. And why we are talking about these? Because the line which has least MSE value, that is our best fit line. Correct. Now, so remember that this cost function is used with gradient descent when we use that, and that is why this 2 comes, because this 2 is for formula in gradient descent. But for us, you understand, this is what we need to understand for us as of now. This is the main formula for normal linear regression without gradient descent. So through that comparison, through the comparison of MSE values of multiple lines, you will find out your best line. And suppose this is that line, for example, which is having the least MSE value, right? This line is having the least MSE value out of all the other lines. And this line is going to be called as best fit regression line. Means this line has learned the patterns present in the data in the best possible way with least errors. So the line with least MSE is our best line, and we call it as a best fit regression line. And this is our ML model also. The final product which we wanted to achieve, this is our ML model. Why this is our final product? Because once I got this line, what I have to do now, I just have to keep input value, touch it here, get the predicted value. Okay, so once I got this line, I just have to keep using that to get the predicted values. That's it. So once I have to make this and then keep using that. So this is why we call it as our final product, which we wanted to. Now, what I have to do, like I said, I just have to take an input value. Let's say there is the number of rooms. So a house has this much rooms. What will be the price? So I touch it on this line. I touch it here. This is the predicted price of a house which has this much rooms. Let's say 3 rooms. I just need to keep using that. But there is one small problem here. Like I said, algorithm cannot see like us or will not draw like this to get the predicted value. Like I'm showing to you that you take this house which has this many rooms, touch it here, and this is your predicted value. This is how we get the predicted value. But you see, algorithm cannot use this diagram for prediction. It will convert this line into a mathematical equation to use that like this. Correct. So what we will do now, just one last thing we will do is we will have to convert this line into its equation form. So how will that equation look like? This line will be converted into this equation, y is equal to mx plus c. Right, this line will be converted into this type of equation, y is equal to mx plus c. So you see here, y is our price, x is the number of rooms, m and c we have to find out from the line. So you see what will happen, this will get converted into its final form. But let's see what is m and c. Because you see, y is the price we want to predict, x is the number of rooms. So x I know because I have a house which I want to, whose price I want to predict. So x I know how many rooms are there. I have to multiply x with something, add something to that, then I get the price. So what is that m and c, from where it will come? Let's see. So you take your line and just stretch it backwards like this. Wherever this line is intersecting the y-axis, this is your y-axis, this is your x-axis. Wherever this line is intersecting this y-axis, that is your c value, also known as intercept. Okay, so c value is nothing but this particular value where the line is intersecting the y-axis, and each of any line that you make will intersect the y-axis, will cross the y-axis at some point. Whatever is that point, that is your c value, known as intercept. And then what is your m value? So m value is, you make a straight dashed point like this. Okay, this is your parallel to x-axis, representing the x-axis, and you have to find out this particular angle, right? So this angle is what your m value is. So m value is calculated using tan theta, right? M value is calculated using tangent of theta. Theta is an angle. Let's say it is 45 degrees, for example. Let's say this theta is 45 degrees. So tan of 45 degree becomes 1. So my m value will become 1. Simple. So m value is called as the slope of the line, which is calculated by 2 lines of code, and each and everything that we have studied till now will be done for us by the algorithm, by that code. So this calculation also we do not have to do. We just have to do m is equal to tan theta, whatever this angle is, and then we have this. So what will happen? The c value is this number, c value is this number, and m value is this angle. So let's say this c value is, for example, say 2.13. For example, it will be some number on y-axis, and theta is what? It is 1. So what will happen? This equation will get converted to 1 into x plus 2.13. Okay, 1 into x plus 2.13. Now, so this is how the equation of line always looks like. Y is equal to mx plus c. is the equation of line always. It's a mathematical concept. So anytime you are making a line, it can be represented by this equation. Okay, remember that. And in this equation, what we need to find out? M and C. But why? Because suppose you have a house which has say 4 rooms, and you want to predict the price of that house. So if you have this equation, y is equal to mx plus c, so you put 4 into your x and it will become 4m plus c. Do you get the answer here? No. You can't you can't multiply 4 with the alphabet m. You won't get an answer. So we need to get the value of m and c. Then only we can multiply 4 with that number and add that number. But you see now, if I have a house which has 4 rooms, so what I will do, this 4 will go here into x and it will become y is equal to 1 into 4 plus 2.13. And what do you get as an answer? 6.13. And you can say 6.13 crore or million, whatever in whatever way you want to represent. So that becomes the price of the house. Right? That becomes the predicted price of the house which has 4 rooms. Okay, so this becomes the predicted price of the house which has 4 rooms, 6.13 crore. Got it? So what we are doing here, what I'm doing with this equation, it is nothing but if I have a house, you see, if I have a house with 4 rooms, I would have, by drawing, what I would have done, I would have touched on this line and I would have got this number. This number would have been your 6.13 crore. So the thing I would have done with this drawing, the same thing I'm doing with this equation. So basically you're touching the 4 onto this line, right? You're touching this 4 onto this line by putting into this equation and you get that number 6.13. So this also should be clear to all of you that why did we convert to this equation? Because the algorithm cannot draw the things like that. It will use this equation. In this equation, it will just put the values and it will get the predicted price. That's it. Okay, you see. C value, you see, it is just mentioned here. Correct, C value is mentioned here. So C is nothing but you have studied the visualization, right? Data visualization. You must have seen on y-axis you have some numbers, on x-axis you have some numbers. So like that, what I'm saying, if it is 0 here, if it is 1 here, if it is 2 here, so it will be a number, it will be some number. So from wherever your line is crossing the y-axis, whatever is that number, that is your C value. That's it. Nothing complicated, no calculation for that. It is straightforward that number which is present at that point from where my line is crossing the y-axis. That's it. And how do you get the m value? It is nothing but it is the angle at which your line is tilted from this. If the angle changes, the m value changes. Right? That is the thing. So, yes. Now remember that you have to find the line once because on a data, your best line will be only one. Okay, so you do not have to keep calculating it again and again. Lines equation, you are going to calculate it once. So once you calculated the value of m and c from your line, that is going to be fixed for that data. Now you just keep using that. So both m and c will become fixed once you find that. Correct. So you have to once find it out. Once on a particular data, only once you have to find out m and c value and then you just keep using that. It will not keep changing. Both m and c value will be once calculated and it will be there. Because you see, on a data, your line will not keep changing its angle like this. Right? It will not change its angle, otherwise it will not be your best line. Angle will be fixed and from the point it is crossing the y-axis, that will also be fixed once it is done. So your M and C value both will be fixed once it is done. Okay. And if I change the data, then the equation of now. So what is your C, the C value? So if your equation is M into number of rooms plus C, because X is the number of rooms. So what is the C value? Like I told you yesterday, this is your base price, right? Base price, where your rooms is what? X. So if I have X is equal to 0, or if I'm saying that there is 0 rooms in that flat for now. So then if this all becomes 0, then what is the minimum price you have to pay to purchase a house? So C value being 2.13, it means that in that flat, in that city, you have to spend 2.13 crore at least to purchase a house. Okay, if I do not take any other feature into consideration at all, this is the base price, the minimum price you have to pay. If other factors are all taken out. Right? This is your C value in simple words. This is the base 1 minute. Yes. So now you see, in this situation, in this equation, what I've done, I have taken only the number of rooms. In this equation, if you see here, I'm determining the price of the house by using number of rooms. But will we have only one feature determining the price of the house? Obviously not. You will have multiple features. So suppose we have x1, which is number of rooms. One last thing for today. Suppose we have x1, which is number of rooms, x2, which is number of floors, then x3, which is area of the house, and x4, which is age of the house, how old it is. Right? Will the equation stay same? Will it still be y is equal to mx plus c, or will it change? It will obviously change. So it will not change, it will basically expand. So what it will become? It will become y is equal to m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 plus c. Your equation of y is equal to mx plus c will change to this. Right, will change to this. So if you have 4 input columns, x1, x2, x3, x4, you see input columns we represent with x. Like when I was having this number of rooms, what I represented it with x. So if I have multiple inputs, so I will say x1, x2, x3, x4 in mathematical terms. And then with each x, I will multiply 1m. Now there is one interesting thing to show to you. Tell me one thing, would you have multiple lines for this equation? Because what is m? M is the angle at which that line is tilted from x-axis. M is the angle at which the line is tilted from x-axis. What do I mean by multiple m? Will I have multiple lines which are tilted from the x-axis? Will that be the case? What do you think? No, m value will all be different. All the m values will be different from each other, will have different values. So think about it. Do you think your m value is going to be because we have 4 m values, then because of that we need 4 lines? Okay, yes. So that is what I'm going to show you now, which will be very interesting for you to see. Let me show it to you. See, the concept of best fit line that we have been studying till now, you will always have one line. You cannot have multiple lines, then you will not have the concept of best fit line. Okay, the best line means one. Best cannot be 4 lines. It has to be 1. So now the question is, how are we going to get 4 different m values from one line? Because the m is the angle at which your line is tilted from this. So how is it going to give us 4 different m values? And remember, all these 4 m values will be different. Okay, all the 4 m values will be different. They will not be same. Okay, and why am I saying that only one line is there? Because you see, C is only one. It is not C1 plus C2 plus C3 plus C4. C is only one. So there must be a single line which is having 4 different angles. But how? You will understand that now. Just 2 minutes I'll take of yours. Let me show you how your data will look like when you are having multiple dimensions or multiple input columns. You see, what you're seeing in front of you is the figure of what kind of data you will have when you increase the number of columns. Earlier, we were just working with one input column, number of rooms or number of or area of the house. If you have more than 2 columns, your data will look like this. It will not be dots on the paper, but it will rather be this kind of data points spread in the air like this. So what we have here, this is a graph representing 3 columns. And what is it showing to you? This is your x1, this is your x2, and this is your y. Means say this is your number of rooms, this is your number of floors, and this is your y, which is the price. You see, as I have 3 columns, now my graph became 3 dimension. So it is not the sheet on which we have dots. It is like this kind of realistic 3D image where we have all the dots floating in the air. And now do you think you need a single line like that in this case also? Is it enough to have that thin single line in this case also? No. Okay, no. Now you see here. All of you see this. This will be interesting for you to see. Let me show that to you. Notice that. This is how your line will look like for multiple input columns. Okay, you see, you won't see this type of animation or visualization at many places. So I made this for you. Look at this. This is how your line will look like for multiple columns. Now, can this line have multiple angles? This is not a line. This is known as a plane. Okay, this is known as a plane. So can this have multiple angles? Can this have multiple angles, this single plane? Yes, because whatever is the angle from this will become your M1. Whatever is the angle from this side, this will be M2. Right? And just for example purpose, just for visualization, what is the angle from this? This will become M3. What is the angle from this side? This will become your M4. So can a single plane have multiple angles? Yes. Yes, easily. So in this case, what we have done, we have updated our basic line to this kind of plane. So plane is nothing but imagine that you have a lot of dots floating in the air around you, and you see this plane is nothing but a sheet of paper you have kept in the air. Some points are above that, some points are below that. Okay, so this is known as a plane that will be created when you have more than 2 columns. What is C value? So C value is nothing but at whatever point it is intersecting your y-axis. So it will intersect at only one point, that will be your C value. So C will be always 1, but angles will be perfect. Right. So with this, we have understood the concept of linear regression from start.
Just a quick info, guys. Intellipaat offers an advanced certification in machine learning and AI in collaboration with Microsoft. Through this course, you can learn all the important concepts of Python, machine learning, deep learning, NLP, computer vision, and much more. The course features live classes with IIT faculty and industry experts, campus immersion at iHub IIT Roorkee, and includes certification from both Intellipaat, Microsoft, And I have Divya Sampal, IIT Roorkee. With this course, we have already helped thousands of professionals successfully transition into careers in AI, ML, and data science. You can check out the testimonials on our Achievers channel. The link is given in the description below. With the 24/7 support, placement assistance, and EMI payment options, this course can definitely set your career on the right track in the field of machine learning and AI. So visit our course page link given in the below description and take the first step towards your career growth in ML and AI.
Okay, so we discussed properly the mathematical version of linear regression, and we tried to understand how does the linear regression algorithm makes a machine learning model. So what was the machine learning model for us? It was nothing but the best fit line that we create. And in mathematical terms, if you say this equation that we have got here, which came from the line itself, the best fit line itself. So this is our ML model. So this equation is what we are trying to achieve. And once we got this type of equation, then we just keep giving it the inputs in X, and we will keep getting the output, which is the Y, which is the price of the house. And I said, if you have multiple input columns, so you will have multiple X values, and your equation will change into something like that, where you have to find M1, M2, M3, M4, and C, all of that. And what will be X1, X2, X3, X4? So if you take a if you take a house which has say 4 rooms, 2 floors, 1800 square feet area, and age is 2 years. So you have to fill this 4 here. You have to put this 2 here. You have to put this 1800 here, and you have to put this 2 here. Simple, right? You just need to find out what is the value of M1, M2, M3, M4, and C from the best fit line, which was like a plane. And once we got that, we just need to multiply with these 4 values and we will get the answer. It is as simple as that. And who will find these M1, M2 values for us? Are we manually going to find it out? No, we will be running the code. The algorithm is going to find out all these M1, M2 values for us. So we have to relax. We do not have to put much effort into that. The algorithm will find out all these values for us. We just need to know what it is finding out, how it is finding out that thing. We understood that uh, there is a process where linear regression makes multiple lines, compares multiple lines, and whichever line has least error, it used to pick that and say that this is our best fit line. Okay, so that it is doing. And once it has decided that it is the best fit line, so it will convert into this type of equation where it will give us M1, M2, M3, M4, and C. We will get this from the algorithm. We have to just provide it the data. And now we are just going to start that itself, and you will understand how simple and easy it is. You will understand the practical part of it. But just before I start it, I want to give you a 5-minute understanding of assumptions of linear regression. See, every algorithm has some assumptions of itself. Like when we were talking about hypothesis testing, each test, Z test, T test, chi-square test, they had their own assumptions. Means when they should be used and when they should not be used. Same way is the case with these algorithms also. They have their own advantages and disadvantages. So they have some assumptions. If those assumptions meet, then only you can use this algorithm. Otherwise, use another algorithm. So what is the assumptions of linear regression algorithm? See, 4 basic assumptions are there which you need to know. Okay. Now, the first assumption, these are very simple ones. 4 assumptions, I'll tell you. Then we will do these with practical also as we move forward and you will understand. The first assumption is that the relationship between input and output column should be linear. It should not be that this type of non-linear relationship is present. Linear means if you can make a straight line properly and your data points is also going in that direction, that is your linear relationship. But this is not linear because here this type of line is required to understand the pattern. This is not linear. Correct. So first assumption is very basic. Linear regression algorithm works on a data where input and output columns are linearly related. Okay, there is a linear relationship between that. If there is non-linear relationship, then you won't use linear regression. There are other better options available for those. Right. So this is your first assumption. Second assumption is when you take all the error values, okay, when you take all the error values and you add them up without squaring them, just take all the error values and add them up as it is. And if they give you zero or a number very close to zero, then you can use the linear regression on that data. Linear regression is suitable for that data. Okay, so what I've written, if you take up all the error values, here we are not trying to find out the total error, we are finding out something else, that if we add up all the errors, some error values will be negative, some will be positive. So if they cancel out each other and the total error becomes zero after adding that, or a number very close to zero, then it means that you can apply linear regression on the data. Another way this assumption can be checked is if you take all the error values and if you plot them, right? If you take all the error values and you plot them, then it should be giving you a normal distribution curve. Okay, the another way this same assumption can be written is if you take all the error values, if you have 10,000 data points, you will get 10,000 error values. So if you take all those 10,000 error values, which are all numbers, numerical values, and if you plot them using plt.hist or sns.kd plot or sns.displot, right? You plot them, and if you get a normal distribution curve using the error values, then you can use the linear regression on that. Okay, so linear regression will be suitable for that particular data. We will see all this with the practical also. So this is our second assumption. This should meet. Third assumption is there is something called as homoscedasticity and heteroscedasticity. Okay. This is a little complicated name. Homoscedasticity and heteroscedasticity. So this is the third assumption, that your data should be like this, not like this. Okay, so what is heteroscedasticity, homoscedasticity? Means in your linear regression, you should have this, not this. Okay, so what is this? You see, you take all your error values, and if you try to see the spread of the error values, how they are spread, right? So they should be spread equally on both sides of the line. Means my data should be my error values, which I am getting on a particular data, they should be, you see, equally spread across the line. Okay, they should be having equal variance, equal spread everywhere on this graph. It should not happen that somewhere the error values are too close to each other, but as I'm moving on another side, they are going farther away. Means there should not be any sort of patterns like this in the error values when we see them like this. Okay, they should be equally spread from our line. They should have equal variance on both the sides of the line. Then we can use the linear regression on this. Otherwise, if this situation is happening, we will prefer other algorithms, not linear regression. So this should happen, this should not happen when we plot the error values. Okay, we should see pattern like this, not like this. So this is homoscedasticity. Homoscedasticity means equal variance of the error values. Heteroscedasticity means non-equal variance of the error values. Variance means spread of the data. Correct. So any sort of pattern is visible to you, then you won't use the linear regression on that. This is the third one, very simple. And the fourth one is the most important one, which you will be, right, which you will be seeing and using a lot, known as multicollinearity. So multicollinearity should not be present in the data. Okay, multicollinearity should not be present in the data. What do you mean by multicollinearity? When input columns are highly correlated to each other, that is called as multicollinearity. This is one of a very frequent issue that your data will be suffering from, and you need to handle this. What is multicollinearity? What is the problem with this? You see, suppose you have all these features: rooms, area, floors, length of the house, breadth of the house, or you can say width of the house. The error values should be equally spread on both the sides, equal spread. Now, so here we have all the input columns, and then we have the output column here. Say I have the house price prediction data, and these are all the input features. This is the output column. Now, there are some names that you need to know about the input and output columns. So all the input columns that you see here, they are known as either features or input or independent variables, right? So all the columns are known as input columns are known as features or independent variables. In simple words, you can call them input columns, but in technical terms, we call them features of the data or independent variables of the data, right? So we have 5 independent variables. And you see, there is mentioned properly, they are independent variables, means the input columns are not supposed to be related to each other in any way, right? All these 5 input columns that I have, they should be as unique from each other as possible. They should be not at all related from each other in any way. Okay. The more unique they are, the better it is for us. But the thing is, there should be high correlation between input and output. Okay, when I check the correlation between this to this, there should be very high correlation. This to this, very high correlation. This to this, very high correlation. Okay, so between input to output, we should always have very high correlation. It means if suppose this is very highly correlated to this, it means that we will be able to predict the price very well using this feature. So there should be high correlation between input to output. But at the same time, there should be very minimal correlation between 2 input columns or 3 input columns. Means input columns should be minimally correlated to each other. Either zero correlation, or if it is there, then there should be very minimal correlation should be present. But why? You see, correlation means what? Correlation means the relationship between those two variables. And if the correlation is high, then what is happening in that? When one thing moves in one direction, other things also moves in the same direction. What is correlation? Correlation is this. If you have one column here and you have second column, so they are moving in the same direction. When one of the value increases, second one also increases with that. They are highly, they are having a lot of relationship between them. You see, correct? So remember this, that you should have, right? You should have very high correlation between input and output, but very, very low correlation between input to input, okay, or between input columns. That is the thing, keep in mind. So what is the problem with that? You see, right? The problem with this is, if you suppose have the area column in this, and then you also have length and width column in this. So can we say that it is having a correlation between these columns? Mari, linear, we are talking about input and output. Linear is not about input to input. That is what I'm explaining. When you talk about linear, we are saying input and output should have a linear relationship between them, not input and input. That's what I'm explaining. Okay. Input and input should not have any relationship, not linear, not anything. When we are talking about linear relationship, we are talking about input and output. You see, so all of you see, we have area column and then length and width. So what is going to happen in that case? So if you know the formula of that, area is equal to length into width, right? Area is equal to length into width. So the thing is, if you have a value here and if you have a value here, if you multiply these two values, you are going to get the same value which is given here. Okay, you are going to get exactly same value which you are getting here. So see, what is the problem with correlation? If correlation is there, what is the problem with that? The problem is that the columns which are correlated, they are giving same information in both of these cases. Same information. You are not getting any new information by using these. So if this column is also giving one information and these columns are also giving the exact same information which that column is giving, would you want to keep that? Does it make sense to keep these two columns in the data if they are giving the same information? No. Why would you want to have exact same information two times? No need, or it does not make sense. So we take all the input columns which are unique because I want all the unique features about the houses, and through that we are going to, right, through that we are going to identify whether there is a correlation between input to output or not. So we want as many unique features in our data. When we are talking about input columns, we want a lot of input columns, but they should be unique, as much unique as possible. Means if correlation is there between input columns, it should be as low as possible. Being high correlation means that they are telling the same thing. They are not giving us any new information. So there is no point in keeping that. No point at all. So it is a redundant feature for you. Okay, giving you the same information. And see, another problem that will happen, this is one problem, that they will just be unnecessarily present in your data and they will just waste your time in the training process, because more columns, more time will be taken for the training process. Okay, this is one issue. But is there any other issue with multicollinearity? Yes. Suppose the area column has this much importance overall, right? Suppose area column has this much of importance. We were talking about M1, M2. So this is my X2, column 2, and it will be multiplied with M2 value. So suppose its M2 value is 1.2. Now what will happen? There are these two columns also which are present. So what will happen in that case? The weightage will be divided, right? The weightage value will be divided across these three columns. So what will happen? So area should have 1.2 weightage, but it will become 0.6, and the remaining 0.6 will be divided between these two, 0.3, 0.3. Correct. So because these three columns are giving the similar information, the weightage will be divided across multiple columns. So now, is this the correct weightage of area or is this the correct weightage of area? Means your prediction will be same. If you are having all these columns, there will be no effect on your prediction, or there will be no effect on your performance of the model. Just that the weightage value that you are going to get, that will give you wrong indication about the actual weightage of the area. Means actual weightage is supposed to be 1.2, but it is getting divided between 0.6 and 0.3 and 0.3. So its weightage is getting reduced. So we will think that area is not that important feature for us because it has a less weightage. Are you getting this? I'm just giving an idea. It may be 0.4, 0.4 also. But you see, why am I writing like 0.6, 0.3, 0.3? Because you see, this is one, and these two together are going to give you the area. So area will get 0.6 and these both will get 0.6. Now out of 0.6, 0.3, 0.3 will be divided. That way I've written. Okay, just as an idea. Because both together will give you area of the house. Correct? So now, are you all understanding what is the main issue with multicollinearity? Your weightage value will get divided across multiple columns. So if it was supposed to have a weightage of 1.2, Now, if these two are also present, if you are not removing them, so what will happen? Your weightage value will get divided across these. 0.6 will become the weightage of the area and 0.6 will become the weightage of these two. So out of that, 0.3 will be of this, 0.3 will be of this. So then what will happen? The actual weightage of area column is this much, a high weightage. Okay, but it is getting reduced and you will get wrong answer, wrong idea about the area of the house. You will think that area does not matter that much in determining the price of the house. You'll get wrong idea, but that is not the case. Area has actually more weightage in determining the price of the house. Okay, so this interpretation that you are going to make will become wrong, right? The interpretation of the weightage will become wrong. Your prediction will be correct. Your performance of the model will be okay, no problem with that. Just that this is going to modify the what importance of the features. Understood? That is what I'm saying. So it will have no problem on the predictions or anything. It will just cause this problem. It will modify the weightage of the features. You see, the weightage value will be found the way we have studied that whichever feature has more correlation uh, in with the price column, whichever feature was helping more in predicting the price, they have more weightage. Okay, how is weightage decided? The weightage is decided on the basis of how much area column is helping in predicting the output. Just this one column, if I just take the area column, how much I can predict the output column with this column alone. On that basis, weightage is decided. Okay, and then that will be found by the algorithm. When we run the code, when we run the algorithm will study all these things and will tell us what is the weightage. I'll show you with the code also all these things. But weightage is decided on this basis. How much area column alone is helping us in predicting the output. The more it is helping us, the more will be the weightage of that. Now, imagine you have 200 columns in the data. Will it be possible for you to find out which columns are correlated with each other and how much they are correlated with each other? Will it be possible for that? Think about, you have a large data, because in industry you will be working with large data, not like 5 column, 10 columns. You will be having 100 columns, 200 columns, 500 columns. So will it be possible for you, right? Will it be possible for you to find out how many columns are correlated to each other and how much they are correlated to each other? No. It won't be possible for you to manually check this thing if you have large number of columns. Manually not possible. So that is why we have a tool which is going to help us identify which columns are correlated and how much correlated they are. The name of that tool is VIF. Again, we will see all this with the code as we move forward. We will see all of that one by one. So VIF is Variance Inflation Factor. So this is a tool. We will write 4 or 5 lines of code for that. And this is going to help us in identifying and removing the multicollinearity. This tool will be applied on the data, on our data. It will go through all the input columns and it will check which column has how much multicollinearity. And then it will give a score to that, right? It will give score to each column, column 1, column 2, column 3. It will give a score to them. The score will be any number like 4, 5, 3, 8, 10, 15, something like that. And in that case, if a column has a VIF score of more than 5, then that column is having high multicollinearity. Okay, so what VIF will do? VIF will give score to all the columns, right? VIF is going to give score to all the columns. And if the VIF score of any column is more than 5, it means that that column has to be removed because it is having very high multicollinearity. So through this tool, it will become very simple for you. You just have to apply this on the data. It will give a score to each of the columns. And if any column has a VIF score of more than 5, it means that column has to be removed. That column is having very high multicollinearity. Okay. So I hope that is clear. Okay. And what does this greater than 5 means? Why am I writing greater than 5? You see, if suppose column 1 has got a VIF score of 6, suppose we got the column 1 has a VIF score of 6. What does it mean? So VIF score of 5 means that the column 1 is 80% correlated with other columns. Okay. So if C1 has a VIF of 5 means C1 is 80% correlated with other columns. Means C1 is giving 80% same information which is being given by other columns. So if you have VIF of more than 5, then you have more than 80% correlation between C1 and other columns. So C1 is giving lot of similar information which I am going to get with other columns also. So we are going to drop the C1. Okay. So VIF score of more than 5 simply means that that column is having 80% correlation with other columns. More than 80%. Right. So that is why we remove them. This is what the VIF score of 5 more than 5 means. Clear? Don't worry too much about them. We will be using them multiple times through other algorithms also. We will have. Okay. So out of means VIF will tell which column you have to drop. VIF will tell you which column has to be dropped. Whichever column has score more than 5, it is telling you that has to be dropped. Okay. It is telling you that this one has to be dropped. If another column has to be dropped, it will give it a score of more than 5. Okay. That is the thing. Perfect. So now assumptions are clear. 4 assumptions are there. And if those 4 assumptions are being met, then you use linear regression. Otherwise, you do not use linear regression. You are going to use other algorithms which are there. We will be studying. See, if 3, 4 columns are multicollinear, then it will tell you, VIF score will tell you which one have to be removed. Okay. So it can tell you 3 columns also be to drop, 4 columns also to drop. It will be told by the score itself. It is not that only one will be correlated. There are 3 columns that can be correlated. There can be 5 columns that can be correlated. So when 5 columns are correlated, you might have to drop one of them, 2 of them, 3 of them, depending upon your VIF score. Okay, so that is the thing. Multiple columns can be correlated to each other. Right. I'll give you the code of how do you check VIF. There is a fixed code. You just have to run that on a data and you are going to get the VIF score in simple. So in this example, out of area, length and width, which one will be dropped? Right. Out of this, which one will be dropped? So what linear regression will see? Which one has less correlation with the output column? Correct. You see that in deciding which one has to be dropped, which one should be dropped. So what it will see that which column out of these 3 have less correlation with the output column. So suppose we found out that area has more correlation with the output column and length and width have less correlation with the output column, so they will be dropped. And if you found out that area has less correlation with the output column and length and width has more correlation with the output column, so area will be dropped. Okay, because more correlation with the output means more important. So the column which is more important will be kept and the other which are not that much important will be removed. Okay, yes. So now we are going to start the practical and we will do a lot of things in that. And whatever we have discussed with theory, you will see that how easily we can get the similar information with this. And also we will see the testing, that once we have trained the model, how do we know how good that is? So testing thing also we will be seeing. So it is going to be very fun. First step is where we are going to import the required packages. The step number 1 when we are going to run the machine learning process is we import the required packages first. Okay. And for now, I will be moving little fast. I'll be writing because I have to show you a lot of things. So that is why I'm saying first understand the things and then later you can practice in the hands-on sessions which you'll have. First, just leave everything, focus on it. You will have a proper understanding of all the steps which I'm going to show you. So step number one, import the required packages. So it is a very good practice to import everything at the top so that you can keep track of what packages you are using. So tomorrow, if you have to update any package or replace any package, you can find out easily that which packages you have used. Because when you are going to make projects in the company, it will be quite huge. It will have thousands of lines of code. So if you kept all the packages at the top, you will be able to understand easily which packages I am using. And if I want to update them, replace them, then you can do that easily at one place. So what are the packages we are going to import here? First, we will have our data reading and manipulation packages, which are import numpy as np, then we have import pandas as pt. Using these two packages, we do reading and manipulation of the data. Do reading and manipulation of the data. Then after that, we will take our data visualization packages. I'll write these comments as much as possible for you so that when you go through the code, you'll be able to easily understand. And you should also develop a habit of writing like this because it becomes a very standard procedure of writing the code when you go and work in the company. A lot of people read your code. So the more you explain your code with these comments, the better it looks. Okay. So these are two packages we use for visualization purpose if I want to make any charts and graph for that. So the assumptions I was talking about, we have to make charts and graphs for those assumptions. So we will need in this case. Now comes the third part where we are going to have machine learning related packages. Okay. So in the machine learning related packages, we are going to write few things. First, from sklearn dot linear model, I'll explain all these things. Import linear regression. From sklearn dot model selection, import trend test split. And from sklearn dot metrics, import mean squared error and R2 score. Okay, so these few lines of code I've written. The first four things you know, the last three lines of code which I've written, you need to understand that. Okay, so for machine learning, we use a package which is called as scikit-learn. Okay, which is in short form used as sklearn. The proper name is scikit-learn. This is the package we are going to use in machine learning. When you go to deep learning, there you will be using packages like TensorFlow, Keras, PyTorch. So there is another module which is known as deep learning. Deep learning is advanced machine learning, more advanced than what we are going to study in this module. Okay, advanced machine learning concepts. So that is known as deep learning. In that, you will be using one of these three packages, either TensorFlow or Keras or PyTorch. This is the most famous one. This is the second most famous. This is the third most famous in today's time. Okay. So you will be using these packages there. But for machine learning, we are going to use scikit-learn. I'm telling you this because you might hear about these packages. So you might think, where are we going to use them? Okay. So this is the best one for deep learning. This is latest and lot of developments are happening and it is easy to learn. The most difficult to learn is TensorFlow, very difficult. Keras and PyTorch are very easy. PyTorch is getting famous nowadays because a lot of development is happening in that. You'll see all of that you'll be using in depth. Okay, so scikit-learn is the package for us, which is used as sklearn. So I'm importing few things. What does these things mean? Okay, whatever I've written here, what do they mean? Understand this. So there is something called as a library or a package. Okay, there is something called as library or a package. So sklearn is our library. So it's a bigger thing. Inside a library, there are some smaller components like this. Inside a library, there are multiple smaller things like these. What are these called? These are called as modules. Okay. So there is something called as modules. They are present inside a package or inside a library. Now, what is a module? Module is nothing but they are all Python files with .py extension. They are all Python files in which some code is written. So a library can have multiple number of modules, 5, 10, 15, 20, any number of modules can be present in a package. Scikit-learn has lot of modules inside this, and we are going to use them one by one. Today I'm using 3 modules. One is known as linear model, model selection, metrics. Okay, so this is our linear model, LM. I will just write LM for linear model, model selection MS, and here we have metrics.py. So what do you mean by writing this from sklearn.linear model? So you are saying that in the sklearn package, you have a Python file which is linear model.py. Okay, so this is present in this. This is present in this. This is present in this. So think of a library like a folder, and inside that folder you have multiple Python files. Correct? And what is written in these Python files? What is written in these Python files? What is present in these Python files? In all these Python files, there are pre-written functions and classes. Okay, remember that in these Python files, there are pre-written functions and classes. Pre-written means they are defined for you, they are written for you. You just need to use them. So you see, how do you know those functions and classes? Whichever you're going to use, you will be taught about them. So first thing you see from sklearn.linear model, that I'm going to sklearn package and I'm going to linear model Python file. In that, I have linear regression which I'm importing from that. Where am I importing? So this is another file I have. This is my code file. This is my code file, which is this notebook, this collab notebook that we are working on. This is our code file on which we are going to run linear regression. So what I'm going to do, I have a class here, class linear regression. Okay, so there is a class which is written for us with a code. I am importing this class into my code file. So whatever code is written here, that will be imported from here into your code file. Then you see in model selection, if I go to another module, that is model selection.py, from that we are importing train test split. This is a function, def of train test split. It's a function, and I'm importing this function from here into my file. Then I'm going to sklearn.metrics. From this, I'm importing two things, mean squared error, comma, R2 score. So there are two functions. One is mean squared error. It has some code, and another function is R2 score. Two functions are there which I'm importing. This also, right? So I hope you are understanding very well that what we are doing when we write these 3 lines of code. Okay, so you won't get this explanation in such a simple way, but in very much detail, you are getting to see what you do when you write these 3 lines of code. How do you make sense of them? Okay, right. So all these modules are there, and they have lot of functions inside of them. Do not worry about knowing all the functions as of now, because you are going to do lot of practical. You will be seeing all of them, and you will know about each one of the functions. You will get to know, right? So how do you identify which one is a class and which one is a function? Because I've written linear regression as a class, train test split as a function, MSE as a function, R2 score as a function. So how do you identify which one is a function, which one is a class? So if there is capital letter in the name, right? If you have capital letters in the name, even one capital letter in the name, then that is a class. Simple. Capital letter, class. And if you do not have any capital letter and there are underscores being used on that, that is a function. So simple thing, capital letter, class, no capital letter, function. As simple as that. Why do we need to know this? Because if it is a class, we will be making objects of it. And if it is a function, we will be calling them. Okay, all of that we will see. So this is the first important thing that you need to know. Okay, simple. This is how you identify that. Difference between class and function, you will have to study the object oriented. You will have to study Python back for that. Okay. Class is a bigger concept compared to function. Functions are there inside classes. In simple words, if I have to tell you, classes are bigger components compared to functions. They are bigger entities. So after importing all the required packages, we start by reading and exploring the data. Right. The next thing that we do is we start by reading and exploring the data. Right. Okay. If you have any capital letter, that will be a class. So the general way we write the names of the classes, if it has multiple words, we always keep the first letter capital. In the naming convention of the classes, the first letter we always keep as capital. This is the rule, means this is a naming convention. This is a style that we always follow. So it will not happen that linear is written in all small and regression R is capital. No. If it is a class, then the first character of each word will be capital. If you have 10 words together, then each word's first character will be capital. That will be the case. Okay. So second step is we are going to read and explore the data. What are we going to do in reading and exploring the data? I'll mention the things related to that for you, that what can you expect in this. So first here we are going to import the data set. Our first task will be import the data set. Second will be to check the shape, info, data type of the columns. Third thing, we will be checking for missing values and handle them. Then fourth, check for duplicates and handle them. Fifth, do the encoding of the categorical columns. Then sixth, check for outliers and deal with them. And seventh, any necessary visualizations. These are the 7 things we are going to do overall. And if we have to do something further, we will be talking about them. We will be adding those things. But for now, in simple words, I have written all these things for you so that you can keep track of what are the things you need to do. Right. Yes, this process is known as EDA, exploratory data analysis. So when you do all these things, you are basically performing EDA. Okay. So EDA is about studying the data, manipulating the data, and making the visualizations. When you do all these things, you are doing EDA, exploratory data analysis. You are exploring the data and you are making it ready for further use cases. Okay. Now, so first step I've written is import the data set. So you see here, we have to write, we are going to use a data set that I have uploaded into this drive. In this drive link, there is a CSV file called as boston.csv. This one we are going to use, boston.csv. Okay. So you can download them and then you can use them. So in Google Colab, I'll tell you how you have to use them. So you can just say data is equal to pd.readcsv and then boston.csv. Now in pandas, you must have seen how do you read the data in your Jupyter notebook. You have to do it exactly like that. But in Google Colab, if you want to use it, you will see that there is this kind of folder icon here. You click on this folder icon here and you will see like this sample data, this thing written. You just take and drop it. Then just take your data, drop it here into this folder thing, and then you can use it from here. Right? In Google Colab, you can do it like this, simple and easy method for now. Right. And then once I have uploaded that into Google Colab, I can just use it without any problem directly. Now, so as we have imported the data, the very first thing, EDA is exploratory data analysis. Whatever you do to explore the data to find out what information is hidden, that is known as exploratory data analysis. So if you are running any pandas function to do the grouping of the data, filtering of the data, okay, or anything that you're writing using NumPy and pandas to find some information from the data, that is EDA. And also when you do the visualizations along with that, that is EDA. So there are no such like fixed steps that this is what you have to do, this is what you don't have to do. It is all about what you are doing to explore the data, to find out the necessary information present in the data. Accordingly, you can do the further analysis. Okay. So EDA consists of writing the NumPy pandas code to find out some information and also making the visualizations. Right. So after reading the data, there are few things that we do. The first basic thing that we do is we check how does it look like with data.head. So this is going to print the top 5 rows of the data for a quick inspection. So quickly you can see how does the data look like. For a quick inspection, you can just do data.head to see how many columns are visible to you, what type of values do you see in all the columns. For that purpose, you have to check data.head first. Now, you see that in a data that you're going to work with, you will be having multiple columns. Okay. So from wherever you get the data, you will be also having the explanation about these columns from that place. For now, for your use cases, for your projects, for your practicals, you are going to download the data from this website called as kaggle.com. Okay. Go on to this platform, make an account. Very simple, just 1 minute. You can directly connect it to Gmail. On this website, you will find out the data set for your use cases, and variety of data set is there. You can just download them, you can use them. This is the biggest platform for data science and machine learning, where a lot of competitions also happen, and you can just search for this and you can get them. Okay, kaggle.com. We will be seeing those process. How do we search? How do we download all those things? We'll see. But for now, I'm just giving you the starting idea that kaggle.com is the website from which we will be getting our data sets. Now, whenever we download the data set from there, on those pages, we will have the explanation of the columns also, that what all these columns mean for now. But when you go and work in the company, so the people who will provide the data to you, they will also give you a data document. Okay, in a company, the people who will provide the data to you, you are a data scientist, you will be given the data from someone, generally a data engineer. Okay, so there is a person called as data engineer. They are responsible for collecting the data, creating the data. So they will provide the data to you, to data scientist, to data analyst. And along with the data, they will also give you a data document. In this data document, you will have all the explanations about the columns, what they are, what they represent, and why does it matter. Okay, so I have just pasted here the explanation of all the columns that we are using in this case, so that you can get a sense of how those explanations will look like. So you have the first column, CRIM. So CRIM means per capita crime rate by town. Then you have ZN, Indus, CAS, NOx, RM. So all these capital letters, capital names that we have written, these are column names that you see here. And in the small case, these are the explanation of all the columns. They are there. Okay. Now don't need to go into too much of what specifically those things are. You are not a domain expert for now, so you won't understand that the data for now. But just to get an idea that this is how your explanations will be for each and every column. And when you're working in that company, you will know that what all these things means, all these technical terms, domain related terms, and then you can identify which column seems to be important for you and which column seems to be unnecessary, and you can delete them if you want to. Okay, so this is the thing. After getting the data, you will be reading your document to find out this information. Now, moving to the further thing, what are the things that we do here? So next thing you will write is data.shape. This will print the total number of rows and columns present in the data. So in our data, we have 506 rows and 14 columns. See, now this data is about house price predictions, where the MEDV is our output column and the remaining all of them are input columns. So out of 14 columns, first 13 columns are input columns and the last one is our output column in this case. How do I know? So from wherever you download the data, you will know these things. And when you work in the company, you will also be given this information that you are going to use. Okay. So last column is output for now. All the others are input columns in this case. Next, we will write data.dtypes. Dtypes is going to print the data type of values in each column. Okay, so you have to check the data types of the values in each column. Why do you need to check the data type of each column? Right. Why do you need to check the data type of each column? To first find out whether each column has the correct data type or not. Second thing is we need to find out whether there is any object column or not in this case. Object column means that column has text values. Now, why does that matter? Because machine learning algorithms, you will see, they do not work with the text values directly or object data type directly. We will have to convert that from object to numbers. Okay, so we need to check by checking the data types, we need to check that any object column is present or not. If there is any object column present, we will need to do the encoding of that. Encoding means converting from text to number. We'll need to do that. See, D types is a pandas function only. It is a pandas related variable only. It is not anything else. Okay. Info is a function which you can use, but instead of info, it is better to use the D types because info, when you check, it is very complicated. It feels like very messed up. So much information is there together. So instead of that, I like to check the D types, which gives us the information about all the data types. And apart from that, I check data.isNull.sum, which gives us the information about the missing values in a clear manner. Correct. So info, if you check, it gives you two information, this information and this information. So I like to check it individually because it is more easy, more clean to understand. Correct. So info is a pandas related thing. This is also a pandas related thing. We are not using something else. Right. So now this is going to print the total number of missing values in each column. This is going to print the total number of missing values present in each column so that we can get an idea how much missing values are there and how we have to deal with them. All right. So we have this, we have the data, we have checked the shape, we have checked the D types, we have checked the missing values, these basic things. Now after that, I'm supposed to check the outliers value, duplicates, but I will keep that for later sometime. For now, I want to dive deep into the machine learning part. Okay, so remaining things I'm keeping on hold for now. The duplicates, the outliers, detection and everything. We are skipping that for now, but we will add that. For now, let's go and focus on the machine learning process. Okay, this is what you are interested in for now. Let's do that. So in this case, when we're talking about machine learning process, what are the things we do in that? I'll just mention for that also. Create X and Y variables for, and you can say store input columns in X and output column in Y. Then split the data into training and testing sets. Third, standardize or scale the data. Fourth, apply the ML algorithm on the data. And fifth, check the performance of the model. And then sixth, necessary improvements in the model to increase its performance, or you can say accuracy. These are the 6 things you will be doing. Starting with the very first task is we have to create X and Y variable. The first thing is creating X and Y variables. So we need to make X and Y. See, generally we keep X as capital and Y as small. It is a general practice which is followed by the data scientist. You can keep both capital, both small, one capital, one small. So generally you will see people write X as capital and Y as small. Okay, it's not a rule. It is just a general practice which people follow. In X variable, we have to store all the input columns. To store all the input columns, we write data dot drop columns is equal to MEDV. MEDV is our output column. So what I'm doing in this line of code, you see, in this line of code, I'm saying drop the MEDV column from the data frame and the remaining all the other columns which are there, store that into X variable. But you see, we are not permanently dropping the MEDV column. We are temporarily dropping that. Temporary means only in this line of code, you are dropping the MEDV column and selecting all the other columns and keeping that into X variable. Now, as you go to the next line of code, MEDV column will be again available for you, and you can just select the MEDV column and you store that into output variable. Now you need to tell these things to the algorithm because algorithm itself will not find out, right? Algorithm will itself not find out which is your output column, which is your input column. You have to tell it to the algorithm. So that is why I've made these two variables. In capital X, we are storing everything except the MEDV. And in your Y variable, we are storing only the MEDV column. Right. This code you must have seen before. It should not be difficult to understand. Now, so capital X, small y, input and output columns made. The next thing that we do here is we split the data into training and testing sets. So we are going to split the data into training and testing sets. So what we do, we divide our data into training and testing data. Now, this is a very interesting thing which I'm going to show you now, and you will understand the process of training and testing with this example. Okay. In depth, we are going to discuss this thing. So all of you see this is your data. Correct. Now, we have to perform the training. Training means we have to teach the algorithm on this data, but we have to also test it before we launch it into the real world. Okay. So for that purpose, suppose we have our data given to us, right? We have been given a data. What we do first thing is, let's say these 34 rows, you see from 2 to this 34, let's say we have only these 34 rows. This is my 100% data. So what we do is I'm going to take all this and put that into a color, say this. And now the green color part that you see is your 80% rows. Out of 100% rows which you have, 80% rows you are going to take for the training purpose. Means the machine learning model will be trained on this much data. They will only see this much data during the training process. The remaining data that I've put into the white color at the bottom, that will be used for the testing purpose. Okay. And that will not be shown to the model in the training process. Right. So now the green color part is known as your training data and your bottom white color part is known as your testing data. Okay, so this is a general convention. Whatever data has been provided to us, we have to divide that into 80-20 ratio, 80% training data, 20% testing data. Okay, now the question is, why do we need to do the testing of the model? Okay, it's a very obvious thing, common sense. Why do we need to do the testing of the data? Because if you do not need to do the testing of the data, how would you understand how well your algorithm has learned the patterns present in the data? Okay, without testing, how will you know? So imagine you have a student here, right? You have a student and this student goes to university. Now this student is going to be taught a subject. Okay, this student goes to university and they are taught a subject. Can the university just assume that since we have taught the student would have learned everything and will be able to contribute in the real world after that? No. Before you graduate the student, would you not want to test the student? Before you graduate the student, you are going to test them. Yes. Same way is your machine learning. Okay, machine learning goes through the training process. Like a student goes to university for what? Training, for learning. ML process goes through the ML algorithm goes through the training process. Okay, on the data. On the basis of this data, it will be trained. But are you going to assume that since we have done the training, our model has been trained very well and we can use that, right? This ML model that has been made, we can use that. Can you just think like that? No, you have to test it. Okay, now see, this ML model will be used in the real world. Once you do the training on your system, you will use this ML model in real world. Where are you going to use this ML model? You will integrate your model in a website, okay, or you will use it in a website, in an application, so that website, that application has the prediction capabilities. So you are going to use this ML model for real world situations, in real world applications. So if you are just using it directly, you do not know how accurate its predictions are, and there can be a disaster that can happen because of that. So before you use this ML model, you have to test it to get an idea how well it is going to perform in the real world. And if it is not performing very accurately, you might want to improve its performance, and you might want to change the algorithm if one of them is not working well. Okay, so you have to do the testing. Now, in many situations, you might not have a separate testing data. All you might have is one data which is given to you, one data file which is given to you. So that is why you have to divide that data file itself into training and testing data. If you have a separate testing file, then perfect. You can use one of the file for training and one of for testing. But that will be in very few cases. Generally, you will have only one file from which you have to do the training also, testing also. So you take 80% data for the training purpose, 20% data for the testing purpose from the same file. Okay. So that is why I am saying here that these green color part that you see of the data will be used for the training purpose, and the white color part will be hidden from the data, will be hidden from the algorithm during the training process. And once it has been trained, then we will be using these for the testing purpose. I'm going to explain it even further, which will make it 100% clear to you. So this green color part, like I said, is your testing data. So we have divided our data into two parts here, but we have to further divide it into two more parts. You see that this MEDV column is our output column. So we need to color it separately. Why we need to do that, you will understand. Okay, yes. So now all of you see this, there are four parts I have created of the data. Green color, orange color, this purple color, and the white color. So why four parts? You see, this is known as training input columns. These white color part is known as testing input columns. What is this orange color part? Just the orange color part, you see it is ending here. Orange color part is ending here, where my green data is ending. So can I say this is my training output? This is my training output column. And then this is my test output column. Correct. So in a simple way, you can see that we have divided our data into four parts: training input, training output, testing input, testing output. Now, when you use a linear regression algorithm, what are you going to provide during the training process to that? So this is my training output column, testing output column. No, 80% is not fixed, but 80-20 is a very common ratio. We can use other percentages also, but 80-20 is very common. So for now, we are discussing that. We will be using other ratios also. You see, so now I have linear regression algorithm. Understand this part very well. Once you understand this part, which I'm going to tell you now, everything will make sense at this point. How training is done, how testing is done, all things will be clear instantly. So this is our testing output column. This is our training output column. Remember, when you have an algorithm, which is our linear regression algorithm, you are going to give it this and this. These are the two things will be given to linear regression. That these are my input columns, this is my output column. When you provide these two things, what linear regression will do, will find the relationship between these. The input columns and output column, it will find the relationship. Now, what will be created once you provide these two things to the linear regression? What will be created? Our best fit line, right? Our best fit line. Correct. That will be created. And how it will look like? It will look like our m1 x1 plus m2 x2 plus dash 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 plus c. 13 input columns are there. So from m1 x1 to m13 x13 plus c, till that point it will be creating this equation. And when you have this equation, the m1, m2, all these values will be found, and you will write those actual numbers here. Correct. Now what you do with this equation? What you do with this equation that you have here? m1, x1, m2, x2, all these things. So what does it mean when you get this equation? Once you get this equation, it means your training process is complete, right? Once you get this equation, this is your best fit line. This is your best fit line. Once you get that, remember your training process is complete. So if your training process is complete, then what do? You perform the testing process, right? Once your training is done, what do? Testing process. So what will you have is your values will be, or evaluation you can say, right? So you'll have like 1.1 x1, then you will have like 0.87 x2. So all these numbers that we are finding out, it is from the training data. That how, what is x1, x2? This is x1, this is x2, this is x3, this is x4. And these numbers being multiplied with x1, x2 is how much weightage we are giving to each column. That is these numbers. So algorithm is telling us how much weightage it has given to each columns after studying the data. Okay, now what you do with that? Now see the main process of testing. In the testing process, you will take your first testing row. You have these 5-6 testing rows are there. You take your first testing row. But in the testing row, you will take only the testing input value. You will take first testing input column, input row, right? First testing input row you will take now. And what will you give? You will give it to this equation, right? Not the output, not the testing output, just the testing input. You are going to give this white color first row to the best fit line that you have created. What will it give you? What do you think it will give you back? Right? Can we say it will give us the predicted price? Can we say it is going to give us the predicted price for this particular house? Each row is a house. So can we say, given these features of the house, it will give us the predicted price of the house? Yes, it will give us the predicted price of the house. Suppose it has given us the predicted price of the house to be 13.9. Now what is 14.8? You see, 14.8 is a number attached to the 29th row, which is the output. What is 14.8? The actual price. Correct. 14.8 is the actual price. And 13.9 is the predicted price using this best fit line that you have created. Now you are going to compare that. How much is the difference between actual and predicted? You are going to check that error. Okay. Now you will do the same thing for all the testing rows. Now once first one is done, you give the second one. Second one will be given to this best fit line. You will get the predicted price for the second one. The actual is 18.4. Suppose you got 19.3. You check the difference. You do it for all the testing rows one by one. So if you have 10 testing rows, you will get 10 predicted values using your best fit line. Now what you do, you compare all the actual prices with the predicted prices, and if your predictions are very close to actual, you have made a brilliant model. If your predictions are very far away from the actual values overall, you have made a bad model. So training we do on the basis of the 80% data. Then once the training is done, you will get your best fit line. Now to check the performance of your best fit line, we have kept some data hidden. That is my testing data. So I give my testing rows one by one. It will give me the predicted prices. We compare the predicted prices with the actual prices and we get that answer. Okay, we get the performance of the model. So the closer my predicted values are overall, the better my performance of the model, and the far away they are, the worse is the performance of the model. Okay, now see, these training input, output, testing input, output, they are given a variable names. We call this training input column as X train. X, because all the input columns we store into X. Train means training. So training input, X train. The training output column, we call it as Y train. Y output column, train means training output. Then testing input columns are X test. Then this is our Y test, right? X train, Y train, X test, Y test. 4 variables we have to create in this case. Perfect. Now we write X train, X test, Y train, comma, Y test. These 4 variable names we take. And you see, we are not going to divide the data, right? We are not going to divide the data into 4 parts manually. We are going to use a function for that, train test split. So we have a function here called as train test split. This function we have imported from a module. We take this function and we provide it input and output column. And then this function will take care of splitting our data into 4 parts. Okay, that's it. We just need to mention a parameter here called as test size. We have to mention a parameter here, test size, which is I'm going to keep 0.2. Okay, 0.2 means I want my testing data to be 20% and automatically train size will be 80%. Then there is something called as a random state. We will talk about this random state. For now, we keep it equal to an integer number for now, random state. Write it for now. I'll explain what is the use of that. But you see, we are using a function providing our input and output column and the testing data size 20%. Training data will be 80%. Now see, since we are using a function for splitting our data into 4 parts, remember that the sequence in which I have written these variable names, this sequence has to be maintained. Has to be exactly like this. X train, X test, Y train, Y test. If you change the sequence, then your data will be stored into different variables. Okay, suppose if you say X train, Y train. So in your Y train variable, your X test data will be stored. So you have to maintain this sequence because we are using a function for that. Manually, we are not splitting that. Okay, for that. Now let's move to the next, the main part, which is apply linear regression on the training data, right? We are going to apply it on the training data. Now, so we are going to now apply linear regression on the training data. So you see, we will have here linear regression class. The linear regression class we have imported at the beginning. We are going to take that class. And since it is a class, we have to make an object of it. Okay, so I'm just making an object of this class, linreg. This is why you need to know which is a class, which is a function, because you see, this was a function. I did not make any object of that. I call this function, it did something, and the results I'm storing into 4 variables. But here it's a class, I'm making an object of it. Okay, then what you need to do in next line, in the next line, you have to take that object and say dot fit, and you provide X train, comma, Y train. So your training process starts here. These 2 lines of code I was talking about, that when you do these, when you run these 2 lines of code, all the theoretical things I've discussed with you will be done here, right? Calculation of those errors, making multiple lines, checking the best fit line, all those things will be done here by these 2 lines of code I was talking about. And you see how easy it is. You have to take the class, make an object of it, take that object, say dot fit X train, Y train, done. Okay, done. This much easy it is if you have to do it in practical, right? So main part is this much. Actually, it is that one line. Here I'm just loading that object of this class, but your main code is just this line, one line, right? And your training process starts here. And you see, once I do that, my best fit line has been created. Now, can we see the best fit line as a diagram? No. We can't see the best fit line as a diagram. No, why not? See, till 3 dimension, we can visualize the things. Correct. Till 3 dimension, we can visualize the things. But see, our data has 13 input columns. Our data has 13 input columns. So it will have 13 dimension. The plane that I'm going to make, I have to make it in 13 dimensions. So remember that anything above 3 dimension, we can never visualize in the real world. We do not have any technology for that. Maximum we can visualize is 3 dimension. Yes, that visualization I have shown you was for 3 dimension, 3 columns. It was not for more than 3 columns. More than 3 columns, we can never visualize, means in the entire world, there is no tool that exists which can help us to visualize anything more than 3 dimension. It is not possible. Okay, it is impossible. So 13 dimensions are there. So my plane which is going to be made, it is of 13 dimension. That is made, but I cannot visualize that. So does it mean that I can't see anything what is happening? No, you can see. What you can see is the M1, M2 values and C value. Those things you can see, which is what you need to know. You do not have to see the diagram. You have seen the diagram. You see your line will be like that. But what mattered to you or what is important for you is your M and C values. That you can get. So you have to write the name of this object, linrec. And you see, where is my best fit line getting stored? When I ran these 2 lines of code, best fit line has been created, but where it is getting stored? Remember that once this line is executed, right? Once this line is executed, after that, your best fit line will be stored into this object, which is your linrec. This object will store your best fit line. Remember that. Okay. Always, all your ML models, any ML model you make, after the training process is completed, after you see this result, after that, your ML model will be stored into this object, linrec. Whatever is your object here. Correct? That is the thing. So my best fit line is getting stored into that. So if I want to see my best fit line equation, I can say linrec, because in this I have my best fit line dot coef. If I mention linrec.coef, you see it is giving us some values. What it is giving? M1 to M13. 13 input columns are there. So M1 to M13, these are your M1 to M13. And to get the C value, you have to say linrec.intercept underscore. This is your C value, right? So your C value is this, and your M1 to M13 are these values. Correct. Now, what to do with this? We will see. Simple idea is that whichever M value is higher, that is more important. Whichever is lesser, that is less important. Okay, simple idea is that for now. So we have to say dot coef. This thing has all the M1 to M13 values, this variable, and this variable dot intercept has the C value. Just that much I'm doing. Okay, now, so what is this? What do I mean by doing all these things? Let me explain you in a code way what is happening. So there is a class, like I said, called linear regression. There's a class by the name linear regression. Correct. You see, in a class, there are a lot of variables by self dot, and then there are a lot of functions in a class. So classes have variables like self dot, and they have functions. So now you notice that this coef on intercept, there is no bracket after that, right? There is no bracket after that. It means this coef is a variable with underscore, it's a variable. And then you have intercept with underscore, it's another variable. Then you have def of fit is a function. You see this fit is a function, and we are going to use one more function called as predict. I'm going to write that is also a function. Now, why am I writing that? Remember, who can access these functions and variables of a class? If I have a class linear regression, who can access the variables and functions of a class? Remember that only the object of that class can access the variables and functions of a class. Okay, only the objects of that class can access the functions and variables of the class. So what I'm doing, I am taking the object and I'm accessing this fit function linreg.fit. And you see, if it is a function, it will have some parameters. So I'm giving xtrain, ytrain as parameter. Then now you see linreg.coef. I'm trying to access this variable. Directly, I cannot write coef. I have to write the object name dot coef. Directly, you can't write just coef and use that. No, it will not work. So you have to write linreg.coef to use that. Then you have to say linreg.intercept to use that. Understood? So I hope this you are getting properly. What is happening in the background? 100% you are understanding each and every line of code. Perfect. So these are our classes and functions and variables, and how we are writing that, why we are writing it like this, because these are functions and variables of a class and they have to be accessed like this. Now the last thing, our testing process. How do we do the testing? So we will write linreg, right? You will say linreg, which is your best fit line, dot predict. And what will you mention in the predict function? In the fit function, you have given x train, y train. What will you give in the predict function? Means this is my best fit line, and using that, I'm going to predict something. So there are two variables left, x test and y test. Two variables are left as of now. So am I going to give x test and y test both? Right, think about it. Do I give x test and y test both to the predict? No. Remember that I have shown you we were only providing the test input values, right? We were only providing the test input values to predict. Correct. So then when you run this thing, it will give us something, right? What are all these things? These are our predicted values. So I'm going to store this into a variable ypred, right? So when we run this thing using my best fit line, I'm trying to predict the output of these x test, and I'm storing those predicted output into ypred. Correct. Now you see, we have to compare the predicted values with the test values. We have to compare ypred with the y test. Remember, we compare y test with the ypred. You see, this purple color part that you see here, this is our y test. This purple color part, this is our y test. And we compare the y test with the y predicted, right? So not with the MEDV, not with the entire MEDV, just with the y test. So we compare ypred with just the y test. So, but before that, we can visualize it like this. We can say pd.data frame of, I can say, last thing for today, actual is our y test values, comma, predicted is our y pred. Now, so you see, I'm just presenting both of them side by side. This is my first y test value, and this is the predicted for that. This is my second y test value, predicted value for that. Third y test value, predicted for that. Okay. So you can see it looks quite close to each other, not big difference I can see, but you see here there is a big difference. My actual was 50, but predicted 36.1, major difference. Here also major difference, here also major difference. So somewhere it is close, somewhere it is far away. So overall, we have to see. Not joined, I have not joined them, I have just put it as a data frame. I had two arrays, one y test and one ypred. So I'm just making a dictionary first and then converting that dictionary into a data frame to show them side by side. I'm not joining them, I'm just displaying them side by side. Okay, so you can write it like this and you will get to see these are your actual y test values, these are predicted. Now last thing is what we do, we have a function called as R2 score. And to this, if we provide y test, comma ypred, it will compare it for us and it will tell us overall how accurately we were able to predict the values. So now I'm getting a result of 0.75. R2 score is between 0 to 1, 0 to 100%. 0.755 means 75.5%. So the performance of our model is 75% accurate. Means overall, we were able to predict the prices with 75% accuracy. The higher this number, the better. The smaller this number, the worse your model is. Right. Now, you understood how we are doing that. This is a function which is used to uh, compare the y-test and y-pred and give us this result. There is a formula in this function. We will be discussing that formula also. And through that formula, we are finding out the score. So the formula is basically 1 minus, there is a formula like we were calculating y minus y square. So it has a small formula, which is this. Let me write it. So the formula is I is equal to 1 to n. As we move forward, we'll be discussing about multiple measures that we have to take to improve the performance from this point onwards. And can we even improve the performance in some cases or not? We will be discussing about all that as we move forward. Okay. See, this is the formula of R2 score that I've written here. Using this formula, this score has been calculated. So yi is your values, actual values. Yi cap is your predicted values. Then this yi is your actual values. And this y bar is your mean of the output, mean, average of the output. So this is a formula which is there, and using this formula, we are finding out the R2 score, which is this. Again, you do not have to solve this formula, calculate this by hand. This is the formula being used in the background, and we are getting that result. Okay. So through that, we are getting the R2 score. So this is 1 minus all of this. Okay. Okay. So we were discussing about the practical implementation of this linear regression, and I have shown you a few things in that. We will continue on that for a few minutes, and then we will move to our another algorithm, which is logistic regression, and some of the practical things I'll discuss with that. Okay. So when we are going to implement the machine learning algorithms, so they will have certain steps in that. Okay. And I have written this file in such a manner that you can look at it and you can see the steps or the sequence of steps I have taken to solve that, right? To implement a machine learning algorithm on a data set. So what we have done as the first step was we have imported the required packages. So I'm just going to run it once again. See, after importing the required packages, there was this data manipulation and data reading packages, visualization, and some machine learning related packages, right? Now, step number 2 was where we start reading and exploring the data. So here you do these particular things that we have mentioned here. And out of these, some of the things we have done according to what was needed. So the data was this boston.csv. And if you look at it, it was having these 14 columns. And out of these 14 columns, like I said, last one is your output column and the rest are your input columns. Okay. And how do you know all these things? I explained that to you that the person who will be providing this data set to you will give you a data documentation where all the columns will be explained. And for now, if you download the data set from anywhere, you will be able to see this information from that place also. Okay, such as I told you kaggle.com from where you will be downloading the data. Okay, now we next check the shape to get an idea about how many rows and columns we are dealing with. Then we check the data types of each of the columns to see what data types we are dealing with. And here we try to see whether we have any object column. Object column means the columns which have text values. So if you have any text columns, you will have to do the encoding of them. You will have to convert them into numbers because machine learning cannot handle the text values directly. Okay, you will have to encode them first, then you will have to give it to machine learning because machine learning uses the linear algebra concepts and it uses some equations. So you can't provide equations in, the text into equations. That won't work. So that is why we will have to do encoding. Then you check for the missing values for each column. and there are 0 missing values for now. So we do not need to do anything specific as of now. But as we move forward, we will be working on data sets which will have a lot of issues in that. We will fix it. Then to check for the duplicates, you are going to write this data.duplicated.sum, the name of your data frame dot duplicated.sum. This will tell you how many duplicate rows are there, and then you have to mention this drop duplicates function. This function will drop or will remove all the duplicate rows from your data, right? Now, we also should be checking for outliers and removing the outliers, because the linear regression algorithm cannot handle the outliers. Okay, it is a simple algorithm and it is sensitive towards the outliers. See, what are outliers? You must have seen outliers in descriptive statistics where you were studying interquartile range. Okay, so interquartile range is also a tool for identifying the outliers, right? And then there was a formula using which you can remove the outlier. Correct. So I've written a function here using which you can remove the outliers. Now see, so problem with linear regression, one of the drawbacks or limitations of linear regression is, suppose you have this data, so you know you will be passing a line through it like this, closest to all the points. But if you suppose have an outlier means any extreme value which is going to be far away from the rest of the data points. Okay, so say that if you have only one outlier in the entire data set, so your linear regression algorithm or linear regression line will be affected by that also. Means what will now happen to your best fit line? It will now pass from somewhere here, because it has to maintain closeness from this one also, and it has to maintain closeness from the rest of the data points also. So what happens when you have outliers in your data? So your linear regression line is going to be pulled towards that. Okay, this outlier point will be pulling the best fit line towards itself. That is going to happen in all the scenarios. And now you see your best fit line is not passing through any of the data points at all. Okay, so this is going to give very bad results, very bad accuracy, because it is not learning the patterns properly. Okay, so outliers have to be removed if you are working with linear regression algorithm. Each and every outlier has to be removed. So I've written this function. You can look at it. It is very simple. You must have seen. So what you do to catch the outliers and remove the outliers, you see. So first you see, here I've written what means you give the name of your data frame and give the name of the columns from which you want to remove the outliers. Correct. Then what we are doing for each column in this list of columns. So here you will be giving a list of columns and here you will be giving the name of your data frame. So what this function is doing for each column in the list of columns, what we will be checking is we will be checking its quartile 1 value, Q1, quartile 2, Q2, Q3, sorry, quartile 3 value. Then you will find out the IQR value, Q3 minus Q1. Then you calculate the lower bound, which is Q1 minus 1.5 into IQR, Q3 plus 1.5 into IQR. Right. And then you write this code to remove any value which is lesser than this lower bound and higher than the upper bound. Okay, those are going to be considered as an outlier. So this is a very proper function I have given for you. You just need to take this function, and in any data set that you're working with, you just take this function, use it as it is. You just need to mention this function here, remove outliers, provide the name of your data frame, provide the name of your columns, and then it will remove the outliers from each and every column one by one. Okay, and it is easy to understand if you know the interquartile concept, and if you have seen this thing, so you would be able to identify that. Okay, right. So now you see that when we are running this function and when we are providing the data and all the columns to it, it is going through each column one by one and removing the outliers from that. Right. So see what happened after that. Our original data had 506 rows, and after removing the outlier from multiple columns, now only 214 rows are left with us. Okay, so what happens when you remove the outlier using this IQR concept? So if there is row number, say 160, and in this row, you have entire row of data, and suppose one of the outlier is present in this particular row. Correct. So if you have, suppose one outlier value in this row, so what will happen? This entire row will be dropped. That is how IQR concept deals with the outliers. It deletes the row in which outlier values are present. Okay. And because of that, you see, we have lost almost 40% of the rows. If you see, not 40% means more than half of the data we have lost. Right. So yes, more than half of the data we have lost. So in such scenarios, if you are running this code and you're losing half of the data, then it is going to be a problem because now we have very less data and running machine learning on that will not be, you can say, fruitful. It won't work very well because now data is too less. So there is another method also using which we deal with the outliers. So there are two ways in which we can deal with the outliers. Outlier removal that we have done above, which means that removing the rows which have outliers. The problem with this approach is that we lose a lot of data if you follow that approach. Okay. Now, if you have a very huge data set with thousands and millions of rows, and if you lose some of the rows in that, then it is not a problem. You can afford that. But if you have a small data set and if you're running this outlier removal process and you are losing lot of rows, so you can go ahead and follow another method which is known as data transformation. So what is data transformation? If suppose I have a salary column which has values in it, right? And this column has, let's say, 4 or 5 outliers in this. Now, if I do the outlier removal, so those 4 or 5 rows in which outlier values are there, they will be dropped. But instead, I can follow the other method in which we will not delete any row or we will not remove the outliers. What we will do instead, we will transform this column in such a way that the outliers will be present, but they will not behave as an outlier after that. Right. For example, what we can do is suppose we have salaries such as, just for example, we have 400, 200, 550, okay, 600. Suppose these kind of salaries are there in dollars, for example. Now, one person has a salary of $9,000. Now, this is an extreme value. So what you do now, before you use the salary column, you can do the square root transformation of this column, which we will all cover in the upcoming session. Log transformation, box-cox transformation. So ignore these two for now. See, what do I mean by transformation here? Square root. So what I'll do now, I will take the square root of each and every value of this column. Right. And then you see what will happen after you do this. So your values will be going through the square root, and after that in the salary column now you will be writing their square roots, which means that $400 will convert into $20, and same way this 9,000 will convert into $300. Okay, so earlier this $9,000 was a very extreme value, but after conversion it will not be that extreme. Okay, so you see that if you are using the square root transformation and after that also if it is behaving as an outlier, so you can use the log transformation. If this one is also not working, you can use this transformation. One of these three will transform your data in such a way that your data will become balanced and the outliers will not behave as an outlier. Okay, in log transformation, what you do, you take the log of each number. You write it like this, log of 400, then log of 600, like that. You take the log value. So square root transformation we use when we have, you can say, not very extreme outliers. And log transformation we use when we have very extreme outliers. Correct. Now, so we will be talking about all this. So in this case, what happens? Our values are transformed into another values and we do not delete anything. Okay. So this is the data transformation, which we will see. Then we came up to the machine learning process and here we saw this X and Y, then splitting the data into, right, you see. So X and Y, then splitting the data into 4 parts, we understood that. So apply the linear regression on the data here and then we check the coef, which was our M1 to M13 value, then the C value, then there's predictions we have seen, and then there are some performance metrics which are used in regression. Okay, right, like this, right. So when we do the transformation, the numbers change into another numbers, but the property of the data is maintained. Property of the data is not lost. Okay. Now see the performance metrics used in the regression. What are the performance metrics which are used in the regression? See, so one, we have the R2 score. The first one is known as an R2 score and it is also called as a R squared. Okay. Then another performance metrics which is used is known as a adjusted R2 score. Then another one is known as mean squared error and the fourth one is known as root mean squared error. Okay. Now, so you see there are four performance metrics. Four performance metrics are there. And out of these four performance metrics, we will be checking them and they will give me different information. The first one, R2 score, which is also known as R squared. Okay, so you say R2 score or R squared, same thing. See what R2 score is. The technical definition of R2 score is how much variability, how much variability in the output column is being explained by the input columns. Okay, so R2 score, the technical definition of R2 score is how much variability in the output column is being explained by the input columns. Variability means what? Variability means you can say information, right? Variability means information. So how much of the changes in the output column? So output column is our prices, house prices, car prices, like that. So how much information in the output column is being explained by the input columns? The more we are able to explain the output column using input columns, the more will be the R2 score, the higher will be the R2 score. In simple words, R2 score tells us that how well our input columns are able to predict the output values. In simple words, this is the technical definition. But in simple words, if you understand, R2 score is a measure which tells us that overall, how much of the output values are being explained by the R2 score, how closely, how accurately we are predicting the output values. Correct. The R2 score values goes from 0 to 1, means 0% to 100%. The higher the R2 score, the more accurately you are able to predict the output using the input columns. So we need to achieve the high R2 score. Okay, right. Now, apart from that, then there is adjusted R2 score. So one is R2 score, another one is adjusted R2 score. So what is adjusted R2 score? I'll explain. I have written the formula for this. I'll written the code to calculate the adjusted R2 score. It has a particular formula for it. But you see now, what is adjusted R2 score? So suppose I have a data set in which there are 13 columns, for example, 13 input columns, and these 13 input columns are being used for predicting, you can say, the output, right? These are the 13 input columns and you're using the information present in these 13 input columns to predict the output. So say that according to 13 input columns, suppose your accuracy is coming out to be 78%, or in this case, like we have 75%. Correct. It is coming out to be 75%. Now, suppose you increased the number of input column and you added 3 more columns. Now you have 16 input columns. So as you increase the number of input column, what will happen? The accuracy value will increase by some percentage. Let's say it increased from 75% to 80%, something like that. Now you will say that it is obvious that if we take more columns, so we are getting more information and we will be able to predict the output more accurately. So our R2 score should increase. But now suppose I'm saying that the 3 columns that you have added extra, those are unnecessary columns. Okay, 3 columns that you have added extra, suppose they are unnecessary columns. So then should my accuracy improve if I do not have any important information that I'm getting? So I'm adding 3 more columns. With 13 columns, I was getting 75% R2 score. And when I'm adding 3 columns, which are unnecessary, okay, they are not helping me to predict the output. So should my R2 score improve? No, right? It should not improve because those 3 extra columns that we are adding, it is not helping me at all, right? It is not helping me at all to do the predictions. If suppose those 3 columns were helping me to predict the output, then R2 score should improve. Okay. But if 3 columns are unnecessary, unimportant, and they are not helping me to predict the output, so then it should not improve. But the problem with R2 score is that it will increase if you increase the number of columns, even if they are not helpful, even if they are not important, they are not going to help us predict the output better. So if you increase the number of columns, R2 score increases in that case, right? So in that situation, if I'm increasing or decreasing the number of columns, so in that situation, we will be using adjusted R2 score. So when we use adjusted R2 score, what will happen? If 13 columns were giving us 75% R2 score, and if I added 3 more columns, the R2 score will stay same if the extra 3 columns are not important, right? So R2 score will get modified. It has a small problem that if you increase the number of columns, it will increase even if those 3 extra columns were not helpful. So in that case, we will use the adjusted R2 score to see whether the increase in the number of columns are helpful or not, right? So there is this kind of code we have to write. There is a little complicated formula for adjusted R2 score. We don't have any function for that to calculate it directly. So for now, see this, I'll tell you about the formula which is used and all those things. We'll do the discussion about it when we deal with changing number of columns in the data set. Okay, right. So now the another measure is known as mean squared error. Correct. I have given you an idea about adjusted R2 score, when to use, what is its benefit, but we will discuss more about it when we do this kind of thing, when we remove the columns, when we add few columns. So we'll understand it better. See, so we have the mean squared error is the another metric. So mean squared error we have calculated when we were working with the linear regression theory, right? So mean squared error is also one of the metric which we should be checking to get a better idea about the performance of the model. Now see, R2 score is, you can say, a standard way, a standard measure to check the performance of the model in regression. R2 score basically tells you overall how our model is performing overall, not getting into too much of detail what is happening. It tells us overall how your model is performing. But there are few extra things that you would want to know to better understand how accurately your model is performing or how much error your model is making. Let me tell you what is that. See, so mean squared error is going to take the same two things, y-test and y-pred, and it will compare that. Your actual output values of the testing data and your predicted values of these testing data. We compare that in the mean squared error. And you see mean squared error is coming out to be like 23.61, something like that. Right. Now mean squared error, MSE value, is the squared error our model is making while predicting an output. So suppose our linear regression line, our best fit line, has predicted the price of a house to be, say, 70 lakh rupees or 7 million rupees. Those who understand this. Okay, see. So suppose our best fit line has predicted the price of a house to be 70 lakh rupees, or you can say 7 million, whichever metric, whichever number you understand. So it has predicted the price of this house to be this much. Now, according to our R2 score, which we have got 75% R2 score, according to that, you see in the background what is happening, our model is making this much of squared error. Okay, means if my prediction of a house is this much, if my prediction of the price of a house is this much, 70 lakh rupees, so this prediction is having an error of this much. But you see, this is a squared error. You are making a squared error of this much, which is, you see, not interpretable directly when I say squared error. So what we do now, we take the square root of MSE and then we get the RMSE, root mean squared error. Right, you see, root mean squared error we will take instead of that. See what happens when we take the root of MSE. So I've written a function here, np dot square root of MSE value. So I'm just taking the square root of MSE. Why square root? Because MSE gives us the squared error, which is not easy to interpret, which is confusing to interpret. So we convert it into its original form, into its direct form by taking the square root. So when you take the square root of 23.61, it is coming out to be 4.85. Now you see this number is interpretable to us. So what is this 4.85 is saying? 4.85 is saying that when we are predicting the price of a house, our predictions are off by this much. Means the actual price, this is my predicted price. So the actual price is going to be somewhere like this, 70 lakh plus minus 4.85 lakh. Okay, 70 lakh plus minus 4.85 lakh means this is the predicted price. But our model is not 100% accurate. It is just 75% accurate. Means my predictions are not very accurate. It is having some error in that. So whatever predictions I make will be off by this much. Means the actual price is going to be somewhere from 70 minus 4.85, 70 plus 4.85. Correct. So my actual price is going to be somewhere from 70 minus 4.85 to 70 plus 4.85. Correct. So I have given this prediction, but this is not accurate. The accurate will be, the price can be somewhere in this range. Right. So is this a value useful for us? If I'm able to interpret this information, so is this helpful for us instead of just getting the R2 score? Right. Do you think this is going to help you in any way while making these all decisions? Yes, obviously it is going to help us because R2 score was just telling me the overall performance of the model. But this is telling me something more useful because whenever we make a prediction of the price of a house, right? So if my R2 score is like this much, which means we are still making 25% error. So according to that, we got this 4.85. If my R2 score was like 90%, so this number would have been, let's say 1.7. The more the R2 score, the smaller will be the RMSE value. The smaller the RMSE value, the more accurate our predictions are. Okay, because the range will be smaller. So this range is helping me to identify that the actual price is going to be somewhere in this range, which is a useful information for us to take. So I'm saying that R2 score is one metric that you check, and along with it, RMSE also you will be checking always. Because R2 score is telling you the overall performance of the model, and RMSE is telling you something more in depth. Okay, more useful information. So both of the things you will be checking, right? See, MSE is basically a squared error. If I tell you that my house is at a square distance of 100 kilometers from somewhere. Suppose there is a point, and I'm saying that from this point, my house is at a distance of 100 kilometers square. Now, this square thing is not a direct thing that you will interpret. So I'm saying that my house is at a distance of 100 kilometers square. So it is not an interpretable value. So why do we even calculate MSE? Because the higher the MSE, the worse our model is. The smaller the MSE, the better our model is. So instead of MSE, what I'm saying is let's take the square root. So this get converted to 10 kilometer. Now this is understandable to us because this number is saying that my house is 10 kilometer away from this point. So is this making sense to us? Yes. MSE value is the square distance. Okay, square distance. RMSE value is the direct distance. So this is interpretable. This is you can use in the direct manner. Right? So this is the main difference. So that is why MSE you are not going to interpret directly. You will calculate RMSE along with that. Now let's see the last point for this. I told you that there are some assumptions, right? There are some assumptions in linear regression, and when those assumptions meet, then only you will use the linear regression. Otherwise, you will prefer using another algorithms. So there are 4 assumptions I've told you that your data should be linear. Correct, means the relationship between input and output should be linear. Second, means when you plot the error values, it should be showing homoscedasticity, not heteroscedasticity, right? Then when we plot the error terms, it should give us the normal distribution when we plotted all the error values. So those I will show you as we move forward. But the most important one out of those are the VIF score, which is for multicollinearity. Correct, VIF score. So what is the VIF score? Understand it better now. What is VIF score? First, what is multicollinearity? I hope you remember. It was this. Suppose we have the area column and the length of the house and the width of the house. In the same data set for the house price predictions, we have the area column also and we have length and width also. Now the thing is, there is this thing which is area is equal to length into width. Means you can get the area of the house using length into width, which means this column, whatever information this column is giving, correct, whatever information this column is giving, so these 2 columns combined are giving the same information, correct. So whatever information the area column is giving, the same information is given to us by these 2 columns also, same information. Okay, because when you multiply the values of these 2 columns, you get the area of the house. So this kind of thing is what we call as a multicollinearity. Correct. Multicollinearity is when there is high correlation between the input columns. So input column should not have correlation with each other. See, all the input columns that we collect is supposed to be unique information, right? Each input column is supposed to be a unique information. The more unique information we have, the more we will be able to predict the output better. Correct. So input column should not have correlation with each other. It basically means that we do not have any new information. So does it make sense to keep these 2 columns in the data? No. If they are giving me the same information, why to keep them? We can just delete them. Okay. So this is the thing. Now, if you do not delete them, so there will be no problem on your accuracy, right? If you do not delete them, there will be no problem on the accuracy or the performance of the model. The problem will be in your M1, M2 values. You see, for each column, we have M1, M2, M3. Means if suppose this is my column 1, so it will be having M1. If this is column 2, M2, column 3, M3. So with each column, we have this M value attached. M value is basically, right, No, if you keep all these columns, your R2 score will not have any effect on that. Right? If you keep all these three columns, which are correlated to each other, R2 score will not have any impact on that. Okay. So the performance of the model is not impacted if you keep these columns in the data. What is impacted is the M1, M2 values. Correct. What will be impacted are these weightages. What are these M1, M2, M3? These are weightages that you give to different columns. Now, you see, suppose your area column is having a weightage of this much. Okay, according to when we are studying this, and let's say these two columns are not there. So if suppose only area column is there, so when I ran the linear regression algorithm, it found out that area column has this much of contribution in the price prediction, a weightage of 1.2. Correct. So when only the area column is there, so linear regression identified that it has a weightage of this much, 1.2. Correct. And the higher the weightage value, the more important that feature is. So these weightage values are very useful for you, very important for you as a data scientist, because when you look at all the columns which have more weightage, you say that these are more important in determining the price. Correct. If number of floors is having more weightage, so you will try to build a house which has more floors in that, because customer will pay more. It has more weightage in that city. Right. So it is important for you as a real estate company that whichever factors are more impactful, you will take care of that factor, because that way you can increase the prices and you can make more money. Right. So the area, if it was present alone, it had suppose a weightage of 1.2. Now, if these two columns are also there, the length and width, right? If these two are also there, then what will happen? Since there are three columns which are giving me the similar information, so what will happen? This will become 0.6 and they both combined will become 0.6. And it will become like 0.3 and it will become like 0.3. Right? Both combined 0.6, this 0.6, because this column and these both combined is giving me the same information. So now we will divide the weightage between area and these two. So 0.6, 0.6. So you see its weightage is getting divided. Now if you look at the area column, you will think that the area column has only this much weightage, only this much importance or contribution. So the problem is, are you not getting the wrong information about the importance of the area column when you see this number compared to 1.2? Right? Are you not getting the wrong idea about the importance of the area? Right. So it is correct that we are now getting wrong idea. Its actual weightage is this much, which is quite high, but because of multicollinearity, it is getting reduced to a small number. And this is the main problem with multicollinearity. Okay, so multicollinearity does not affect the performance of the model. If it is affecting, it will be very minimal, but it generally does not affect the performance of the model. What it affects are these interpretations about these weightages. Got the idea about the multicollinearity and its main issue? Now you see, how do you check for VIF score? So VIF score is having a formula of 1 upon 1 minus R square, or R2 score, right? 1 upon 1 minus R2 score. You see, so what is the VIF score telling us? So VIF score checks how much is the correlation of one input column with other columns. Okay, so VIF score basically checks that if I have a column 1, how much it is correlated with other columns. Now, a column 1 can be related to one another column, two another columns, three columns, four columns. So there is no limit on that, right? Now, the more this column is related to another columns, the more will be its VIF score. Correct. So you are trying to basically check how much is how much this particular column is correlated with another column. Now you see, I have written some code here, which I'll explain. So we have from stats model.stats, this is a package from which we have this function called as variance inflation factor, VIF. Now, we take this function, and this function is going to help me calculate the VIF score for each column. Because when we have a large data set, manually we cannot identify which column is correlated and how much. Manually it will become very, very complicated if we need to do that. Okay, so we have a function designed for us inside which there is a formula which is doing all this calculation for us. Now we will apply VIF on the entire data or on each of the columns one by one, and it will tell me the scores. If the VIF value is anything more than 5, so that column is highly correlated with another columns, we can delete that column. Okay, now you see. So what is the code I've written? First, I'm taking a variable VIF in which I'm storing an empty data frame. I'm making a pd.data frame, an empty data frame, and I'm storing that into VIF variable. Now what I'm doing, I'm going to this variable, which is our VIF. You see, for now, it is an empty data frame in first line of code. In second line, I'm creating a column. In this, I'm creating a column by the name features. And what I'm storing into this column is the xtrain.columns, means the name of the columns, the name of the input columns basically, right? So in this case, you see all these names of the column will be stored. So we have 13 input columns. Those 13 names will be stored into this column. This is our second line of code. Third line, in third line, I am creating another column into this data frame called as VIF. You see, that is your second column that you're creating. Now, in this column, the main calculations I'm doing. So what I'm doing now, I am creating a list first. See, VIF, and I'm creating a new column by the VIF. So VIF, this is the name of the data frame. This is the name of the column that we are creating inside that. Now, what values will be filled in that? So in that, I'm filling a list. Inside list, there is a function called as variance inflation factor. Okay. So variance inflation factor is a function which I'm applying on xtrain each column. Okay. So you see here, it is xtrain dot values comma I for I in the range of xtrain dot shape of 1. So what is shape? You see, when you check the shape, it is the number of rows comma the number of columns. So I'm talking about xtrain. Xtrain is the input, right? Training input. So it will have 13 columns, right? So xtrain dot shape will give you this. And what is 1 means? Xtrain dot shape of 1. What does the 1 means? See, this is going to be given to you by this code. So what does the 1 means? Yes. So this is a tuple. This is 0. This is 1. So you are picking 13. 1 means the second value in this tuple. Correct. So what you have now for I in range of 13. Correct. For I in range 13. So which means that you are running this variance inflation factor on 13 columns one by one. So what you do now? So you have range of 13. So you'll go from first column to 13 column. Now when you say for I, in range of 13, what happens? It goes like this: 0, 1, 2, 3, 4, 5. 0 means first column, 1 means second column, 2 means third column, 3 means fourth column, and it will go till 12. So when you say range of 13, it goes from 0 to 12. Because the numberings of the columns are also like that. The index number of first column is 0, not 1. So 0 means first column, 1 means second column, 2 means third column, 3 means fourth column. So you are saying that for 13 columns, which are these 0 to 12, you have to do this. Correct. Now what you are saying? So first time when the loop runs, this is going to be 0, I is going to be 0. Correct. And xtrain dot values means of the 0th column of the first column, take all the values of this entire column and check the correlation of this column with another columns. So variance inflation factor is a function which will check the correlation of that particular column with the other columns. So are you able to understand this entire code? So for I in range of this, it means we will go to each column one by one, starting from 0 to 12. So this will become 0, then 1, then 2, then 3, then 4, like that till 12. So one by one, we are going to each column, taking its column values and checking its correlation with the rest of the columns. Okay. And who is doing that? This function has a code in the background. This function is calculating the correlation between this particular column values with other columns. Right. Now you see, once we have done the calculations, we have stored that into this particular variable. In the second line, I'm just rounding it off. Like the values are supposed like 89.2, 6, 8, 5, 3, 1. Suppose the P ratios VIF value is showing like this. So I'm rounding it off to two decimal places so that it becomes 89.27. So you see the entire VIF column, I'm rounding it off to 2 decimal places by using this round function. So here we are doing the main calculation. In the next line, I'm just taking all the values of this column, rounding it off to 2 decimal places. Then in the next line, I'm just sorting it, right? I'm just sorting it from maximum VIF to minimum VIF. Correct. So now you can see. So round is this function. Round is a function to which if you give a value, let's say 11.7352, put a comma 2. So 2 means how many decimal places you want to round it off to. So it will be rounded off to 11.38. So this is a value which you are taking and round it off to 2 decimal places. It felt complicated, but now I've explained all these things, all these terms, so you now can understand. Okay, so anytime you have to check the VIF score on any data, you can just simply copy this code and paste it as it is. As it is. Okay, because in all the scenarios, you are going to have the extrain variables. So you can use this entire code as it is, copy paste. And you will get the VIF score of the columns in any data set. Correct. Now see. So there are multiple columns that you see here are having the VIF score of more than 5 and much more than 5. Okay. So VIF of 5 means this. So why did I say that VIF of more than 5 is bad? Because see, when the VIF of so when I have VIF of say 5. So what does this mean? It means that, correct. So it is like this. The formula I was talking to you, it is VIF is equal to 1 by 1 minus R2 score. You see, so VIF is suppose 5. Okay, what does the VIF tell us? Understand, VIF is not talking about the output column or not about the performance of the model. VIF is only focusing on the input columns. Understand, VIF is only focusing on the input column. It has nothing to do with the output column at all. Okay, only the input columns. So I'm saying if a column has a VIF score of, let's say 5, equal to 5. If suppose this is having VIF of 5, what does that mean? It means VIF is 5 and we say 1 by 1 minus R2. And if you solve this, you are going to get R2 is equal to 0.80. Means if you transfer this here and it becomes like, it becomes 5 minus 5 R2 is equal to 1. Now you send it this side. So it will become minus 5 R2 is equal to minus 4. You remove minus and minus, you can do that. And then you say R2 is equal to 4 by 5. Okay. So what is 4 by 5 here? So if you see 4 by 5 is equal to 0.8. Okay, 0.8, which means that the column whose VIF value was 5 is 80% correlated with the rest of the columns, with some other columns. Correct. So what you're doing now, right? What you're doing now, you are predicting the other columns, or you can say you are predicting the value of this particular column using other columns. And you are able to predict 80% the values of this column using other columns. So what is this 0.8 is telling us basically this is an R2 score. So we are saying that the values of this column, we are able to predict 80% of the values of this column using other columns. So which means almost the entire thing of this column we are able to explain with VIF, which means it has high correlation with other columns. If other columns are able to explain 80% of information of this column, it means that it has high correlation with another ones. And the more the number is compared to 5, the more is the correlation. Correct. So now what we do to handle this thing, the highest VIF score which is there, that column we will delete first. Then we will train the model again without this column. So what I'll do now, I'll drop the p ratio column and I will run the linear regression again. And then again I will see how much VIF score is coming next. Because when you delete the first one which has highest correlation, highest VIF, so other columns VIF will also reduce when you delete that one. So you should not delete all the columns which are having VIF of more than 5 at once. No, you are not going to delete all the columns at one time which are having VIF of more than 5. Otherwise, you will lose all these columns till this 11.14. So we do not delete all at once. We delete one by one. So first I'll delete this column, then train the linear regression again, and then run the VIF code again without this column. And then we will see how much VIF I'm getting. If suppose the second time I saw that RM is having a high VIF, but it will be less than this. It will be reduced. All these other VIFs will be reduced. Okay. Then we will remove the RM second time. Correct. We can remove this RM column second time. Then we will train linear regression again. So we are deleting columns one by one. And we will keep doing this until we have all the columns and their VIF score less than 5. We'll do this continuous basis. And the next we have to discuss is the logistic regression algorithm. Now, so one algorithm that we have just now studied is the linear regression, and it was applied on a regression data set. The second algorithm which I'm going to cover is the logistic regression. Let me check the file. Yes. So I'm now going to cover the another algorithm, logistic regression. See, it has regression in its name, but it is used for classification purpose. Classification means to predict the output which is in the form of yes, no kind of things in the categorical form. Right. So why does it have regression in its name? Should it not have a logistic classifier if it is used for classification? We'll understand all the reason for that. Okay. So let's see about this algorithm. And before I explain you the working of this algorithm, logistic regression, how does it do the classification? Classification means what? Given the inputs, this model has to predict whether it will be yes or no. This kind of output we have to predict. Like in linear regression, our best fit line was supposed to predict a number, right? It was supposed to predict a number. So in this case, we will try to predict a categorical value instead of a number. So first thing I will start with like a story thing. Means why can't we use linear regression for this task? Because linear regression is an algorithm which we have just now studied, and it was one of the first algorithms which have been developed for supervised learning. And if we have already created that, if we have already got that algorithm, can we not just make some adjustments into that and use it for classification purpose also? Why do we need to create a new algorithm? First, we will discuss that. Okay. So now let's understand that scenario first. What if I use linear regression with this? What are the challenges we will face? What are the problems we will face? And can we somehow not use the linear regression for classification? Because if I'm able to use linear regression for classification also, then we do not need to study a new algorithm, right? Then it is all perfect. Because we have to study one algorithm less and we have to develop one algorithm less. Okay. So anytime a researcher writes a research paper to create a new algorithm, to design a new algorithm, they think about all these things. What is the problem with the existing solution for which we would need a new algorithm? Because if there is no such problem with the existing algorithm, we don't need to create a new one. Because even if we create the new one, then no one will use that. Okay, because the existing one is working fine. Now, so let's understand with this data what is the problem if we use linear regression on this. And after that, when I explain you the working of logistic regression, you'll understand it very well. Logistic regression is a little complicated. If you see some explanations online, you will find it little complicated, little confusing. Okay, so I will try to make it easiest for you so that you can understand it very well. Okay, let's get started. So I have taken a small data to explain you all these working here. Suppose I am uh, having a data of some of the people related to diabetes. Okay, so say I am working in a hospital or for a hospital chain as a data analyst or as a data scientist, and we have collected the information of some people who have came for the checkup of diabetes. So first person who came to the hospital for a checkup, we checked this person's sugar level, and this person had some sugar level, and this person was found to be diabetic. The second person was also having some sugar level, but this person was not diabetic. Maybe their sugar level was very less. Okay. Now, so like that, we go ahead and we have collected the data of multiple people. Some had diabetes, and some did not have diabetes in the past. Now, on the basis of this much information, we have to train a machine learning model. We have to teach an algorithm what is the relationship between the sugar level and diabetes. Okay, and once it has learned those patterns, then we will take any new person, we will just provide their sugar level, and this model will tell us this person has diabetes or not. Okay, now you will say that this a person can also do. Why do we need algorithm for that? See, it is just an example to help you understand how this learning is going to be done. But obviously, we will not be having only one factor. We will be having 50 different factors to predict this. Okay, so I'm explaining for one input, one output, but you will have multiple inputs. You can expand it to that. We'll see. So for now, if I take this kind of data where I have one input, one output, you see, we will convert this output also into numbers. So yes will be converted to 1, no will be converted to 0. Yes into 1, no into 0. Right. So both the columns will have numbers like that. So now, see, if I try to plot this data, then you can plot it on a single line. You do not need this two axis to plot it. In a classification data, if you have one column, then you can represent the entire information on a single axis. In regression, what happens if I have suppose area of the house and the price of the house? So I need two columns, area on one and price on one axis. Okay, so whenever we plot the information in regression data, the input and output column both are plotted. Okay, so if you have 13 input column and one output column, so 14 dimensions will be required to represent that information. Okay, 14 axes will be required. But in classification, what happens? Only input columns you plot, output column you do not plot. So what we do with the output column, you see. So suppose I have taken one single line, which is x-axis, and this is sugar level, starting from 0 going forward. So one person had this much sugar level. One person has this much sugar level. One person has this much sugar level. One person this much, one person this much. So for each person, we will make one dot. A dot means a person has that much sugar level, means going from 0 to a number onwards. You see, so the plotting of the data points we will do using the input column. But what I can do with the output column in classification is we can color them. Means after plotting all the points, so when I just plot all the points using this input column, I'll let's say put them into pink color. But now when I look at the output column, I can put them into two different colors. The people who are diabetic, I will color them red or with the pink color, and people who are non-diabetic will color them with green color. Okay, so that I can identify there are two sets of data point. Here we have two categories of data point: diabetic patients, non-diabetic patients. And why do we need to do that? Because in classification algorithms, we are supposed to make a line we are supposed to make a line to divide our data into two different sections. Here we do not make a best fit line which is passing through the data. Here our main focus is to make a separation boundary. We make something called as a separation boundary, a decision boundary. And the separation boundary has to be created in such a manner that on one side we should have one type of data points in majority. On another side, we should have another data points in majority. Okay. Now, so like if I make a line here, if this is the separation boundary I'm making here, I'm saying that below this sugar level, most of the people are non-diabetic. And above this, most of the people are diabetic. Okay. So now we need to make this kind of separation boundary in classification to separate two classes into two different sections. Correct. Now, can we have three categories also in the output column? Yes. Can we have four categories also in the output column? Yes. So for that, we will need multiple boundaries, not just one boundary. We will need two, three uh, separation boundaries if we have multiple categories, which we will discuss. Okay. So now you got the idea. We have a classification data where output is categorical. So using input values, we can plot the data points, and using the output column, we can color them. Why to color them? So that we can identify where to make a separation boundary, so that on left side of it, we have one points in majority. On right side of it, we have another set of points in majority. Correct. Now, so to explain you the difference between linear and logistic, or to explain you the limitations of linear regression on a classification data, I am now representing this data in this form. Okay, this because this way it will be easy for us to understand a little bit what is the problem with linear regression. See, so how did I represent this data in this way? You see, on the x-axis I still have the sugar level, but I'm making a y-axis here, which is I have put the no or 0 and yes or 1. Means the people who are not diabetic, I'm putting them into this line, and people who are diabetic, I'm putting them into this line. I'm just separating them into two different lines of no and yes, so that I can clearly see the difference and I can understand whether linear regression will be suitable for that or not. Okay, all good till now. So I will move forward from this point. Understood the idea, understood this setup. Now, first, let's try to fit a best fit line in this data. If I apply linear regression algorithm on this data, we will fit a best fit line to this. And how will that look like? How will that perform? So, you know, the best fit line is a line which passes closest to all the data points. So we have some data points here, some data points here. So when I make a best fit line, it will go through it somewhat like this. Okay, it will go through the data point somewhat like this, so that this line is closer to these points also, and this line is closer to these points also. It will pass through the center of both of this data, right? And this will be our best fit line. Now ignore this yellow curve that we have made here. That is going to be made by the logistic regression. We will understand how it comes, but ignore that for now. Just focus on this white line that we have made. This is our linear regression line that I'm making on the data. Now, the thing is, once we make the line, once we make this best fit line, so what it means? Creation of the best fit line means that our training process has completed. Okay, once we have created our best fit line and it is done, it means that we have completed our training process, right? And now we are going to use this line for future prediction. So now what I can do, I can take a person whose sugar level is, let's say, this much. Okay, starting from 0 here, the sugar level of this person is this much. How will I predict any output using the best fit line? So we touch it on the best fit line and we touch it here. Okay, we touch it here. So you now see here we have 1, here we have 0, means this is no, this is yes. And when I'm touching it on the y-axis, it is somewhere more than 1. So suppose there is a person whose sugar level is, let's say, 172. Just for example, I don't know what is the range of values. So say that a person, which is this one, has a sugar level of 172. And I predict the value for this person to be 1.68. Will this output make sense to you in classification? Can you look at this number and tell whether this person is diabetic or not? See, imagine that you do not have any graph to see like this. You do not have any graph. You just have an input. You give this input to your algorithm, your linear regression, and linear regression gave this predicted output to you for this person. Now, when you look at this kind of output, will this output make sense to you in classification? No. Okay, because in classification, I need yes, no. Okay, or we need 0 or 1. Only two answers I need, only two predicted values I need, 0 or 1. Means yes or no. No other number will make sense here in this classification. So the first problem with the best fit line is that when you use the best fit line, it will always give you this kind of predicted output, which is continuous, which is numerical in nature. But that does not help us in classification. This is first problem with linear regression. This is first problem that you will face when you use linear regression. So when the researchers saw this, they thought, let's do something. Let's try something and let's see, can we somehow use this output for classification also? So they tried something. Let's see what they tried. They thought that, can we not make a cutoff boundary somewhere? And if any further value, if any given input is more than that cutoff value, so its predicted output will be yes. And if it is less than that cutoff value, then its predicted value will be no. So let me show you what they have done to make this thing usable. They said that let's take a 0.5 point. Let's take a point here which is at 0.5. Now, why at 0.5? This they have decided. I am not deciding that. So it is a fixed thing. They have decided that let's take a point at 0.5. Okay. Now, from this point onwards, we will extend this line and we keep extending it until this one touches our best fit line. Okay. We are trying to touch this on the best fit line, not on the S curve. Forget the S curve that you see, yellow one. We are touching it on our best fit line. It is touching it here. Now, wherever it is touching the best fit line, from that point, we will make a straight line. From that point, passing from that point, we'll make a straight line like this. Okay, straight line like this. What is this? They called this line as a decision boundary. They have called this line as a decision boundary. Okay, or this separation line which I was talking about. You see this line I was talking about. So this is the separation boundary, or in technical terms, it is known as decision boundary. Let's say this is at 155. For example, this line we have made at 155. Now, 155 becomes our cutoff value. Okay, wherever this decision boundary is made at whichever point. So 155 becomes our cutoff value. It becomes our threshold. So now we said that we do not need to use the line further. We use the line and we made a decision boundary. How we use the line here? You see, we touch this 0.5 point on our best fit line, and wherever it touched at that point, we made this a decision boundary. Correct. So once we have made this decision boundary, we now do not need to use the best fit line onwards. So now if I have a person whose suppose sugar level is this much, now I do not need to touch it on this line and get this prediction. No, now I do not need to do that. I will just see that is this point on the right side of this. So this is a number, let's say 168. So is it on the higher side or is it on the lower side? So we can clearly see it is on the higher side. So if it is on the higher side, this input value, so we will predict its output to be yes. Means this person is diabetic. And if I now have a person whose sugar level is this much, this person is on the left side of this boundary. So this person, we will say that is non-diabetic. So what we have done now, we have found a solution somehow to this problem. And at this point, it feels like a very good solution, right? Because now I do not need to use the best fit line and I won't be getting this kind of output because I'm just comparing my inputs with this cutoff. So I'm just now seeing that if a person has a sugar level of this much, I'm just comparing that with this cutoff. If that input is more than this cutoff, their prediction will be yes. And if input is less than this number, then their prediction will be no. Correct. And see, this person I'm talking about is a new person who is not in our data set. I'm saying that suppose tomorrow a new person comes and their sugar level is this much. We need to predict using this model whether they are diabetic or not. Okay, so when I'm writing these numbers, I'm talking about a new person who comes to hospital. Okay, so now it feels like a good solution. As you can also agree to this, it feels like a good solution as of now, that it is making sense. We have got a decision boundary, and through that we got this threshold value, this cutoff value, and now everything is working fine. But there is another challenge that comes into picture now. Okay, with this approach, there is a challenge that comes into picture now. What is that challenge? The challenge is, right, the challenge is, there are two challenges which are now going to come up. You see, suppose in our data set, there is an outlier point. Means I have one more data point. We have 9 values or nine rows in the data set, and one of them is this outlier point. Means these are the people, and this is one more person in our data set whose sugar level is this much, very high. Okay, and this is also present in our data. Now, if I have this outlier point, what will happen to our best fit line? Will it change or will it stay same? Correct. So if we have this another outlier point also, so will our decision boundary, sorry, will our best fit line change? Obviously, it will change according to that, because just few minutes ago I've told you the best fit line is pulled towards the outlier. Whenever we have outlier in the data, the best fit line will always be pulled towards it. So now your best fit line with this data will look something like this. Okay. Now you see, this is our second best fit line we have made because of this data. And you see now this has shifted from here to here. And why did it shift? Because of this outlier point. Because it has to maintain closeness from this point also, and it has to maintain closeness from this points also. It is now like that. Now, is it passing through the data points properly now? No, because this line is neither passing through these points nor passing through these points. So it is not able to understand the patterns properly at all. Okay, so this is one thing. What is the problem with this? The problem is, you see, now we will be touching it on this line, and now we will be making an updated decision boundary here. So earlier, if the cutoff was at 155, now the cutoff will be at, let's say, 158 or 160, something like that. The threshold value moves forward and the cutoff value moves forward, right? Now, if the outlier is even more extreme, the line will shift even more in that direction and your cutoff will move even further. Now, don't you think if the cutoff moves higher, then a lot of predictions will start to become wrong? Because you see, earlier, if there was a point here, right? If suppose, you see, if suppose there was a point here. So according to our perfect best fit line, this would be classified as a diabetic person. But since my best fit line has changed because of outlier, my new cutoff is this. So this particular data point is now coming on the left side of this new boundary. So this person will be called as non-diabetic according to the new boundary. So you see the danger here, because our best fit line is changing. According to that, our decision boundary is also shifting, and we are making a lot of wrong predictions because of that changed cutoff value. Our performance of the model will become bad, right? So this is the first challenge. This is the another challenge that comes up. So first challenge was getting this kind of output, which we solved by making this decision boundary, by making this cutoff. We solve this. Second problem that comes up is outlier. And because of outlier, the best fit line shift. Because best fit line shifts, the decision boundary also shifts. Our cutoff also shift, which is wrong thing, which is bad thing. Now you will say that, can we not just remove the outlier and then everything will be perfectly fine? Yes, you can do that. Outliers are some of the values. So you can say that I will remove the outlier and then everything will be back to normal. So can we do that? Yes, we can do that. But now let me discuss you the third problem that will come into picture. So now suppose you said that let's remove this outlier. Now this line goes away, this line goes away, and everything is back to normal. Okay, problem solved. Now third challenge that will come up. See here, I have made a decision boundary, something like this. So now I'm saying that if you did that, if you remove the outlier, and now everything is back to normal. So now let me tell you the third challenge that you're going to face, which is the major challenge here. The major challenge is, say that tomorrow a person comes and you see you have made this cutoff of 155, a fixed cutoff of 155 you have made according to this best fit line and decision boundary. Now say tomorrow a person comes whose sugar level is showing to be 156. Okay, tomorrow a person comes and their sugar level is 156, which is very little on this side, just crossing the boundary point. So can you say for sure, are you 100% sure that this person is going to be diabetic? Just because it is on the higher side of the boundary, are you 100% sure that this person is diabetic? Means if it is just crossing the boundary and very close to boundary, can you 100% surely say that this person is diabetic? No. Okay, no. Because you see, these numbers of diabetes or anything, they are not like a fixed number. Okay, that when this number is there, then this person is diabetic. When this number is there, this person is not diabetic. See, there is a general idea that it has been observed that more than this number, if someone has the sugar level, the blood sugar level, they will be generally diabetic. It's a general idea. But the thing is, if suppose tomorrow a person comes and their sugar level is 156 on checkup, there can be multiple reasons of that. So maybe this person is non-diabetic, and when this person came for checkup, just one day before they have gone to a party and they ate a lot of sweets. Okay, just one day before, and the next day they went to for checkup, or 2 days after they went for a checkup, and their sugar level is showing temporarily high. Or maybe they were doing some maybe they were doing some stressful work for the last 4 or 5 days, and because of stress, the blood sugar level gets modified, means it is impacted. Okay, so mainly you get diabetes because of lack of sleep and because of stress, not because of sugar. Okay, you must know that you never get diabetes because of eating more sugar. You always get diabetes because of stress and lack of sleep, right? So the thing is, this person might be having more stress or lack of sleep from the last few days, and because of that their sugar level is showing high. Okay, so it means that this person's blood sugar level is just temporarily high. That is why this is just above the boundary. Okay, so I'm trying to tell you that if this person was actually diabetic, they would have generally a sugar level much higher than the cutoff, not very close to the boundary point. Okay, so the problem with this kind of fixed cutoff, or like this defined boundary, the problem with this is the values, the input values, which are very close to the boundary. You can't just say that this is going to be yes or this is going to be no just because they are on one side of the boundary. You can't say that since a person is just having a sugar level 154, they are definitely non-diabetic. So maybe that person is diabetic who has taken care of health very well and their blood sugar level is showing less. Okay, maybe that person is diabetic. So having this kind of defined cutoff or a fixed cutoff is not very helpful in these scenarios. What will be a better option in this is to attach a probability along with the answer. Okay, so see now, what is the solution for this? The solution which has been proposed or which has been approached by the people, by the researchers, can we say that since this person is having 156 sugar level, which is above the cutoff, so can we say that this person may be diabetic or this person is diabetic, and that I'm saying with 55% probability. Will that be a useful information for you? Instead of just saying that this person is diabetic, can we say that this person is diabetic, and that I'm saying with 55% probability? Will that be a helpful thing for us? What do you think? If I'm attaching a probability with the output, will that be a helpful thing for us? The answer is yes. How? Let me show you. How? So suppose there is a person and you're saying that this person is diabetic. So if you say only yes, you might be wrong because this is just closer to cutoff. So if you're just saying yes, this person is diabetic, you might be wrong, but you are saying that this person has 55% possibility of being diabetic. So if I tell you, if I'm a doctor and if I tell you that you have a 55% probability of being diabetic, can you go ahead and do the further checkup to be sure that you have diabetes or not? Means if I'm telling you with the probability that you have 55% probability of being diabetic, which is not close to 100%, which is in the middle, half and half. So with this percentage, can you go ahead and do the further checkup, other checkups apart from sugar level, to be sure that you have diabetes or not? Yes, we can do that. So doctor also can do the further checkup apart from sugar level to find out whether this person has diabetes or not, given this percentage. Now, if there is a person whose sugar level is 172, very high compared to cutoff. Okay. So now a person is having a sugar level of 172. So can I say that for this, the prediction will be yes, this person is diabetic and the probability is 99%. Okay, will it be a better thing to say than just saying yes? So I think yes, it seems to be a better option, because if I'm saying that yes, this person has the chances of being diabetic with 99% probability, I'm saying that with 99% surety, I'm saying that, then it means that this person has diabetes, because 99% is very high, close to 100%. So this person knows that this person has diabetes. They do not need to do any further checkup. They know, means it is sure, right? So what is happening with this probability thing, that I can take the further decisions whether to consider this person as diabetic or not. I can further decide if I see the probability attached with that. Otherwise, if I did not have this probability value, then I would have said yes for this person also for 172, and I would have said 1 for this person also, which does not seem very right, very correct. Okay, so this is what the logistic regression is going to do. So when they saw this challenge, they created this thing, they created this logistic regression algorithm, which is going to do exactly that. Okay, which is going to predict the output with a certain probability. And see, because the logistic regression predicts the probability, which is going to be a number between 0 to 1. This is why it is having a word regression in its name. Okay, because logistic regression actually predicts a numerical value. It gives you the probability of a person being yes. Okay, so what we do in logistic regression? We find out this. We find out what is the probability of the person being diabetic, given that the inputs are there for that person, given the medical conditions are given for that person. So in logistic regression, whenever we give an output, whenever the logistic regression gives an output, so it is always the probability that a person is diabetic given the input values, given the medical conditions. Or in general terms, you can say we always represent the probability of the output being yes given the input values. Okay. So we always give the we always give the output as the probability of the output being yes, okay, given the input. So if suppose the probability came out to be 0.2, means 20%. So the probability of output being yes is 20%, which means 80% is of no. Okay, so we always give the probability of the output being yes given the input. We never say it for no directly. No, we do 1 minus that, 1 minus the probability of yes. Correct. And because the output is this kind of probability, this kind of number by the logistic regression, this is why logistic regression has a word regression in its name. Okay, otherwise it would have been called classifier. Okay, now what we do, we put a cutoff of 0.5. If this probability is less than 0.5, we convert it to no. And if this is more than 0.5, we convert it to yes. So this is an extra thing that we do. We put a cutoff of 0.5. And if the probability of yes is less than 0.5, it becomes no. And if the probability of yes is more than 0.5, then we convert it to 1. Okay. So this is an extra thing we do. This is not the part of logistic regression. Logistic regression gives you an output, which is the probability of the output being yes. Got the idea? Perfect. I hope you understood the story till this point. We were talking about this concept of logistic regression, where I have explained mainly this much part that what if you try to use linear regression for classification? Okay, what will be the challenges with that? And we saw a few challenges. First, if I use a best fit line and try to use it for prediction in classification data. So if I take this point, if I touch it here on the line, and if I touch it here, I would be getting a number like this, which won't make sense. So if I provide this number to the algorithm, and if it gives me back this number, this output, so it won't make sense to me in classification. So we solved that by using this decision boundary. We made a 0.5 cutoff line. We touched it here on the best fit line, and wherever it touched, wherever it touched that best fit line, from that point onwards, we have made this straight line, which was our decision boundary, which is a separation boundary. So that was like a cutoff value we have found out, okay, which was this number, for example. So we found out that 155 is, let's say, a cutoff value found using the decision boundary that we have made. Now, I do not need to use the regression line. I can just use this 155 as a cutoff and I can use that. So now any input value, any person whose sugar level I am collecting, I will just see, is it on the right side of, is it on the higher side of this cutoff, or is it on the lower side of this cutoff? Means if for this I have to predict whether it will be this person is diabetic or not. So I'll take this blood sugar level and I will compare this with the cutoff. If this number is higher than the cutoff, so we will predict it to be yes. And if it is lesser than the cutoff, we'll predict it to be no. But there is a small problem with that. If there is an outlier in your data point, then your best fit line will shift towards that and your decision boundary will also shift. If you want to solve that, you said let's remove the outlier. Okay. So we can do that. But even if we do that, and if we use this decision boundary, one small problem here is that if you just get any input which is just on the higher side of the cutoff, means at the boundary, so we can't say that this person is definitely diabetic. It is not very correct to say that. So here what we do in logistic regression, we are going to attach a probability with this output. Means if this is a person who is having a sugar level more than the cutoff, but it is not that much more that we can confidently say that this person will be diabetic. It's just on the boundary. So we will give a cutoff, let's say, yes, this person is diabetic, but I'm attaching a probability with that so that I can decide further if we need to do any further checkups to predict this person as diabetic or not. Okay. So that is what we will be talking about. Logistic regression is going to give us the probability that the person is diabetic given the input, given their medical condition, or in simple words, in logistic regression, we get the probability of output being yes given the input values. Okay. So it always give you the output being yes given the input values. Now let's see how are we going to achieve this probability thing. For that, we use sigmoid function to fulfill the above requirements. Means whatever are our main requirements in the logistic regression in this classification data. So to fulfill those requirements, to be able to get these type of probability related values, we have a sigmoid function in mathematics which has this particular formula, which we will understand about this formula. So the formula is gz is equal to 1 upon 1 plus e to the power minus z. Now, like in linear regression, we have used one equation which was y is equal to mx plus c from mathematics. Okay, for linear regression, we have used this equation y is equal to mx plus c to write the equation of the best fit line. So this is an equation from mathematics. Same way, in mathematics, there is an equation called a sigmoid function. It's an equation, it's a formula. And the formula is this. Gz is equal to 1 upon 1 plus e to the power minus z. The property of this formula is that it gives you an output between 0 to 1. Okay. Whatever input you provided, it will give you the output between 0 to 1. Now, when it provides the output between 0 to 1, so that output can be treated as probability because probability also is between 0 to 1. Okay. So it gives us a value between 0 to 1 and output between 0 to 1, which we can interpret as probability. That is what I'm going to explain to you. So let's see what we have been talking about. So we saw that if you use linear regression, in linear regression, you have an equation of best fit line, which is this kind of equation, y is equal to mx plus c. The property of this equation is that it gives us the output between minus infinity to plus infinity. Right? The property of this linear regression equation is that, or the best fit line equation is that, if you give any input to this equation, it will give you the output between minus infinity to plus infinity. Means it can give you any negative number or any positive number as the output. Right, that is the main property of this type of this equation. Its output can be any negative or any positive number. There is no limit on the range. Because of this, it is not suitable for classification. Because in classification, we are expecting a very limited outcome, which is 0 or 1. Right. So in regression, we were not expecting any particular value. It was the prices or profit of the company, sales value of the company that can be negative, positive, any number it can be. Okay. So there, uh, in regression, we have such a data whose output can be any number, any negative, any positive. So there, this equation seems best because it gives you any kind of output, any number as an output that we were expecting. But in classification, we won't use that. It is not suitable. So what we should use in logistic, what you should be using in classification. So for logistic regression algorithm, we will use another formula which is known as sigmoid function. Sigmoid function is also known as logit function. From this, the name comes logistic from this logit function that you see. Okay, so we have this formula here, gz is equal to 1 upon 1 plus e to the power minus z. This formula has a property that it provides the output between 0 to 1. Right. So any person's medical conditions you provide to this equation, it will tell you an output between 0 to 1. And because it does that, you can treat that number as a probability, that output as a probability. So this is the starting idea, what we are going to do and which equation is going to help us in that. So now let's get into the proper mathematical understanding with the examples and uh, all the diagrams and everything that will help us to understand this. So what we do in any algorithm when we have to use that, we follow this kind of approach that we have a training data, which is 80% of our data set, training data set, and 20% we keep for testing. So we have a training data that we provide to algorithm. Now algorithm has a equation, has a formula in it, and through that it will be making for you the ML model. Like ML model in linear regression was the equation of the line, which was y is equal to mx plus c or m1x1, m2x2, m3x3 plus c. That kind of equation we were getting, that is our ML model. So best fit line that we get is our ML model whose equation is represented like that. Correct. Same thing we will do here also. We will provide a training data and we will be training a model. So let's see what happens in this logistic regression. Let me make a page. Okay, see. So the general idea is when we take a training data, and this is a training data of classification, means it is related to that kind of data where output is in the form of categories, yes, no kind of thing we have. So what we will do in logistic regression, we will first provide the training data to this equation, which is the equation of a line that we have used in linear regression. Okay, so in logistic regression also what we do, we take a training data and we provide the training data to a equation of a line, which is this particular formula. Now this will provide us a number between minus infinity to plus infinity. Okay, so suppose I have given the heart disease uh, related data set in this training data, right? Now, given this data set to this equation, what we will create this kind of final equation like y is equal to 1.12x plus 0.89. Okay, so on the basis of the heart disease data set, we have 100 people, 200 people in our data set, 100 rows, 200 rows we have in our data set. Okay, and see, this is a data of heart disease, means output is yes, no, means a person has heart disease, does not have heart disease, that kind of thing we have. So I'm saying that a data which is of classification, if I'm working with logistic regression algorithm, I will provide that training data first to this equation, which we have used in linear regression. And we will get this kind of equation, right? We will get this kind of equation made. Now we will put this equation, correct? We will put this equation into this. What we will do now, we won't use this equation for the final prediction purpose. What we will do now, we will take this equation and we will store it into another variable, say z. Okay, so this equation is going to give you the y value, which is the output. But we are not going to use that output as the final output. What we will do now, I will store that output into another variable, say z. And then whatever is that output, I am going to provide that to 1 plus e to the power minus z. So whatever output is given by this particular equation, so that I am going to provide to another equation. Okay, and then we get the final answer. So what you need to understand here that in logistic regression, we use two different equations together to get the output. First, a linear regression equation, a line equation, and then the sigmoid function we will use, and then we will get the final answer. Why, how, we will understand about that. But I'm giving you an initial idea for now. This is what we are going to do. We are going to use two different equations, right? We are going to use two different equations in the logistic regression algorithm. See, so let's understand how that is going to be done. So I have a training data here, which is related to heart disease predictions. Okay, and how will that data look like? Let me show to you. Okay, see. So look at this set of columns that we have here. See, so we have multiple columns given to us, and this is the data set related to heart disease patients or the people who came for the checkup of heart disease. In this data, you see the target column, the last column. Just a minute. You see this target column, it has 111 written. And then if you scroll at the bottom, you will see somewhere 000 written. So 0 means this person did not have heart disease in the past. And 1 means this person with all these medical conditions had heart disease in the past. Okay, so what we will do now on the basis of this data, we will provide this data set to the equations, and those equations will learn the pattern, and the final equation will come out. Okay, so here what you notice in the output column, we have categories 1 and 0. Two set of outputs are there, 1 and 0. Now, so this is our training data of heart disease prediction. This is our training data, and we provide it to regression line. Regression line, when it sees that particular data set, it creates this type of equation. So you know that whenever you provide a data to the regression line, to this equation of a line, it will create this kind of best fit line equation for you. Correct, because whenever you provide a data to a regression line, it will try to create a best fit line for us. So let us say this is your best fit line that has been created on the basis of this training data, right? On the basis of this training data, we have found this equation. So we have got this equation now. So the problem is, if I use this equation for prediction purpose, we are not going to get the right answer or the answer that we expect or the output that we expect. So once I have given this training data to this regression line and I got this equation, so according to linear regression, our training is done, because in the linear regression, getting this output, getting this equation is our training process. Once we get this equation, this best fit line equation, training is completed. Now, if I try to use this to get the output in classification, see what will happen. So now we have, suppose, our first training row, and we provided that to this equation. Say chest pain level is 4. Let's say column number 2 is cholesterol level, whose value is, let's say, 35.8. X3 is blood pressure, and its value is, let's say, 110.5. So we have one row. In that row, these 4 values are there. Okay. Now, if you provide this first training row to this, okay, suppose if you provide this first training row to this equation, then what will it uh, provide as an output is this 14.2. Okay, it will provide this 14.2, this kind of output. So let's understand what I'm trying to say with this example here. Now see, so I have my training data and I provided it to the regression. Now it created this equation for us. So I'm saying, suppose it created this equation for us. Right. Suppose it created this equation for us, because whenever you provide a data to this regression, it will create this equation. So by saying that it will create this equation, what do I mean? I mean that we are doing this. You see, I mean that this was our classification data, the graph that I've made. So these points and these points are of classification. Now I'm saying that I provided this data to linear regression and it made this line, this best fit line that we were talking about, it made this line. So I'm doing this as of now. I'm taking the data and I'm applying the linear regression algorithm on that data. Our data is of classification, but I'm saying that on that data, we are applying the best fit line, correct? And because I'm applying this equation, this regression equation on our data, so it will give this kind of equation, it will be making a best fit line in that. But we can't stop here. Okay, we can't stop here because what kind of output it will be learning? It will be learning this kind of output, which is like 42.8 or 11.3 or 3.76. It will learn these kind of outputs, which means, let me show you with the data set, which means that it is going to be something like this. Here it will be better to understand. Yes. So I'm saying that if you provide this training data to linear regression, we have got that line. So what it is learning, it was supposed to learn this. Okay, the algorithm or the equation I am going to use in classification is supposed to learn these values, 1 or 0, right? But if I give this data to the linear regression, my training data to linear regression, for these outputs, what it will exactly learn? So it will not learn the output to be 1. What it will learn? For 1.0, it will learn something like 11.3. Or for this one, it will learn 42.8. Or for this one, it will learn 7.5. Okay, so I am saying that if you provide this data to the linear regression, so linear regression can't learn one zeros. You know that it has a property that whatever it will learn will be this kind of output. Okay, why? The last question concept was entirely about it. Look at it. Okay, look at it. This is your house price prediction data set in which your output column is this. Correct? You see, right? So here we have this is our house price prediction data set in which you see the output column is this, which is having all these numbers 24, 21.6, 34.7. We have all these things. Now, if I provide this equation, this data set to linear regression, what are we trying to do? Means if I provide this data set to linear regression, so what they will learn, what I'm teaching to them. So suppose my first output is 24. So I'm trying to teach the best fit line, this number 24. But what will it learn? It might learn, let's say 23.6. Why? Because you see, your actual values are these, right? Your actual values are these, and your best fit line, from where it will pass from the middle. So let's say row, your first row is represented by this data point. Okay, in regression, say your first row is this one, which is, let's say, this data point. Okay, now what is the actual output of this? Say 24. Okay, say that this is your first row whose actual output is what, how much? Actual price is how much? 24. What is your best fit line learning for that particular data? This much with an error, right? So let's say it has learned 23.6 where it should have learned 24. Right, that is what we were talking about as the error. When we make the best fit line, where are you applying the best fit line? On the training data. Okay, you apply the best fit line for learning the pattern on a training data. What was our training data like in the regression? So it was this kind of output. So we are trying to teach the best fit line this number, this output, which is 24. But will it learn that exact output? No, it will learn that with some error, which is basically this number 23.6. Then say second row I take, second row, and this is the data point for second row, whose actual value is 21.6. Is the line learning exactly same value? No, it is learning a little bit different value, say 22.8. Okay, are you getting the point? How the training is done? In the training, you are trying to teach these numbers to your best fit line. But will it learn exactly those numbers? No, it does not learn exactly those numbers. It tries to learn something very close to that, as close to these numbers as possible. But what they will learn another number which is very close to these actual. Means uh, if you say that it should learn all this, it means that you are passing your line through each data point. Correct? If I say that my line is learning exactly these outputs as it is, so can I say it must be passing through all these dots? It must be touching all these dots? Correct. So in the training, our best fit line does not pass or does not pass through each and every data point. It passes close to them, which means that if you have this point, right, it means that if you take this point, so this is one row, this is one training data, this is one training row. A dot in this graph represents what? This represents one training row, one training row. Correct. And how did you make this dot? This dot is made using the input column, and you see on the y-axis we have its actual price. This is its actual price. But is my best fit line learning the actual price of this house? No, it is learning another number which is with distance. Correct? So we are learning this number for this particular house, where actual price is this much and we are learning this much. Correct. So when we do the training in the linear regression, so in linear regression, we are trying to learn the outputs, which are these outputs. But can we learn those exact outputs? No. Right? We can't learn those exact outputs. We will learn that with this much of error. Correct? Now, whatever amount of error we are doing in the training process, can we say that much error we will make while doing the prediction for these test values also? Okay, can we say whatever amount of error we are making in training process, that much error overall we will make in the testing process also, right? So that is the thing. So why we were predicting the closer number, why not we were predicting the exact same number? Because while training, while we were learning from the training data set, there also we did not remember the exact number. We are learning a number as close to that as possible, right? We are learning a number which is as close to the actual output as possible, but we never learn the exact output, which is 24. We Our best fit line tries to learn a number which is close to that, right? So it tries to learn these outputs, but they will not learn the exact output. It will learn it will learn a number as close to that as possible, right? because when it is making a best fit line, it is not touching each and every point. It is passing as close to all the data points as possible. Now, what I'm saying is this. If I provide this data set to the linear regression line, right? If I provide this data set, if I provide, let's say, all this to the linear regression line, where linear regression line is supposed to learn this output, 1. Can it learn this output, which is 1? No. It will learn this kind of numbers like 11.3 or 7.5 because it has been designed to learn this kind of numbers. It has not been designed to learn 1 or 0. Right? It is not designed to learn 1 or 0. It will learn this type of numbers. Correct? Now, we wanted, yes, because of the straight line property of the linear regression, right? It can't learn these numbers like 1, 0. So if I provide this data, to linear regression, I want the linear regression to learn these outputs 1 0 1 1 1 0 0 like that. I want it to learn these outputs, but can it learn those outputs? No. It will try to learn a number which is related to 1. Correct, which is related to 1. But can you use this for prediction? If you try to use this for prediction on the testing data, see what will happen. Okay, so what we have done, I have given this data to linear regression. And when I have given this data to linear regression, it was supposed to learn these kind of outputs for these inputs. But what it is learning, it is learning the outputs like 11.3, 7.5, 3.28, that kind of outputs it is learning. Now, if you use that line, for testing data prediction, can I say that if I provide my first testing row to that line, and it should have predicted 1, but it will predict something like 27.4? Can I say if I use this line on the testing data, so it should have predicted 1, but it will predict this kind of number, which is 27.4 or 5.89, something like that it will predict? Correct. Now, can I compare these two to find out whether my prediction is right or wrong? Can you compare 27.4 with this 1 to say that whether your predictions are correct or not? No, because this is a category and this is a continuous value that your line has predicted. You can't compare these two numbers at this point to find out whether your model has been made accurate or not. Correct. Now, what would you want to do instead of these? So can I say whatever output I have got here, which is 11.3, whatever this number has been learned by the linear regression line for this training data, can I say I would want to convert this number in another range which is closer to 0 or 1? That will make sense. So you see what I'm saying now. Let's provide this output into this equation, which is gz is equal to 1 upon 1 plus e to the power minus z. I'm saying that this number, which is this output, which is being learned by the regression line, is not suitable for us because we are supposed to learn this number 1, but we are learning this kind of continuous values, which is the property of regression line. So I'm saying that let's take this output and let's not use it. Let's give it to another equation now, a second equation now, which is gz is equal to 1 upon e to the power minus z. What is z here? Z is this output, 11.3. So I will take this and I will provide 1 upon 1 plus e to the power minus 11.3. Now what this function will do, what this equation will do when I provide this 11.3 into this, it will convert that between 0 to 1. So now suppose it has converted this into 0.97. When I provide this 11.3 into this equation, it gave me 0.97, for example. Okay, it gave me, for example, let's just say it gave me 0.97 as an output. So what we are doing now, we converted this 11.3 to 0.97. Okay, we converted this into another number now, 0.97. Is that output which you are learning, is that useful for us? Can you make sense of this number? So we are supposed to learn 1. If I use the regression line, I was able to learn this number 11.3, but this does not make sense to us. So I converted that output into another output, okay, which is a number between 0 to 1. So we are supposed to learn 1 and I'm learning 0.97 using the sigmoid function. So what does that 0.97 mean? Can I say 0.97 mean that the actual output is 1 and I'm saying that this person has 97% probability of being a heart disease patient? Right. Can I say that this is the person who has heart disease? One means a person who has heart disease, 0 means no heart disease. Okay, so this is a person who actually has heart disease. And what are you learning about this person? What is your model learning about this person? A probability 0.97. Okay, we are learning that this person has heart disease with a probability of 0.97. Will that make sense for you? We can say yes, that makes sense for me, because we are supposed to learn 1, but I'm learning the probability of getting this 1 using the logistic regression. Now, if I use this thing for the output, can I say we can convert this 27.4 also to, let's say, 99 or 0.993, something like that? So we had to predict 1, but we have predicted 0.993. Is that somehow usable for us? So I can say that the person had uh, the person was supposed to be a heart disease patient. And what I'm predicting? I'm predicting that this person is going to have heart disease or has heart disease. That I'm saying with 99.3% probability. So does that make sense in some way? Yes. To some extent, it is making sense. But now, can I convert this number into 1 or 0? Is it possible to convert this probability into 1 or 0? So that becomes even more easy for me to compare that. Can I now bring a cutoff of, let's say, 0.5, right? And we can say that if this number that we have learned for this, if this number is more than 0.5, we will convert it to 1. Okay. And if this number is less than 0.5, we will convert that to 0. Okay. So now can we do this one final thing, that we converted from this to this probability. And if the probability of this person being a heart disease patient is more than 50%, we will say that this person is a heart disease patient. We will convert that to 1. Same thing can we do for this also? It is 0.993, 99.3, which is much higher than 0.5. It is greater than that. Can we then convert it to 1? Yes. Now can I compare this output with this actual output? This is my predicted output and this output. Am I now able to compare that? Yes. We are now able to compare that. Perfect. Yes. See, this number can be negative. When we are having 1 and we are learning this number using the regression equation, that can be negative. In what case will it be negative? You see, when you have output which is 0, okay, suppose if your training data has that row where the output is 0. If I provide this training row to the linear regression equation, it might learn like minus 4.37 for this row where actual output is 0, but my linear regression is learning minus 4.37 for that. Now, when I provide this minus 4.37 into this equation of 1 plus e to the power minus z, that will turn into what? It will turn into 0 to 1. So the linear regression, whatever output it is learning, that can be negative, but when we convert into the sigmoid function, then it will be between 0 to 1. Not ever less than 0, not more than 1, between 0 to 1. So this minus 4.37 will get converted into something like 0.023, for example. Now, our actual output is 0. And what we have learned, the number that we have learned using this regression and the sigmoid function combined together, 0.023. What am I learning here with this number? We are saying that this person, right, this person has 0.03% chances of being a heart disease patient. Can I say that is correct according to my actual output? So this person I know is not a heart disease patient because its output is actually 0. So I know that this person is not a heart disease patient. It is for sure. And what is the thing that I'm learning about this person? That this person has 0.0023% probability of, or if I have got this number, so if I multiply it with 0, so it will move here and it will become 0.23. So can I say if a person, the actual output is 0, means this person is definitely a non-heart disease person, healthy person. And what I'm saying that this person has 0.23% probability of being a heart disease person. So can I say I'm learning the right thing? Yes. Now I can compare that, right? I can compare that with the cutoff. Okay, I can compare that with the cutoff, which is 50%. So this was 0.23% compared with the 50% that is less than that. Okay, so it will get converted into, so it gets converted into 0.23 and sorry, it gets converted into 0.023 and that gets converted into 0. So what is the difference in the training process of linear regression and logistic regression? I hope you are getting the point. So what we are doing now in this case, we are using two different equations to make this kind of learning, to do this kind of learning. Okay. Now, if you have this data set, right? Let's say if you have this data set and from this data set, we are saying, let's say this much part is my testing data and this much part is my training data. Okay, above this line, this is my training data. Now understand one last time the difference between linear regression and logistic regression, their learnings. So if I suppose take this data and I provide it to linear regression, what does linear regression try to do? It tries to make a best fit line. Okay, if I provide this training data to linear regression, it tries to make a best fit line. Okay, now what is the best fit line trying to do? Best fit line is trying to learn the outputs, these type of outputs. But you know the property of best fit line is that it learns the output which is a continuous number. It does not learn 1 or 0. It learns any number, a decimal type of number, which can be any negative number or any positive number. So what it will try to learn from them, when you provide this data to the best fit line, it will learn that this is the first output. Okay, this is my first training data and whose actual output is 1. So what it will learn? It will learn suppose 11.37. Now, if you were working with the regression data, you would have stopped here. But in classification, you are not going to stop here. Okay, in classification, you are not going to stop here. Why? Because you were supposed to learn this in this classification and you have applied the best fit line which learn this number for this output. Okay. Now we can't stop here. So what I did, whatever output I have got from this best fit line, whatever learning I have got from the best fit line about this first testing data, I give it to sigmoid function. Sigmoid function takes this 11.37, converts that into 1 plus e to the power minus 11.37. It converts that. So what happens? It gets converted into a number, let's say 0.97. Right? Now you see this number is making sense compared to actual output. So we are supposed to learn this one, but using this best fit line, we learn this, okay, 11.37. And as I provided this to another equation, which is sigmoid function, I got this number between 0 to 1. And this is 0.97. What is this? What is the probability given by the sigmoid function? Remember that it is the probability of 1. Okay, sigmoid function always gives you the probability of achieving yes, or the probability of the output being yes or 1. Remember this thing. So what is this 0.97 telling you? That we have learned that, right? We have learned that this person who is actually a heart disease patient, because you see, one means this person is actually a heart disease patient. What are we learning about this person using this uh, sigmoid function? We are learning that this person has 97% probability of being a heart disease patient. So can we say we are learning the right thing? Okay, when this person is actually a heart disease patient, we are learning that this person has 97% probability of being a heart disease patient. So can I say we are very close to that? Actually is 100% sure that this person is a heart disease patient. I am saying that we are 97% sure that this person is heart disease patient. Now here, instead of comparing these two things, you do what? You do one final thing, which is you take a cutoff number, which is 0.5, and you say that if this probability is more than 0.5, you convert that to 1. And if this probability is less than 0.5, you convert it to 0. Correct? So what we did, one last thing that we did is we converted that to 1. Now, can I compare my learning, whether it has been done right or wrong? Yes. Makes sense? That what we are trying to learn and what we are getting out of this? Yes. So now you see, in linear regression, we would have stopped here. In linear regression, we would have stopped here. And in logistic regression, we are doing two more things. Okay. Now, remember that or understand this point. Your logistic regression will also stop here. When it gives you this probability, it stops here. This comparison part that we do is an extra thing. It is not the part of logistic regression. It's an extra thing that we are doing. The output which is given by the logistic regression is this probability. And you see, can we say that this is a continuous number like what we were getting in logistic regression? It's a continuous number, it's not a category. So because logistic regression also gives us this kind of continuous number, it does not give us 1 or 0 as a final output. That is why it has a regression in its name. Okay, so it is not giving this kind of continuous number, but still if you look at this number, this is also a continuous number. It is not 1 or 0 like yes or no. So because the logistic regression's final output is also this kind of number, this kind of decimal numbers, that's why logistic regression has regression in its name. Now you see what I'm trying to tell you. You are getting this probability as the output. So now, can we say that we are getting a benefit using logistic regression? What kind of benefit? So I converted this person to 1 by comparing it with cutoff. But can I say I'm getting two answers, that this person is a heart disease patient with 97% probability? We are saying that. Can I say two things, two information we are getting? Right. Is it correct to say we are getting both the information, the probability also and the actual output also? So we are saying that this person is a heart disease patient with 97% probability. Correct. That is the difference between linear and logistic, we are saying. Okay, so we are converting that to 1 or 0, but we had achieved a probability related to that, which we converted to 1 or 0. Right? Now, so this is the idea about the logistic regression, and let me summarize that for you. Okay. So what happens? when we do the training process, how your model will be created. Understand this diagram, you will understand what we have discussed. So we have a training data, which is a classification training data. And we are giving it to regression line. I'm giving my classification training data to a regression line, which makes this kind of equation. Now, whatever output is being learned by this equation, like 11.37, I'm saying that let's store into a variable z. Okay, for example, z is equal to 11.37. This is what we have learned for the first training row. We have, let's say, 80 training rows. So we have learned this number for the first training row, 11.37. But see, this number does not make sense to us. So what I do not stop here. I provide the output of this equation, the learning of this equation, to another equation, which is gz is equal to 1 upon 1 plus e to the power minus z. Now, what is z here? Z is coming from this. So we take that 11.37 and we provide to this equation now 1 upon 1 plus e to the power minus 37. Yes, e, I am explaining. E is basically a Euler's number. It's a Euler's number. It's a constant which has a value of 2.71. Like we have a gravitational concept. So you must have seen that gravity has, you can say 9.8 milli meter per second square, and then, or its value is 10 meter per second square, right? So yes, it's a constant value whose number is fixed. Meter per second, I think, yes. Right. So it's a constant number, its value does not change. So in this entire equation, you see, the only thing which is variable is this z. Okay, yes. So like you see, one is fixed, this one is fixed, and this e is fixed. These three numbers are fixed. These three things are fixed. E has a fixed number of 2.71. The only variable part, only changing part in this entire equation is z value. So from where the z value is coming? From the previous equation. So what we will do, for if suppose we have 80 training rows, we have suppose 80 training rows in my training data. So for each training row, we are going to first learn output using this equation, which will be like this kind of number. Then for each training row, we will provide its value into this sigmoid function, and it will get converted to a number between 0 to 1. So let's say this number got converted to 0.97, right? So this is the output we receive from the logistic regression. This is the output we receive when we use linear regression. Okay, so you see this kind of output we receive in the linear regression, and we are just converting that with another equation to this kind of number, which is we are transforming that to a number between 0 to 1, so that I can treat it as a probability. Now what I do one final thing, which is compare. Okay, now this comparison part is not the logistic regression thing. It's an extra code that we write ourselves. So here we say that we have a cutoff of 0.5. 0.5 means 50% probability is our cutoff. We are saying that if the number is more than 0.5, which is here, so we will convert it to 1. And if this probability is less than 0.5, let's say 0.23, so we will convert that to 0. Right? Yes. The cutoff is 0.5, which is the fixed cutoff that we can say. Now, can I change my cutoff? If I want, is it possible to change this cutoff number? What do you think? Because you see, this is not the part of the algorithm. This is not fixed in the linear regression, logistic regression algorithm. I'm saying that it's a number which is commonly used, 0.5. So is it possible that I change it? I can change it. Yes, it is possible. I can make it 0.7 also. It's possible. Right? Depending upon the scenario that I'm working in, if I want to change it, I can increase or decrease this cutoff also. Generally, we increase. In some cases, we don't decrease. Okay. So 0.5 is the most common used cutoff. Generally, people do not change, but in some scenarios, we can even change that. Okay. Now, you see. So what we have understood now, are you getting the idea about this entire process? Through that data set also I explained the same thing, and through this also I hope you are getting the idea. What is happening? Your training data is going through two equations, the regression equation and then this sigmoid function. So basically you are applying two formulas on your training data set, and then it is learning this kind of probabilities, right? And then you convert that into 0 or 1. That's an extra thing, because but you are learning this kind of probability. Okay, so now I hope you are clear about this also, that why do we call logistic regression as regression? Even though it is a classification algorithm, why does it have regression in its name? That also you should be clear, because logistic regression is not learning 1 or 0. It is actually learning this number, which is a continuous number. Okay, if any algorithm learns a continuous number like this as an output, so that is regression thing. It's a property of a regression algorithm, right? We are converting that to 1 or 0. That's an extra thing we are doing. But the actual output of logistic regression is this kind of continuous number, like this decimal number. Okay, it is not a category, it's a continuous number. That is why it has regression in its name. Correct. So you can see that the logistic regression is nothing but it's an extension of linear regression. In simple words, you can say that logistic regression is nothing but it's an extension of linear regression that we have studied. Correct. Now, can I say it like this? I have used two equations here, m1x1 plus m2x2 plus m3x3 plus c. Then we use this equation. I put this output into another variable, say z, and then I'm saying gz is equal to 1 upon 1 plus e to the power minus z. These two equations we are using in logistic regression. Can I combine both of them to write it as one? So can I write it as gz is equal to 1 upon 1 plus e to the power minus, instead of writing z, can I write this equation directly here? Minus m1x1 plus m2x2 plus m3x3 plus c. Because z is coming from which? Z is basically coming from this entire equation. So I can just replace the z and I can write one equation overall for the logistic regression. Yes. So what I did, I just combined both of these equations and I have written that as one. So this is the final form of your equation in logistic regression, which is like this. Okay. Now, you see, what exactly are you supposed to learn in this equation? When we were talking about linear regression, we said that in the training process, we are trying to learn M1, M2, M3, and C values, right? So when we learn those M1, M2, and C values, we get our best fit line basically. That is our training process. What are we going to learn in the training process for this equation, related to this equation? Can I say here also we need to learn the values of M1, M2, M3, and C? Okay, can I say we have to learn a suitable value of M1, M2, M3, and C here also in logistic regression? Because everything else is known. This one is known, this is fixed, this is fixed. Can I say only variable components in this equation are M1, M2, and C? Why am I saying? Because when you have the proper values of M1, M2, M3, and C, then you will predict the correct number, let's say 11.37, that got converted into proper probability. If suppose this number is not predicted correctly, can you predict this probability correctly? If suppose this is not predicted correctly, can you predict your probability correctly? No. From where this value will come? From this equation. So can I say that we have to learn M1, M2, M3 and C values in logistic regression also, so that this output comes right? If this output comes right, it will be automatically converted to a correct probability. Right? I hope you're getting the point. So here also we need to learn in the training process the perfect values of M1, M2, M3 and C, so that using which I can predict this correctly. And if this is predicted correctly, then our probability will also be predicted as close to the actual output. But as an idea, what are we going to learn in the logistic regression? The values of M1, M2, M3 and C here also, like linear regression. Okay, so the main difference between the equations of linear and logistic is in linear, our final equation would have been this. This would have been my final equation in linear regression, and this is my final equation in logistic. Small difference in that because it's a combination of two different equations. Okay, let's understand what we are talking about. So let's say first, I'm just going to repeat one point which I have already discussed with you, but just for the clarity purpose, I'm repeating that one part and once again. So suppose we have the house price prediction data. In this house price prediction data, we have 0, 1, 2, 3, 4, 5, 6. Multiple rows are there. Okay. And what is the output? So we have 1 is the number of rooms, then 1 is the number of floors, and 1 is the area. Right. Say we have 3 input column, and then we have this price. Price is the output column. And when you do this, correct. So this is our house price prediction data set, which is a regression data set. And we have these rows. Now say I divide this into two parts, my training data and testing data. So these 4 rows, I'm saying this is my training data. And these 2 rows, I'm saying it is my testing data. Okay. Now, if you make a plot here, if you make a plot to visualize that. So what we do when we make this kind of graph, whose graph am I making here? Am I making a graph of the training data or my testing data? Means when we talk about this graph of these type of dots, do we make this graph of the training data or the testing data? Or do we make it of the entire data? This graph we were making always of the training data. Okay, so when I have to make a best fit line, on which data do we make a best fit line? On our training data. Because creation of best fit line means that you are doing a training. So remember, whenever I show you this type of dots in the linear regression, these dots are our training rows. So if you have 4 rows in your training data, you will have 4 dots. Correct. This will give you 100% clarity on everything just in few minutes. What I'm going to explain you now. So this is my training data set. And what I'm showing you here, these 5 rows. First 5, 0 to 4, 5 rows are there. So you'll have these 5 dots, something like this. Say. So I have just visualized my training data, and the graph of my training data looks like this. Each dot is representing a training row. On x-axis, you have input, and on y-axis, you have the output. Okay, so in simple words, understand that on x-axis, we have the input, and on y-axis, we have the output. Right. So what you have on output is, this is a house, this dot is a house whose actual price is this. This is a house whose actual price is this. This is a house whose actual price is this. this is this, and this is this. So all these points on y-axis for these uh, white points, these are your actual prices of these houses. Now, what you need to do, you need to train a machine learning model. You need to apply linear regression to that so that it can learn the overall pattern present in the data. So what does the linear regression do? Linear regression tries to pass a line as close to the data points as possible. Okay. So let's say it makes a line like this. But how do you know that this line is better and this is not better? Means how does the linear regression know that this line is better and this is not better? Through the error concept, right? Whichever line is making least error in the learning process, that is our best fit line. Correct. So you see now, if the price of the houses are, let's say, 80.1 lakh rupees. So I'm using the term lakh. Lakh means, so if I'm saying 80.1 lakh, it means 8.01 million rupees. So whichever term you understand, you can take that. So for now, I'm writing that in Indian terms. So first house has a price of 80.1. Okay, 80.1 lakh rupees. Now here I write, let's say this house has 75.3 lakh rupees. Okay, this has 68.5 lakh rupees. This one has 99.2 lakh rupees and this one has 84.5 lakh rupees. Correct. So just some numbers we have. These are the price of these 5 houses which I have. And I'm using that for training. So what I'm doing now, I'm trying to teach these outputs to my best fit line. My best fit line is supposed to do what? It is trying to learn a relationship between these inputs with these prices. Okay. So how does it try to learn this relationship? By making this best fit line, right? Now, how does the linear regression know which of these two lines, suppose, is the best fit line? How does it know? So you now see here, let's take the first line. Okay, understand it carefully. You take the first line. How do you judge whether it is the best line or not, or can we have another line? See, so your first training row is this. For example, this is your first training row, is your first house in the training data. This one. Its actual price is what? 80.1. Its actual price is this one, 80.1. But is my best fit line learning that same output for this first training row? Is it learning that price exactly for this particular house? No. It is learning this number. You see this number. Okay, which is, let's say, 75.6. It is learning this number 75.6. So you wanted to teach this number, you wanted it to learn this number, this output, but your line is learning this output. Okay, 75.6. Correct? It is learning this output. So here what we have learned through the best fit line, 75.6. What we should have learned is this number. What is our best fit line learning? This number. Can I say the same thing for the second? Let's say your second value is this. You see, second value has this number little bit higher than that. Can I say I'm learning exactly that number for this data point? Can I say I'm learning exactly the same output? Means actual and the learned output is the same number? Yes. So for this one, since my line is passing through that data point, so it has learned the same output for this one. Now I take the third data point. Let's say this is my third data point. Now for this one, the actual price is this much, but the learning value is this much. Actual is lower, but we are learning something high. So actual is this 68.5, but say we are learning 72.8. Correct. So what you understand here, you wanted to teach these outputs, these prices to your best fit line, but does it learn those same values? No. It tries to learn the values as close to actual as possible. Okay. Now, how do you know which line is best? Can I say that I will take two lines and one line has learned this value for this price, okay, and say another one has learned this one 72.5, then this one has learned 61.3, this one has learned say uh, 80.5. So out of these two lines, who is learning the output more accurately, more closely? So can I say our number one is learning the output with lesser errors, means as close to that as possible compared to the second line? Can we say that? Yes. So you can see we were supposed to learn this and our second line is learning this much. Big difference, which means that my line number two is making lot of errors, bigger errors, and it is not close to that. Compared to that, line number one is more close to that. So what we did out of these two lines, we picked this line to be our best fit line. So we won't just compare two lines, we will compare 5, 10, 100, 200 lines like that. And we will see which line is giving me more closer predictions of the actual prices. Correct. So now, once we have decided that we are going to keep this line, which is giving this type of equation, so can I say now we will just convert it into its proper equation format? Y is equal to m1 x1 plus m2 x2. How many input columns are there? Three input columns. So m1 x1 plus m2 x2 plus m3 x3 plus c. So can I say we have found that line number one is best. So line number one will be attached with some numbers here. It will give us these three numbers and say we have found 1.08x1, then 0.97x2, and let's say 0.52x3 and 1.01. Can I say these are the numbers? How did we get these numbers M1, M2, M3, and C? Can we say we got this using the best fit line? So first we decided out of multiple lines which is the best fit line. And on what basis we decided? We saw that we were we were trying to teach these outputs to the line, and this line has learned the outputs as close to actual as possible. Other lines are not learning that much closer, they are making more errors. So on the basis of less errors, we decided this line is best. And then once we decided this line is best, we just saw what is its equation and we have finalized this equation. So we stop here, and this is what we call as our best fit line equation, and our training process stops here. Now, if I use this line for the prediction of these testing outputs, can I say we will be able to do more accurate prediction of the testing using this line compared to any other line equation? Right. Can we say this line will do better predictions, more accurate predictions of the testing value? Yes, because this line has learned the prices close to actual in the training process. So it will predict that also close to actual in the testing process also. In the real world scenario also, it will predict close to actual. Yes. So this is the idea. This is the entire thing about the training process in linear regression. Let us now move on to that classification part. Should I take any other example? Yeah, let's say loan approval. Loan approval model we have to make. Means given the financial details of a person, we have to predict whether this person should be given a loan or not. So same way with this simple data set, with the same way, I am going to explain to you the classification part. And you will see how easily we will be able to switch from linear to logistic in a simple way. So here I'll take the data set for that. We have 0, 1, 2, 3, 4, 5, 6. Now, and the input columns and output column, what will be that? So say we have a data set And here we have one column, which is the salary of the person who is applying for the loan. Okay. Then we have the CIBIL score, the credit score of that person, which is between 0 to 900. The higher, the better. So we have the credit score of that person. And let's say we have age, whether that person is young or old or mid-age. And then we have the output, which is approved or not. Okay, yes. So we can take multiple of the input column, but just for simple understanding, I'm just taking 3 input columns and 1 output column. So output column is approved or not. So other input columns can be, means what type of loan they are asking for. Personal, car loan, home loan, and then for how much amount they are asking the loan for how much tenure, means they are asking the loan for 5 years, 10 years, 20 years, that thing. Do they have any other uh, running loan, right? Then the number of dependents on that person. If that person is earning, how many other people that person has to take care of. So number of dependents on that person. There can be multiple things that you can collect to decide whether a person should be given a loan or not. But what we do in the machine learning, we take a data where these outputs are known. This has already happened. So here also I'm dividing my data into the training and testing. Right, I'm dividing my data into this training and testing. Now understand the main thing. So what I'm saying, here the output is now in the form of yes, no, no, yes, and no. And in the testing data, we have your output as, let's say, yes or no. Okay. So these first five rows are my training data, and the last 2 rows are my testing data. And what we do, we just encode these columns. So yeses becomes ones and nos become zeros. Okay, so yes will become 1, no will become 0. So we have 1 0 0 1 0, something like that. Now what we are doing here? So here we are supposed to learn these yes and nos. How are we going to do that? So I said, you first take your data. I said, you first take your data, plot it. Right, you take your data and plot it. Now, how are you going to plot the data point? Simple. You have salary, CIBIL score, age, all these things. According to that, you plot your data points. Something like this. Okay. Now, what you are doing here are different in classification. So in this case, you are going to give your training data to a regression line first. Correct. You are going to give this data to a regression line. Means you have this type of data, and for explanation purpose, I'll take the same type of data that we were earlier talking about. So what I have in my case, I will have some crosses here. 1, 2, 3, 4. Sorry, 5 points are there. So let's say 3 of them are no and 2 of them are yes. So this is no or 0, and this is yes or 1. Correct. So 3 crosses I have here. Sorry, let's make them little far away. So 3 crosses I have here, and on this line we have 2 crosses. Let's say this and this. Okay, so what you are having here, on x-axis you have your inputs, and on y-axis you have your outputs, which is yes or no, loan approved or not. These are your outputs. So this is a person uh, whose salary, CIBIL score, in age was something. According to that, we have put it here. So this person had this much salary, CIBIL score, age combined together. We are just representing on one axis, let's say. So these are the inputs, and according to that, we found out that this person was given a loan. Okay, so their salary must have been high, their CIBIL score must have been high. That is why they have been given a loan. So we are just shifting this data point onto this line of one because they were predicted to separate the no's and the yeses. Okay, so these are two people who have been approved for the loan in the past, and these are three people who were rejected. Okay, so for simple understanding, let's just assume one input, say salary. Okay, so say salary, or another better term would be to use the CIBIL score. This is more important than salary, you can say. So say CIBIL score, this is your input, and we have the output yes or no. So now we have these five people, and they had a different CIBIL score, starting from 0 and maximum till 900 we go. So this person has a very small CIBIL score, means let's say 250. This person has a credit score of 180. This person has a credit score of just 80. So can I say these people have been rejected because they had very less CIBIL score, credit score? Okay, and the bank thought that it is risky for us to give these people loan because they have bad credit score. And why they were given loan? Because their CIBIL score is very high. Both of them had close to 900 CIBIL score, like 720, 800, 10, like that. So they had high CIBIL score. Now, what I'm going to do now, this five crosses that I've made, this is my training data. Okay, I'm just representing these five training rows here. So this is the visualization of my training data. So what we do in logistic regression, this will make it clear. First thing is we pass a line through this. Okay, first thing is what we do is we pass a best fit line through that. Perfect. Because first we were giving this training data to the regression equation. What does that mean? We are basically applying the best fit line to this. So can I say that first thing that we are learning is we are adjusting the line in such a way that it learns the values for them as close to that as possible. But the idea is, how do you adjust this line to be better? Okay, so say that the C is not 0. What will be C value? See, there is a graph that goes on this side also. So if this number is 0 here, if at this point we have 0, so what we will have in this side, we will have negative values. So it will be minus 0 point something. Okay, it will be a negative number, not 0. Why it is the case? Because when you talk about these type of graph, the actual graph is like this. We have four sections. We always study about this section, this one section, where we have x-axis here, y-axis here. But remember, it is not the only section. We have minus y-axis, we have minus x-axis. So if your best fit line is passing from here, so it will have a positive C value. But if your best fit line is passing from here, it will have a negative C value. Right? So it is not 0. It can have a negative C value also if it is below this. Right? That is the thing. So it is not 0. C has a negative. Correct. So now we have this best fit line which is passing. So can I say we are adjusting this M1 x1 plus M2 x2 plus M3 x3 plus C? So let's understand what we have done in the logistic regression. Can I say here also multiple lines are possible? Like if I take two examples, I have this one line which is passing from somewhere here. And let's say I have one another line which is passing from somewhere here. Correct. Two lines passing from two different places. Now, which line is passing closer to the data points, which is trying to learn the data properly? The green one. Because green one is passing closer to the data points through the data points. So the green one is such a regression line which is trying to learn the classification data properly. But the red one is not learning it properly. So can I say that out of these two lines, we are deciding which line is better out of these two? Yes. Okay. So we can have two different equations if I say line number 1, if I say we have line number 1 which has this equation, suppose y is equal to 1.03x1 plus 0.32x2 plus 0.21x3 plus minus 1.2. Okay, so you see the green one has, let's say, this equation, and green one has a C value of negative. So I've written that negative. Now I have line 2, which is in red color. Okay, this also has this equation, y is equal to say 0.81x1 plus 0.57x2, then 0.63x3 plus 0. Because you see it is passing exactly from the origin point. So here I can say C value 0. So it is like that. Now, can we say in logistic regression also we first decide which one of these two equations is better? Means we are deciding on whether these m values is better or whether these m values is better. Can I say that that is also, that is one thing we are doing in the classification also, in logistic regression also? Is it correct to say that in logistic regression one of the things we were learning? Now, you see, why am I saying we have to pick one of these lines in the in this classification? Because see, now we can have two different equations. So one, we can have gz is equal to, right, we can have gz is equal to 1 upon e 1 plus e to the power minus line 1. Okay, you can say line number 1. And then we can have another equation, gz is equal to 1 upon 1 plus e to the power line number 2. So can I say the probabilities that we predict depends upon this equation of the line? The probabilities that we predict definitely depends upon the output given by the line. So if my line is not good, my output given by the line will not be good. And if the output given by the line is not good, then the probability will not be correct. Okay, so let's understand what I'm saying. So we are supposed to learn these numbers 1, 0, 0, 1, 0. That is what we are supposed to learn. But what we do in classification, first we provide this training data to a regression line. And what it will do, so suppose there are two regression lines. Let me make it short. Approved. Okay, let me make this short. So suppose we have line number 1, which learn these type of probabilities, say 11.37, then minus 4.21, then minus 17.35, and then 42.51, and then let's say minus 5.8. So given this training rows, what my line number 1 has learned, these numbers. Okay, and what my line number 2 has learned here, it did learn these numbers, let's say 2.58. Okay, and then uh, for 0 it did learn uh, minus 0.23, and then for it learned, let's say, minus 11.56, and it did learn this, say, 25.51, and it did learn for this, let's say, minus 9.6. Right. So when you provide this data to the regression equation, they will learn these type of values where they were supposed to learn these. Okay, they are going to learn these type of values where they were supposed to learn this. So now how do we decide whether this line is better or this line is better? How do we decide that? So what I do now, I take both of these numbers, this number and this number, and I put it into this equation, 1 upon 1 plus e to the power minus 11.37. And I got how much? Let's say 0. 0.99. And then I put 1 upon 1 plus e to the power minus 2.58 and I got 0.87. Okay, so I took both of these numbers 11.37, 2.58 and I got 0.99 as the probability for this and 0.87 as the probability for this. Now, out of these two lines, which one do you think is helping us to predict the correct probability? Given that your first one is having the actual output is 1. Okay, your first training row has actual output of 1. So which is predicting this number more accurately? The first line, because it is predicting a number very close to 1. Okay, so we are not able to learn exactly 1, but we are able to learn a probability very close to 1, which is 0.99. Okay, so I'm saying that there are two lines. One line is saying that this person has 99% chances of getting a loan. So I know that this person already has got loan. Okay, this person has already got loan. And what is my regression line learning? And then what is the probability I'm able to predict for that? That this person has 99% probability of getting a loan. That is correct because this person has gotten a loan and our line 1 is saying that this person has 99% chances of getting a loan, which means it is predicting very correctly, as correct as possible. And the line number 2 is saying that this person has 80% probability of getting a loan. So this one is not that much accurate, right? So how do you decide this equation of whether the line 1 is better or the line 2 is better? You decide that on the basis of the number. When you convert that to probability, which is giving you the probability more closer to actual numbers. Okay, so what should happen? So this one, if you notice, let's talk about this one, third one, where we have the answer 0. Okay, we have the actual output 0 and we are getting minus 17.35 and here minus 11.56. So when you take the negative values and if you give it to the sigmoid function, so you have 1 upon 1 plus e to the power minus 17.35. So it will become plus 17.35. Minus will become plus 17.35. So what will happen? If this is in plus, then you are going to get 0.00023. And if you take 1 upon 1 plus e to the power minus 11.56. So minus plus 11.56. And this is giving you suppose 0.056. So when my actual output was 0, which line is giving me a better answer? So line 1 gave me minus 17.35, that got converted to 0.00023 and the output given by the line 2 got converted into 0.056, which means that this line number 1 is saying that this person has, if you multiply it by 0, so the probability is 0.023%. And here, if you multiply it by 100, it is 5.6%. Okay, so when the person has not got a loan, when they were rejected, the actual answer is 0. Which one is helping me to predict a more accurate value for that, more accurate probability for that? The line number 1. Okay, so when this person has not got a loan, when this person was rejected, when the actual output is 0, who is predicting the value close to 0? Using line number 1. You see, this is 0.00023, more closer to 0 compared to 0.056. Both are close to 0, but this one is more closer to 0. Correct. So this way also we will decide that we have the line number 1, which is giving such a number. When we convert that to probability, those probabilities are coming more closer to actual. Right. So what we are doing now, so whatever answer I get from this line 1 and line 2, I put it into Z1 and Z2 and this becomes 1 upon 1 plus e to the power minus z1, and it becomes z2. Okay, so what we are getting? We are getting this z1 and z2. What is z1 and z2? This is your output, which is given by the regression line. We say that these are our z1, z2. This is z1 and this is z2. So see what happens with the z. When z is less than 0, when z is negative, the probability will be less than 0.5. Okay, the probability that you predict will be less than 0.5, and when z is greater than equal to 0, it will be greater than equal to 0.5. Okay, so means when your uh, when these numbers that your line is predicting, when these numbers are greater than 0, like 11.37 is much greater than 0, so this will get converted into a probability closer to 1, like 0.99, something like that. And when the z is in negative, it will get converted into probability closer to 0. Okay, so whenever you have the number um, in positive, which is predicted by the line, so whatever values are predicted by the line, we store it into a z variable. Right? If you remember, I said that whatever this y value, we store it into another variable. So whatever is the output given by the line, if it is a positive number, so it will convert to a probability more than 0.5. And if the output is less than 0, so it will get converted into a probability less than 0.5, means less than 50%. So what is the difference between regression and classification? You see, in classification also we are using the line, but we are not stopping at these outputs. When we got these outputs, we are then further giving it to one more equation. Okay, so what are we doing in classification differently? We are first deciding on this kind of equation, and once we have decided that out of these two equations, the first one is better because it is giving me more accurate answers. So then what will you do with this? It gets converted into gz. It will get finalized into this. Gz is equal to 1 upon 1 plus e to the power minus 1.03x1, 0.3x2, 1.03x1 plus 0.32x2, then 0.21x3, 0.21x3 plus minus 1.2, or I can directly write minus 1.2. So can I say that using this kind of comparison, we have come to the conclusion that this is our final equation? Okay. Can we say we have come to this final conclusion that this is the final equation that we learn from this data? This is the final form of the equation that we learn from this data. And you see, so what happened? The line number 1 was giving the better answers. We keep that and we remove this one. Okay, now this one is gone. Okay, so we have got that the first one is now going to be kept, second one gone. That was not accurate. So now we can represent for this line 1 in its probability terms. So this is, let's say, 0.99. Let's say this is 0.056. Let's say this is 0.00023, and this is 0.99997, and this is 0.125. Correct. Now converted to probability. So we first decided on the equation of the line. Once we decided that, then we can represent them into probability. So first what we did, we decided the equation of the line. Then what we do now, if I provide a data to this, what will happen if I provide a data to this equation now? What will this equation give me? First, it will give me a number like 11.37 using this equation. Now this 11.37 is now going into another equation, which is 1 upon 1 plus e to the power minus 11.37, which gets converted into a number like 0.997. Are you now getting this idea, this flow of what we just now made? Is it making it crystal clear for you to understand? Perfect. Okay. So what are we now saying? That if I now take a testing data, right? I'm now saying that if I suppose take a testing data, this is the equation we have learned from the training data. And what exactly did we learn? These numbers. Okay, because on the basis of these numbers, we get those values like 11.37, 42.51. And the more accurate those numbers are, the more accurate the probabilities will be. So this is the equation we have learned from the training data, which is this best one. Now, if I take the testing data, if I now take, let's say, the first testing row, that a person has salary, CIBIL score, and age. So I'm now taking my first, just 2 minutes more, and we will continue from here. We have our first testing row here. And let's say this is our person who has salary of, let's say, 30K and a CIBIL score of 810 and age of 28. So can I say I will just provide this number to this number to this number to this, and what will I get? I will get the probability. First, I will get this type of number, let's say 31.59. Correct. So first, when I provide these three into this equation, I'll first get this type of number because first this equation will be solved, which is in green color. I'll get 31.59. Then what happens to that? 1 upon 1 plus e to the power minus 31.59, which gets converted further into, let's say, 0.999937. Okay. So now what is the actual output for this person? 1. What did we predict? We predicted first 31.59, then we converted that into 0.99997. So can I say we are learning correct probabilities where the actual is 1? Yes. So when the actual output is 1, we are learning a number very, very close to that, a probability very, very close to that. Okay. And if we were talking about this number, so I would have predicted a negative value for that, like minus 16.31, and that would have gotten converted into 0.000352, something like that, close to 0. Okay. So this is the idea. Now, the better this equation is, the better will be this prediction. And the better is this prediction, the better will be the probability conversion of that. Okay. So that is why in the logistic regression also, we are going to find out the values of proper M1, M2, M3, which will get converted into correct probabilities, the more accurate probabilities. Right. So you see what we do with the VIF. In the VIF, we take multiple columns. Say we have column 1, we have column 2, we have column 3. And we have to find out how much these columns are correlated to each other. So what I do now, I take this particular column and its entire values. Right. I take this column. When I say xtrain dot values, what we are doing now, we are going to each column, and for each column, we are taking all the values of that particular column. So when you say xtrain dot values, you are talking about the column values of that. Okay. So now you see what you're doing in VIF. So in VIF, what are you trying to do is you are trying to predict the values of this column with the rest of the columns. Means in VIF, what you do, the column 1, all these 3 columns are input columns. Understand? All these 3 columns are input column. But what you do now, in VIF, you take one of the column and you consider this as output, and you are trying to predict this output using these 2 inputs. Means all these three columns are input columns itself. But what you do, you take your first column, for example, you say that this is my output and I have to predict the column values using these two columns. Am I able to predict this column values using the rest of the columns? If yes, if I'm able to predict most of the values of this column using another columns, so VIF score of this column is going to be very high. Okay, so if this column has a VIF of, let's say 6, which means that more than 80% values of this column I am able to predict by using the values of these two columns. That is what we do in VIF. So in VIF, right, in VIF, we are trying to predict this column using these two columns. What are you predicting? Basically, you're trying to predict these numbers. Okay, so what you basically get a R2 score. You first get a R2 score that you convert to VIFs. So formula of VIF is 1 upon 1 minus R2 score. Now R2 score of what? You see. So what you're trying to predict, you're considering this input column as your output column, for example, and you're trying to predict this column using these two. So if you are able to predict 80% of the values of this column using these two columns, what will be the R2 score of this scenario? Right. What will be the R2 score of this entire scenario? Okay. So the more we are able to predict the value of this column, the more will be the VIF score. Correct? Now you see. So if suppose understand this much part, that will be easy. So I'm saying that we have three input columns and I have to identify whether these columns are correlated to each other or not. Okay. What is correlation? What is the correlation between input columns? If I am able to explain one column with the other columns, it means that there is high correlation between this column and other columns. How do we find out that? Now the idea is that this column can be related to two other columns or three other columns or five other columns. It can be related to that. So what I'm doing now, how do we find the VIF score of each column is we consider one of that column to be output whose VIF score I want to know. So I want to know the VIF score of this particular column. So I consider this column, it is an input column. But for the calculation of VIF, I say that let's consider this to be output column. And this column's values is xtrain dot values that I've written. Okay, this column values is your xtrain dot values basically. No, sorry. It will be these. These will be xtrain dot values. Sorry. Okay, now you see. So using these values, we are trying to predict what? These. Using these values, we are trying to predict these values. So if I'm able to predict 80% values of this column correctly using these two columns, can I say the R2 score of this experimentation will be 80% or 0.8? Can we say that? Is it correct to say? Yes. Now, if you put that into this formula, VIF is equal to 1 upon 1 minus R2 score of that. So 1 upon 1 minus 0.8. What is that? 1 upon 0.2. What is that? 5. So its VIF came out to be 5. Yes. And that is the same thing I was talking about yesterday also. That if the VIF is equal to 5, it means that you are able to explain 80% values of that particular column using other columns. So now what we have just found out, we found out that this column has a VIF of 5, which means using the other columns, we are able to explain 80% values of this column. And if it is so, we can delete this column if it is more than 5, suppose. Correct. Now, same thing we do for the other columns also. Same thing we do for this. Now we have to find out the, yes, correct, greater than 5. Yes. Now we have to calculate the VIF of this. second column. So can I say now we will treat this column as output and these two will become input? Right. So this will be now treated as the output column and we will try to predict the values of this column using this and this. Right. Yes. And now let's say that we are able to explain 73% of the values of this column. So R2 score of this situation will become 0.73. If I put it into this formula, 1 upon 1 minus 0. Let's say 0.75. So what it becomes? 1 upon 0.25 or 4. So what is the VIF score of this column? 4. Got it? So this is how we got the VIF of this column to be 4. Correct. So whichever input columns VIF score we want to find out, we consider that as the output column, and using rest of the input columns, we try to predict that column's value. And the more you are able to explain that column value, the more will be the R2 score of this experimentation. Okay. Correlation is a measure of relationship between two columns only. But VIF is for multicollinearity. VIF is a measure to check multicollinearity. Means here we are trying to find out, is this column 1 correlated to the rest of the columns? So the rest of the columns can be 5, 10, 15, 20, 25, 30, 50, 100, anything. So correlation is always between two columns, and VIF is a measure of multicollinearity. Multicollinearity means I'm trying to see if there are 50 columns or if there are 50 input columns in my data set. So using the rest 49 columns, am I able to predict this one or not? Okay, so is this column correlated to any of the rest 50 columns or not? That's the thing. So VIF is about multicollinearity. Multicollinearity means one with the rest. That's the thing. Okay, and it is not only for regression. VIF you can check in classification also and in regression also, in both the scenarios. Because in any of the data set, we do not want input columns to be highly correlated to each other.
Just a quick info, guys. Intellipaat offers an advanced certification in machine learning and AI in collaboration with Microsoft. Through this course, you can learn all the important concepts of Python, machine learning, deep learning, NLP, computer vision, and much more. The course features live classes with IIT faculty and industry experts, campus immersion at iHub IIT Roorkee, and includes certification from both Intellipaat, Microsoft, and iHub Divya Sampal IIT Roorkee. With this course, we have already helped thousands of professionals successfully transition into careers in AI, ML, and data science. You can check out the testimonials on our Achievers channel. The link is given in the description below. With the 24/7 support, placement assistance, and EMI payment options, this course can definitely set your career on the right track in the field of machine learning and AI. So visit our course page link given in the below description and take the first step towards your career growth in ML and AI.
Right. See, so in linear regression, what So our flow was basically this. I'll give you this in a better way. This is more like a rough thing we have done yesterday. See, simple thing what we understood about logistic regression is when we take this particular training data and when we give it to a regression line, it will make this kind of equation for us. Right. Now, this equation was created on the basis of the training data of classification. Now, this equation gives you what? This equation gives you y value, which is basically your output. And which output? It is going to be your y train. Okay. So when you give your training data means x train and y train. When you provide x train comma y train to a regression line, then on the basis of the training data means on the basis of x train and y train, we try to find out this kind of relationship. So it is saying that the relationship between y and these x values is this. Okay, came out to be like this, which means that if you want to predict the training output value, you will use this equation and you will get the training output. Correct. So row, right? If you take the first training row and whatever values are there in that, so if you take that and if you put it into this x1, x2, x3, x4, and then if you multiply and add up all those things, you will get a y, which is your training output, your 1 or 0 or whatever it is. You're supposed to get that. But you know, this equation does not give us 1 or 0. This equation is supposed to give us a number like this, or 23.58, 37.61, or 5.58. It is supposed to give us something like that, which is not our final output that we were expecting. So what we do, we do not stop here in logistic regression. We store that output into another variable called as z. Okay, whatever we are getting as an output through this equation, we are storing into z, and then we are giving that into another function, which is gz is equal to 1 upon 1 plus e to the power minus z. So that z, which was this, gets converted into this kind of number, which is between 0 to 1. So 11.37 suppose got converted to 0.97. So what is this 0.97? So this is uh, our first training output, means in the row number 0. Row number 0 is our first training row. In that, the output value was 1. The linear regression equation predicted 11.37. For this, means it should have predicted this number 1, but it learned that this is 11.37, which does not make sense. So we converted that to 0.97, and this is the probability. This 0.97 is saying that this particular row is representing a patient, a person. So this person has 97% probability of being this. 1 means a heart disease patient, 0 means healthy person. So 0.97 is basically saying that our logistic regression is saying that we learned from the data that this person has 97% probability of being a heart disease patient, which is very close to actual. So this person is actually a heart disease patient, and my logistic regression is saying that this person has 90% chances. So it is right. So what we overall want to do, I will write that for you. Overall, what we are trying to do, we you see all these things are done in the training process, because in the testing process we just test whatever model we have created. So we have training process. In the training process, we have our y-train variable. Right. And y-train variable is what? The training output column in the in this classification data. So we have our y-train, which is 1 0 0 1 1 1 0 0 1 1 0. This is our training output column, y-train. And what I need to do is I need to identify this equation. I need to create this equation on that particular data. Now the equation has to be created in such a way that it is able to predict a probability close to 1 where the actual output is 1, and close to 0 where the actual output is 0. Okay. So what we need to do, we basically need to find out these values, which is M1, M2, M1, M2, M3, and C. These all values we need to find out. So such values we have to find out of M1, M2, M3, and C, so that this equation overall is able to identify the probability closer to actual output, right? For example, suppose I get equation 1, and then we have equation 2. What do I mean by this equation 1, equation 2? So I've written since yesterday. So suppose this gz equation. So I'm saying 1 upon 1 plus e to the power minus z1. Z1 means this. where M1 is this, M2 is this, M3 is this, M4 is this. So if I put these values in the place of Z1, so it becomes that particular equation. Then I have another line which has this values, and I say, let's say this is my Z2, and I put it into this equation. So I'm considering this to be my equation 1 and this is to be my equation 2. Okay, so for example, if I have two different equations, which one will be finalized as the final equation which is going to perform the best, right? How do we decide that? So two lines are there. So the way it will be decided is this. Now using equation number 1, what we are able to learn as a probability is this. So when the actual output is 1, according to equation 1, we learn that it is 0.99 and it is learning 0.91. When the actual output is 0, this one did learn that 0.00035 and it did learn that 0.056. Now, this one did learn that 0.00246 and this one is learning, yes, say 0.073. And in this case, it is learning 0.099973 and it is learning 8742. Correct. Now you see what your model is supposed to learn, what this equation is supposed to learn. This equation is supposed to learn a probability which is close to the actual output. Right. So our actual outputs are Y train 10010, all these. And what my equation, GZ equation, is supposed to learn, it is supposed to learn the probability close to actual. Now, when the person is a heart disease patient, this is Y train. So we know that this is the first person, my first training row, and this person is a heart disease patient. It is sure because this is the output given for that. So my equation 1 is saying that I learn from the data that this person has 99% probability of being a heart disease patient. And the equation 2 is saying that I learn that there is 91% probability that this person has heart disease. Okay. So who is predicting the thing more correctly? You can see clearly this one, because when we know that this person is heart disease patient, so equation is learning with a very higher probability that this person has heart disease. Okay. Now see, when you see this one, remember this point for the zeros. So this person is a healthy person, no heart disease. Second one is a healthy person, no heart disease. Zero means no heart disease. So what is your model saying here? 0.00035. What does this mean? How do you read it? So our equation number 2 is saying that this person has 0.00035 this probability of being a heart disease patient. Okay, understand what is this saying? This is saying that this number is saying that, see, when you multiply it by 100, then you can represent in percentage terms. So it will move two places ahead. So it will become 0.035%. So this equation 1 is saying that this person has 0.035% probability of being a heart disease patient. Okay, there is a 0.035% probability that this person is a heart disease patient. And on the other hand, what is your equation 2 saying? If I multiply, it will move two places ahead. So we are saying that equation 2 is saying this person has 5.6% probability that this person is heart disease patient. 5.6% probability. So who is telling us more actual answer? The equation 1, because equation 1 is saying that this person has only 0.035% probability, not even 0.5%. It is way too lesser than that. Okay, so equation 1 is saying that there is only 0.035% probability, very small, probability that this person is a heart disease patient, which is right because this person is very healthy. This person is not a heart disease patient. On the other hand, equation 2 is predicting a higher probability for this person being a heart disease patient. So remember that all these probabilities, they tell you the probability of the person being a heart disease patient. These probabilities are the probability of 1. Okay, all these probabilities are the probability of getting 1. Remember this point. Okay, now, so let me show you the S curve that will be made in this last few points, and then we will see the practical related to it. Okay, how will you get the S curve? Now, suppose we have our input column here and we have our output here. Output, you know, is no or 0. And here we have yes or 1. Okay, now, so see what happens. I have some data points where I am having my training data. And for this one, just in 2 minutes, you will see in the simplest possible way that how do you get a S-like curve in the logistic regression. That is what is made. Now, see, so I was explaining to you yesterday about this two things, that when you have this classification data, first you are learning these numbers which are coming from the equation of a line, then getting converted to probability using the equation of sigmoid function. Okay, so first you are learning the equation of a line and then predicting the probabilities. Now you see, if you take these numbers, right? If you take these numbers and then you plot it. So what do you get is this. See. Okay. So when we talk about this regression line, what do we learn? So we learn that this is the first actual output, first actual data point whose output is something. See, so we learn this, we learn this, we learn this, we learn this, and we learn this. Okay, see, so what are we learning? We are learning that this is our first data point whose actual output is this much, but our predicted output is this much according to the line. For the second point, this is the actual output of the second one, and this is what we have learned using the line. So whatever prediction is being made, whatever learning is being done by the line on the training data, these are those learnings. Okay, these are the output that it has learned. It should have learned these black points, which are little different values, but it is learning that which is close to that. It is not exactly learning the same output value. It is learning as close to that as possible compared to any other line. So when you put all the predicted values into this equation, into this graph, so it will form this straight line, and you can pass a straight line through all the predictions. Correct. So I'm saying I'm talking about this. I'm talking about plotting these values. So I was showing to you that this is our Y train. So suppose I have 7 rows here. So first 5 rows are our training rows. And this 5 values that you see here in the price in the blue color box that I made, this is our Y train. And our linear regression equation is supposed to learn these 5 values. But what it is learning? It is learning the values as close to that as possible, not exactly those values. Okay, now out of 2 lines, whoever is learning the values
close to actual, that is learning well. Okay, so if this is a line which is learning the values more close to actual, it will predict for the testing data also more close to actual. Okay, so that is the thing. Now I'm saying if you take these numbers, which has been learned by your line equation, and if you plot these values into a graph, so it will fall exactly on the line. Getting the point? What I'm trying to say? So they will fall exactly on the line. And if you keep putting that, it will form this straight line equation or a straight line manner, it will be plotted. All right. Now, same thing you can do in this sigmoid function scenario also. See, so I have taken 8 data points here. These are 8 people. Out of these 8 people, these 4 people does not have heart disease and they have heart disease. Okay, I'm taking, for example, 8 such data points, out of which 4 of them, yes, out of which 4 of them does not have heart disease and 4 of them have. Or you can say these 4 does not have diabetes and these had. So this is my training data. I'm taking 8 rows of my training data. Now, so these are our actual outputs. These are 0, 0, 0, 0, and these are 1, 1, 1, 1. These are the wide range values of these 8 data points, the actual outputs. Now, if you take the equation number 1, if you see, is predicting a number very close to 0 when the actual output is 0. Right. So when the actual output is 0, the equation number 1 is learning the probability which is very close to 0, like 0.00035, 0.00246, like that. So what I do now, if I plot all the predictions or the probabilities which have been learned by the uh, first equation, so it will fall something like this, close to 0. Okay, very, very close to 0. And for the ones, it is predicting number very, very close to 1. Correct. Means here the predictions or the probabilities which is being given by the equation number 1, which is like 0.99, very close to 1. Correct. That is what it is learning. Now, if you go and see the second equation, equation number 2, which had a different m1, m2 values, if I take this into my sigmoid function, so it did learn different probabilities. So you see now, where equation 1 did give me this probability when the output was 0, equation 2 is giving me little bigger probability value, not that much smaller. So it is like if I take, yes, if I take the equation number 2, it is learning something like this for the actual output. Now, what I do, I will connect these. So when you connect these, you will see they are like, sorry, bad. And the second one is, okay. So S curve is nothing but when you connect all these points, you will connect them in this manner because this is how they will be plotted. Okay, if you take more and more White-Trend values and if you take their predictions, you will see that they will fall on the line. They will fall in this particular manner, like the S curve. So if you just connect them, you will see this kind of S curve being created automatically. So how am I making the S curve? I'm just connecting the points which will fall on this in this way, in the curve manner itself, it will fall. I'm just connecting them, the points. Now what I have got, so this is the curve which is representing the probabilities that has been learned by equation 1, and this is the curve after representing the probabilities which have been learned by the equation. So you see now we have got two S-curves and we have to identify best S-curve out of these two. Like we were identifying best fit line out of multiple lines. Same way here also we have to predict the best S-curve out of these two. So which one is a best S-curve? How do you decide that? So you see here, what I did, I just took these numbers and I plotted it into the graph. And then I took these numbers, I plotted into the graph. And then I connected them. So I'm telling you that when you connect those points, if I would have taken more of these numbers here and more numbers here, so they will turn out to be like the S curve automatically. If you just keep connecting all the points, they will automatically make this S curve. That is the property of the sigmoid function. Okay, sigmoid function is this. This gz is equal to 1 upon 1 plus e to the power minus z. So it is the property of the sigmoid function that its graph will always be like this S curve. That's the property. So this will always happen when you represent the output of sigmoid function. Now you see the equation 1, the curve which is being made using equation 1 is better out of these two because when the actual output is 1, it is learning the probability also very close to 1. Okay. And now for the same White value when it is 1, right? For the same value when it is 1, so it is learning this probability. Okay, yes. So when you first notice this point, this is one of my White values, means one of my training rows. So for this training data, my actual output is 1. And who is learning better this value? Equation 1, the curve of equation 1, because it is predicting this probability very close to 1, like 0.99 something. And the equation 2 is learning a probability like 0.85 something, not that close to 1. Okay. So the curve which is closer to 0 and 1 line, that will be better. Okay, and whichever equation helped me to make this curve will be finalized as the best and the final. Now, right, now what we do here, there is a concept related to that. So what I'm going to do, I'm just going to remove this second one for now. Okay, so what we are basically doing, there is one technical thing that we are doing here. Look at this, what we are doing. So for the actual outputs which are 1, yes, here we are picking the best fit S curve. As simple as that. Now focus on one last thing for now, theoretical aspect. So what we are doing when we talk about these, right? When we talk about these, whose actual output is 1 for the 4 training rows, whose actual output is 1, what are we predicting for those? A very high probability. Okay, so if I say, if I make 4 lines here, so all 4 of them is put here. And if I mention them, let's say P5, P6, P7, and P8. Probability 5, probability 6, probability 7, probability of 8th data point. So you see now, these are the probabilities of that. And what are the probabilities of the first 4? This much. From the line of 0 to that point. Line of 0 to that point. So I'm making this kind of line here. From the line of 0 touching the first point. That is the probability we are doing. Okay, so can I say we are focusing on minimizing these probabilities and maximizing these probabilities? Means through our learning, what is our equation trying to do here when it is predicting these probabilities? Can we say it is trying to maximize these probabilities, the probability for these values? See, I'm talking about these dots, the green dots, which are our probabilities. So can I say our best learning means what? We are trying to maximize the probabilities when the actual output is 1, and we are trying to minimize the probability when the actual output is 0. Okay, probability of what? So the probability that the output is 1. Now, when the actual output is 0, so the probability of it being 1 should be minimum. Okay, because in the sigmoid function, what do we represent? We are always representing the probability of output is equal to 1 given the input. So when the actual output is 1, so probability should be high, close to 1. But when the actual output is 0, the probability of that being 1 should be minimum, right? So you can see that we are trying to make these dots very close to 0, which means that we are saying that the probability is only this much. This should be only this much. Very minimum. Okay, so because they are 0 points, because their output is actually 0, the probability of them falling into 1 should be minimum. Now, so if you see now closely, if suppose the probability of this is this much, and probability of this is this much, probability of this is this much, this is this much. So I'm saying this is P1, P2, P3, and P4. So can I say, can I write something like we are trying to minimize the probabilities P1, P2, P3, and P4. And at the same time, we are trying to maximize the probabilities P5, P6, P7, and P8. All right. So we are trying to minimize these first 4 probabilities, and we are trying to maximize the next 4 probabilities here. Now, can I write it in a single equation instead of having 2 different equations for this, that we are minimizing 4 and we are maximizing 4? Instead of that, can I say this? If suppose P1 is this much, which is 0.00 something, can I say 1 minus P1 will be this much? Okay, so this black line can be 1 minus P1, and then for the P2, if that much is P2, then the rest of the part going from that point to this can be 1 minus P2. And then we have here, this can be 1 minus P3. And then we have here 1 minus P4. So if you are minimizing P4, can we say that we are maximizing 1 minus P4? If means that if P4 is 0.05, then what will be 1 minus P4? 0.95. Okay. And if I make P4 as 0.005, so what will happen? The 1 minus P4 will become 0.995. Now, which one is more closer to actual? So this one, where the actual value is 0, if I'm predicting 0.005, it is better than predicting 0.05 because we are going more close to 0. So can I say if I'm minimizing this number, then automatically we are maximizing this number? Right, it should not be 0.095, it will be 0.0, what should be there? 5 and 99.5. Okay, see. So can I say if you are minimizing the P1, P2, P3 and P4, if you are minimizing these 4 probabilities, so can we say it is also true that we are maximizing 1 minus P1, 1 minus P2, 1 minus P3, 1 minus P4. And why am I writing that? Can we write overall that 1 minus P1 into 1 minus P2 into 1 minus P3 into 1 minus P4 into P5 into P6 into P7 into P8. Can I say that we are overall maximizing this entire formula, all these probabilities? Means, can it be said, is it correct? Is it okay to say if I say we are maximizing this entire thing? Yes. Okay. So instead of writing that few things we are minimizing and few maximizing, few probabilities we are maximizing and minimizing, we can say instead of P1, let's write 1 minus P1. So if I'm trying to find the P1 as low as possible, so I can say I'm trying to find out 1 minus P1, which is as big as possible. Okay, right. So then I can write this one equation overall where I'm saying we are trying to maximize this entire thing. And this concept is known as maximum likelihood estimation. Okay, this concept is known as maximum likelihood estimation. So your sigmoid function or this logistic regression is going to utilize this concept of maximum likelihood estimation to determine which curve is better. Okay, so whichever curve is maximizing this equation is better. Understood? So this is a function known as maximum likelihood estimation, like we had cost function in linear regression. So cost function was saying that the line which is the best has the least cost value, or cost was what? Total error. So cost function was nothing but the total error or MSE value. So the line which has the least total error will have least cost function value also. Same way, in the logistic regression, we use this maximum likelihood estimation. So whichever equation of our sigmoid function, whichever equation of M1, M2 does this, maximizes these probabilities, will be finalized as our final M1, M2 values and that final equation. Makes sense? That there is a particular central formula which is guiding the logistic regression towards that. Okay, so theoretically also we understood, and through this equation also we understood that scenario. Don't worry, it will take some time to. Yes. So now the idea of the logistic regression is understood at this point. Now we will move ahead and see the practical related. I'm going to write the most of the code that I'm going to write here will be similar to what we have seen in linear regression. Okay, only 2-3 things will be new. So we will focus on that new part. Yes. So what I said, Sagar, is this. I said this in simple terms. Let me explain to you with a simple graph. So that part is little confusing because you might have forgotten yesterday's few of the points that I said. So to understand that graph, remember. So we have this kind of equation in sigmoid function, which is 1 upon 1 plus e to the power minus m1x1 plus m2x2 plus c. Let's say only two input columns we have, x1 and x2. See, x1 and x2 represents our input columns. Anytime you see this equation, x1 first input column, x2 second input column. Now you are trying to find the weightage of both the columns. M1 and M2 is the weightage of those columns. Simple thing. That is what we are trying to find, and C is the intercept value that we have. So this is how the equation look like. This is how our uh, machine learning model look like in logistic regression. In linear regression, our machine learning model is the best fit line equation, where we find the final values of M1, M2, M3, all of that. So when we get that final equation, it means that our learning has been completed, and that is our ML model, the final output. In the case of logistic regression, our final output is what? This equation, where we need to find these values M1, M2, and C. Now there can be many values of M1, M2, and C. So how do you find out those exact values of M1, M2, and C so that our model is learning the values close to actual? So see what I was trying to say. A simple example I'll take. So we have input and then we have output. So here Let's look at 2 points, one here and one here. And then we have the line of yes, which is 1. And this is the line of no or 0 here. Okay. So now I'm saying that there are 2 points, these and these. So 4 points I am taking, which means 4 input rows. Now, plotting of these dots, plotting of these data points is done using input values, input columns, and the output is 1 for these. So these are the two data points whose actual output is 1 and 1, and these are the two data points whose actual output is 0 and 0. Means from the given data, from the given training data, what we know is that these two people are non-heart disease patient, means healthy people, and these two are the heart disease patient. So what we are saying that is, if I take a particular value of M1 and M2 here, right? If I suppose find the value of this equation to be like this, 1 upon 1 plus e to the power minus say 1.2 x1 plus 0.87 x2 plus 0.93. Let's say I'm trying these values into this equation. I'm trying M1 to be this much, M2 to be this much, M3 to be this much. Sorry, C to be this much. And I'm trying these three numbers. I do not know whether these are the best values or not, but I'm saying how do we know whether these M1, M2 value is best or not, whether this equation is best or not, or should I try any other M1, M2 values? So you see, when you do this M1, M2, and C value, what you are getting as a prediction, that equation is predicting this kind of probability. For this one, this much, for this one, this much, let's say this much, and let's say this one, this much. So I said, if you suppose take this equation for now, this M1, this M2, and this C, so what probabilities you predicted? So when the first training row you saw, its actual output is 1. So I'm saying row number 0, row number 1, row number 2, row number 3. So its actual output is 0. It is also 0. Its actual output is 1. Output is 1. I'm talking about Y train. So what is the probability that you're learning using this M1, M2? You're learning this much, which is not close to 0. Here it is 0. So here it is say 0.25 or 0.20. Okay, so actual is 0, but what probability you are learning through this equation? 0.20 when the actual output is 0. Means you are saying that this person has 20% probability of being a heart disease patient, which if you see is not very right, because I know that this person is a healthy person and my equation is saying that because of these M1, M2 and C, this equation is saying that this person has 20% probability. So, and if you connect these, you will get this type of S curve, right? Now I'm saying, let's change the equation. And now I'm trying this equation. Gz is equal to 1 upon 1 plus e to the power minus, say, 0.51 x1 plus 0.72 x2 plus 1.53. I changed the value of M1, M2 and C. Now what I got these when I change the equation. So now what probabilities I'm getting are, let's say, these. And when I connected them, it came out to be like this. Right? When I connected them, they came out to be like this. So what are we doing here? What was that this maximize part that I've written? How I have written this equation is this. You see. So what are we supposed to do? What is our equation supposed to do? it is supposed to predict a probability close to the actual output. So when the actual output is 0, the probability that we are supposed to learn from that should be close to 0. When it is 1, it should be close to 1. So out of these two curves, first and second, out of these two curves, which one is learning the probability close to actual? So you would see that it is the curve number 2. But how did we decide that? Means I am seeing the drawing here and I am able to tell you that curve 2 looks better because it seems to be closer. I am able to see the drawing. But logistic regression is a mathematical concept. It will not see the drawing like this. So how will the logistic regression decide out of these two curves which is better? And should it try the other equations also or not? How will it know? So you see, so take the first training row number first, your first training row. Its actual output is 0, and what is the probability being learned by the curve number 2? This much. And what is the probability being learned by curve number 2? This much. Correct. So you see the height. Notice the height of this and notice the height of this. So this height is what? This is the probability that we are learning uh, using these two different equations. Okay, by equation number 1 here and by equation number 2 with these m1, m2 and c, these are the probabilities we are learning. So now you see that this is p1, the probability learned by the equation number 1, and this is p1, the probability learned by the equation number 2. So you see now, can we say when the probability is minimum? So we are saying that when the actual output is 0, I know that for this one the actual output is 0. So can I say that our equation will be best if it is predicting the probability also close to 0, a very minimal probability for that? Because probability means what? Remember this, whenever I say probability, it is the probability of output being 1. We are always saying the probability of our output being 1. So when the output is actually 0, so is it correct to say that its probability of being 1 should be very minimal? Right. So if the actual output is 0, so its probability of so the probability of the output being 1 should be very minimal. Correct. So because it is 0, so the probability that our curve has to predict for this data point should be very minimal, because we should say that if this person is a healthy person, so our probability should come out to be like very, very small number. Okay, this probability that our model should learn should be very small. So when the person is actually non-heart disease patient, our model is learning this probability saying that this much is the probability that this person is a heart disease patient, which is very small. So we are trying to find such a equation of m1, m2 and c so that the probability learned by our equation should be very small when the actual output is 0 and very large when the actual output is 1. This point all of you should be getting, right? This much point you should be getting. So you can see that what are we trying to do? We are minimizing these two probabilities. We are trying to minimize these two probabilities and we are trying to maximize these two probabilities. Maximize means what? So when this, if I take this data point, this is actually 1. Its actual output is 1. So who is giving a more closer probability for that? Right. So this is the equation number 1 and this is the equation number 2. So this is saying that 95% and this is saying that 0.87, suppose. So equation number 1 is saying that this person has 87% probability of being a heart disease patient, and equation 2 is saying that this person has 95% probability of being heart disease patient. So can I say when we have the actual output 1, so we are maximizing this probability? We are trying to find as maximum probability as possible for that. Then only this will go closer to 0. Yes, right. So when the actual output is 1, we are trying to maximize the probability. And when the actual output is 0, we are minimizing. Now, so you now see this. Okay, now see this. So if this is the probability being learned by equation 1, so what is 1 minus that probability? This much. If I talk about this probability that has been learned for the first data point. So this is P1. This is 1 minus P1. Now, look at this one. Okay, look at this one now. For the equation number 2. If this much is the probability being given by the equation number 2, what will be 1 minus P1? You see, 1 minus P1 is this much. Look at this blue line and this green line. Which is longer? So you will see that this blue line is longer than the green line. What does this mean? So it means that this 1 minus P1 given by this blue line is longer, is higher compared to 1 minus P1 given by the green line. So what does this mean? When you minimize this probability, you automatically maximize 1 minus P1. If you make the P1 small, you are making 1 minus P1 larger, because what is the total probability? 1, 1.0. So if P1 is our 0.05, I said, so 1 minus P1 will be some number, and if P1 is 0.005, then the 1 minus P1 will be even larger. Okay, so whichever equation is giving a smaller P1, for that 1 minus P1 will be larger. So can I say we are minimizing the P1, and we can also say we are maximizing 1 minus P1? Correct. So I could say that we are minimizing P1 and P2, which also means that in another word, I can say that we are maximizing 1 minus P1 and 1 minus P2. So that is what I've written here. So you could say that we are minimizing these 4 and maximizing these 4. But then you will get two different equations. These you are minimizing, these you are maximizing. Now to write it as one equation, we are saying that, can we write it like this? We are maximizing these 4 and we are maximizing these 4. So we will get one equation. This total product we are maximizing. Means whichever equation of sigmoid function gives me the highest value of this equation will be finalized. Means out of these two equations, whichever equation gives me the highest value of this product will be finalized as our best S curve, or will be finalized to make that line. So what you are basically doing, you are taking first these and then you're converting to that. In logistic, what you're doing, first you're taking a line and then modifying that value to this curve. So we only have to focus on this one. This is an intermediate thing which will be done in the background. We do not need to focus. Okay, now, so in this drive link, I have given you the file hard.csv. Download that one and steps we are taking. We have seen these steps properly in the linear regression also, but just I'm writing that for you to give you an idea. Okay, and whatever new is there, we will focus on that for now. So we have pd.read csv and we have hard.csv. And then if you look at the head function of this data frame, we have this type of data. We have one output column, target. In the target column, 1 means this person is a heart disease patient and 0 means this person was not a heart disease patient. 0 means healthy, 1 means heart disease patient. So it's a given data. We need to learn that equation of the sigmoid function, and basically we need to find out the value of m1, m2 those things. So when we run this code is going to help us find out those M1, M2, and C value, like we have done in linear regression with the code. We'll see that. So here what we do, we print the top 5 rows of the data. After that, we write hard dot shape. Very good name I've taken. Yes. So here we have 303 rows and 14 columns are there. This is the shape of this data frame. Print the number of rows and columns. This is the amount of data we are dealing with. It's very small, but no problem. We'll use it anyway for now. Dot D types. And what does the D types tell us? It is going to print the data type of values present in each column. Okay, and we are trying to see, is there any object column or not? If there is any object column, which means that is a text column, and we will need to encode that. So there is no such column. So what I move to, first I check pd.read CSV. I've given this notebook file, you can see. And whatever I'm writing, if it is not updated, just update the link and it will be okay. I've uploaded this one, hard.csv, in the drive link. Just you can refresh that if it is not visible. At the bottom, it is present. So we have this pd.read CSV and this CSV file, then head function to see how your data look like, shape to see the number of rows and column, D types. And after that, few other basic things we check is for the missing values, hard dot is null dot sum, and this is going to print the total number of missing values column wise. So if you see, there are 0, 0, 0 visible. It means there are no missing values in any of the column as of now. After missing value, we focus on the duplicates. So here we say hard dot duplicated dot sum. Hard dot duplicated dot sum. So this is going to print the total number of duplicate rows present in the data. Total number of duplicate rows present in the data. So how many duplicate rows we have here? 1. Okay, we have 1 duplicate row in this data. So how are we going to see which is that duplicate row? So we say the name of the data frame and then the name of data frame dot duplicated. I have written all these things and you must know all these things. So we are printing the duplicate row. So when we run this code, we are going to print that particular duplicate row. So we have 1 duplicate row and that is row number 164. That's duplicate. So what I can do for that, I can remove it by saying hard dot duplicated dot sum. Okay, sorry, not this, hard dot drop duplicates. And we say in place is equal to true for that. And what is this going to do? Drop all the duplicate rows. It is going to delete all the duplicate rows from our data. So we have checked missing value, duplicate, the data types and all. So one important thing that you need to do is outlier removal, and that I'm leaving for you. I've given you a function already in the last session. Use that or try to write a function yourself and try to do the outlier removal from the data by writing a code for that. That one thing you have to do. Next, once we have checked all those basic things about the data, then we can move to the machine learning process, which is our step number 3. Okay, so what we have done till now, we just took the data, read it, and saw some basic things. And here we removed one duplicate row. And one more thing I'm saying that you will write the code for now. Okay, so now we are coming to the machine learning process. In the machine learning process, what is our step number 1? In the machine learning process, our step number 1 is to create this x and y variable. In x variable, what do we store? All the input columns, and in y variable we store the output column. Okay, so x variable all the input columns and y variable the output column. So what is our input column? So here we say hard dot drop. We have a column called as target. Okay, we have a column called as target. Right. So target column is our output column. So I'm saying that don't take the target column, except the target column. Keep everything else, keep all the other columns into x variable. Since this is the output column, I'm saying that apart from this one column, take every other column and store into x variable. And then I'm saying take that hard column, sorry, not hard, target, yes. So take that target column and store into y. Right, this is what we do. Now, once we have got the x and y variable, what is the next thing that we do is we split the data into training and testing. Right. So here we create 4 variables: x train, x test, y train, y test. Okay. Now, so then we have this function called as train test split x comma y, and then we have test size is equal to 0.2, and then random state is equal to, let's say, 100. So random state I'll explain. So you can see here we have written these 4 variables: x train, x test, y train, y test. Am I making a mistake here? Why am I getting confused? Is it right, the sequence that I've written? Let me check. Yes, I am forgetting. Correct. It should be x train, y train, and I think it should be x test, y test. Yes, correct. So now, once we run that, we are splitting our data into 4 parts. And you see, this means that 20% rows should be taken for testing purpose, and 80% of the rows should be taken for the training purpose. So what is the random state? Just coming to that in 2 minutes. But first, let me show you the next process that we do here is something called as standardization, or also called as scaling of the data. Okay, there is something called as a standardization or the scaling of the data that we need to do. Okay, so what is that? You see, first let me explain you a simple idea about it. See, there are some columns in this data which have larger values, which are having little big values, and then there are a lot of columns which have very small values. For example, if you see this column, this column, this column, this column, they have kind of big numbers in that. 150, 187, 233, 250. They have big numbers in those columns. Compared to that, if you see this column, this, they have small numbers like 0, 0.8, 1.4, 3.5, 2.3, 1, 2. Small numbers are there in other columns. So what happens if you take a data like this? Your M1, M2 values, which are the weightage, those will not come out to be the correct values. Okay, because of some column being having larger values and some column having smaller values. So what will happen? Your weightage values that should be a particular number, it will not be coming out to be that number. It will become a smaller number and our interpretation of that will become wrong. So we have to make it, we have to do what? We have to do a process called a scaling of the data, where what we will do, we will convert each column into such a range of values that they all are of the similar range. And it should not happen that a column has bigger value or smaller value for in this. But why do we need to do that? So let me explain to you with a proper example. Why do we need to do the scaling of the data? Here. So scaling means converting all the column values in such a range that none of the columns should feel that it has larger value compared to another columns. So we convert that into some other set of values. Say we have a data set in which I have area of the house, number of rooms, and then we have the price. Say we are working on this data set. It's a regression data, but you get the point here. So we have row number 0, row number 1, row number 2, row number 3, 4, like that. A house has 2500 square foot area, 4200 square foot area, 2100 square feet, 1700 square feet, 5000 square feet. Number of rooms are 2, 5, 2, let's say 2, and say 7. And then we have some price of different houses. So say the first house has say $500,000, $500,000, and then the second house has, let's say, a price of $950,000. This one has, let's say, $1.2 million. These are the house prices of different houses. Now, so this is our training data. And on the basis of these training data, in both linear and logistic, we need to find out M1x1 plus M2x2 plus C. In both linear and logistic, we need to find this, where we are looking for M1, M2, and C. Now suppose the area column is supposed to have, okay, for example, the area column is supposed to have the M1 of 2, because this one is our x1 variable, this one is our x2 variable, and this is y output. So suppose the actual weightage of area column is supposed to be 2, and the actual weightage of the rooms is supposed to be 1.8, and the C value is, let's say, what, C value, let's say 5, just as an example. Now, so here, what do you see? Just as an example, I'm taking this. Suppose focus on these M1 and M2. These are weightages of the two columns, X1 and X2. X2 is the rooms, number of rooms, and X1 is the area of the house. Now you know that the bigger the M value, the more is the weightage of that particular column. So if I see M1 being 2, I will think that, or I will get this information that area column is more important than rooms, and because it has more contribution in the prediction of the price. But you see, if I try to use it into the equation, and if I suppose have the first training row. If I take the first training row, in that training row, in row number 0, what is given? You see, the number of rooms is 2, area is 2500, and its actual price is this much. Right. Now, you know that these are the actual output, and we are supposed to learn an output which is closer to that. We don't learn the exact output. We have just studied that. We are supposed to learn the output which is closer to these. So the closer, the better. Now, let's say these are the best values to 1.8 and 5 that we have learned from the equation. Now, if I put it into this equation, if I put it into this here for the first training row, what it will be? It will be 2 into 2500. M1 is 2, X1 is 2500 for the first house, plus 1.8 into number of rooms, which is 2, plus 5. Okay. Now what it will come out to be? It will come out to be 5000 plus 3.6 plus 5. What is it coming out to be? 5,000, 8.6 thousand dollars. Now, what is the actual price? Actual price is $500,000. What are you getting if you multiply all these things? $5,000. Actual price is $500,000, but you are getting $5,000. Okay. So why did this happen? You are supposed to predict this number, but you are predicting a very big number here. Why did this happen? See, can we see that this is overpowering this entire equation? Means these two values do not even matter in the context of this. Correct. You see what is happening? These two numbers even do not matter in the context of the first one, because one is 5,000 and other is just 3.6 and 5. So it means that these two even don't matter. Is it right? No, it is not right. Something is wrong. What is wrong? Let's see the solution. Okay, let's see the solution. Yes, it is not standardized. See what is happening. This value, which is very large, okay, this area column has very large values and room column has very small value. Because of the values being large in the area column, see, it is overpowering the entire calculation. Okay, but it should not happen like that the entire calculation is being overshadowed by only one of the values. And why is it happening? Because one of the column has very large numbers compared to other columns. So that is overpowering this entire calculation. What are the solutions? The first solution that we have is we modify the M1, M2 values. Okay, we modify the M1, M2 values. So I can say that, okay, M1 I have taken 2. I have found that to be 2. M2 I have found it to be 1.8. So let's do one thing. Instead of M1 being 2, let's make it 0.002. Will that be okay for us? Let's say now when we have M1 x1 plus M2 x2 plus C. So now I'm taking 0.002 into 2500 plus 1.8 into 2 plus C. Right. Now, what is this that we are getting? So when I say 2500 into 2 into 0.002, so it will come out to be like 5.0, I guess. Yes, it will come out to be 5.0 plus 3.6 plus 5. Okay, or let's not make it that small. Let's make it 500K. So let's say I'm making 0.0 better. So 2500 into 0.2, it will be 500, I guess. It will come out to be, let's say 500, I guess. Now, if I add it up, I get $508,600. Now see, as I reduced my M1 value from 2 to 0.2, am I getting close to what actual value should have been? Means somehow, if I just do this modification, my actual output is 500K, right? 500,000, and I'm predicting 508,000, close to what the actual output is. Now, what I had to do to get to that point? What I had to do to get to that point, I had to scale down my M1 value from 2 to 0.2. Right? Now, you see, its actual weightage is this much. I'm saying that the actual weightage, suppose for the area column is 2, but we are scaling down this weightage value to 0.2 just to make the calculations in that same range. Okay. Because this x1 value is very large, I had to make its m value small. I had to scale it down so that overall calculations can be right. Is it right thing to do to scale down your m1 values just to make the calculations correct? What is the problem with this? See, we will get the predictions right. We will get the predictions right. But what is the problem that is going to happen because of this? Can I say our interpretation of this M1 value will become wrong? Okay, can we say it will be like when I see the M1 is 0.2, I will think that the M1 is not important, or the area column is not that much important in predicting the price of the house. Because M1 is what? M1 is the weightage given to the area column. So if M1 I am making smaller from 2 to 0.2 just to make my calculations of the same scale, what is happening? Now if I see the M1 value, I will think that the weightage of the area column is just very small, 0.2. So in actual, right, you see, in actual, which one has more weightage? In actual, more weightage is there of uh, area and lesser weightages of the number of rooms. But after modification, now your M1 became smaller just to make the calculation correct, and your uh, M2 is staying same. So now I will think that this is a bigger number and M2 is more important. But that is wrong. M2 is not more important. M1 is actually more important. We just had to scale down the M1 values to make this calculations correct. Okay, so this is not the correct thing to do. To make the calculation correct, it is not right to make to scale down that number. So can I say, instead of scaling the M1 value or M2 value, I will scale down the column itself, the area column itself, I'll scale down. Right. Will that be a better approach to take? So instead of using this big numbers, 2500, 4200, I will use its scaled version. And how is that scaling done? So there is a formula which is called as Z is equal to data minus mean upon standard deviation. So what we do with the area column, so our area column has numbers like 2500, then 4200, 2100, 4200, 2100, 1700, 5000. These kind of numbers are there in the area column. So I'm saying, let's modify these values into their scaled version. What I will do, I will take that number 2500, subtract the mean of this data and divide by standard deviation. Let's say the mean value is 3000, for example, and standard deviation is say 200, for example. So we will say 2500 minus 3000 divided by 200. It will get converted into, you see, 500 by 200, 2.5. What happened? 2500 got scaled down to 2.5. Same way, I will take 4200 minus 3000 divided by 200. So 1200 by 200, 6. So 4200 got scaled to 6. What does these numbers are? Have you studied the z-score concept? What does the z-score represent in statistics? It is a formula which is called a z-score. And can you tell me what are these numbers telling you? Which are these modified or scaled down version? So these are nothing but we are saying 2500 is such a number, right? It will be minus 2.5 because minus 500 by 200 minus 2.5. So we are saying 2500 is that number which is 2.5 standard deviations away from the mean on the lower side. Okay, so instead of representing the actual values of the area, we are representing them in their standard deviation terms, which is a smaller number to see. Now, whichever is the larger value, its scaled value will also be larger overall in the column. So is it right to do this thing? Yes, perfectly fine. There is no problem of doing the scaling. It might not make sense to us, but it will make perfect sense to the algorithms. So what we are doing now, we are representing the actual values in their standard deviation terms. Means I'm saying 2500 is the actual value, and we found out that its z value is this minus 2.5 by doing this calculation. What is it? So instead of representing 2500 in that column, I'll replace it with minus 2.5, which is what we are saying is that 2500 is such a number in that column which is 2.5 standard deviations away from the mean on the lower side. So instead of giving the actual values, we are giving them locations, the relative locations from the mean to the algorithm. So is it usable enough for the algorithm? Yes, perfectly, without any problem. Okay, so if I do this, then is it a better thing instead of scaling the M1, M2 values? Is it better to scale the column itself instead of scaling the M1, M2? Yes, it is better. Okay, because we want to make our calculations right. And if we scale down the M1, M2, our interpretation becomes wrong. Instead of that, we try to scale down the columns, input columns. Makes sense what we have just now discussed? So we are using this particular formula for scaling the column down to its smaller versions. So instead of area column this, I will be using this scaled version of the area column. Okay, I'm saying that instead of using this, I will be using their scaled version. This process is known as standardization process. Conversion of this to this into this form is known as a standardization process. Why standardization? Because this formula is known as standard score. It is known as z-score also, but it is also known as standard score. So since we are applying standard score on the data, so that is why this is known as standardization process. Okay, yes. So standardization basically means scaling down the values of the column which are very large. How do we do that? So there are two lines of, yes. So here we have taken a standard scalar class, and we are going to make an object of it. So since it is a class, we make an object of that. Then what I do, I say take this object, and then we mention here dot fit transform xtrain, and then here we say scalar dot transform xtest. What it will give me, I will store that into a new variable xtrain scaled, and see, I will say xtest scale. See, in the classification data, we do not need to scale the output column. Output column is already so small, 1, 0. We just scale the input columns. And in the input columns also, we scale the training and testing data separately. Okay. We need to scale the training and testing data both separately. This is one very important thing. Okay. We do not scale the entire input columns together. We have to scale the xtrain and xtest separately. Right. Now you can see that for xtrain I have written fit transform, and for the xtest I have written transform. Why this difference? We'll understand about it. But see, this is the code you have to write to scale the xtrain and xtest. So what I'm doing now, I'm taking the xtrain data, the training input columns, 80% of that I'm scaling, and I'm storing it to a new variable. I could have stored it back into the same variable, but I'm storing into a new variable. Okay, so that my original variables are safe and secure. This is done. If you do this much, you have done the scaling of the data. After that, let me show you one last part, which is applying logistic regression on the data. Let me show you why we have done the scaling and where do we see its benefit. Come back to that. Okay, now I'm going to do the final part where we take the logistic regression class and we make an object of that. And then we say logreg dot fit, and we mention x trained, y trained. See, for now, I'm showing you that I'm using the x trained version, not the scaled version. Let's say if I just use the original x trained, the non-scaled version, what is the problem? You see, so what we have done logreg.fit xtrain ytrain. Here, once this part is done, see it is giving us a warning, ignore that for now. So the thing is, here we have run the training part and we have found our M1, M2 values and C value. So if you want to see that, you will just say logreg, that particular object, dot coef, that dot coef underscore, and then you say logreg dot intercept underscore. This is my M1 value, M2 value, M3 value, M4 value, M5 value, like this. Right, so these are M1, M2, M3, M4, these values. Now, instead of that, if I now use, you see, M1 is 0.01 minus 0.97, 0.90, and you see the intercept is coming out to be very small, like 0.0044. But what I do now, I will make it xtrain scaled. And then I will train it once again. And then I'll say coef, and then I'll say intercept. Now you see those numbers changed. So earlier the intercept value was becoming very, very small, like 0.0044. Because of some column being larger and smaller, it became like that. Now, if you see your M1, your M2, your M3, your M4, all these numbers are properly understandable to you. How much is the weightage being given to each column? What does the negative means? M2 is negative, means the second column is impacting the output in the negative manner. Means whenever the X2 is high, the output is low. Correct. So now you can see that all the M1, M2 values are visible to us properly in the proper scale when we have done the scaling of the data. So you can just try again before and after, try xtrain and then try xtrain scaled. You'll see the difference in the M1, M2 values which are visible to you. Right. Now coming to this part, when we say logreg.predict, here what we should mention, if I'm using the xtrain scaled version here, is it okay to use the xtest? No. Right, no. So we should be using xtest scaled. Because if you have taught the algorithm the scaled version of your data, why would you use the actual version? See, so it means this. If you're thinking why scale the testing also, see, suppose first three rows are our training row and last two testing row. Does it look good, or is it okay that if I scaled these to 2.5, 4.8, 1.3 in these version, and then I'm using the X test in this, will it make sense? No, because you have taught your algorithm on the scaled version of your area. Then how can you give the original version or the original range of the values for the testing? It won't be able to understand that. Okay, it will not be able to do. So if you have scaled this, then this also you need to scale. Got it? So that is the thing. So when I am scaling X train, what I'm scaling, this is our X train that I'm scaling separately, and this is our X test. This I'm scaling separately. Simple thing. This is our X train, this is our X test. So we scale them separately, not together. What is the reason? There is a reason of data leakage. We'll discuss about that. But for now, we scale them separately. Now, so we have got this X test scaled and we got the Y predictions. Now, here what we use, here we are going to use a function called as accuracy score to compare the Y test, comma the Y pred. We use the R2 score in the linear regression, but here we are using the accuracy score. Why we are using we are using another function here? Why not the R2 score? Because the comparison of the Y test and Y pred is different here compared to that. There we were predicting the prices. Y test and Y pred were like the prices. And here our Y test and Y pred is both 1010 like that. Okay. So now notice one thing. Notice one thing. What is your Y predict? So it is saying that the first output is predicted to be 0. First testing row is predicting it to be 0. Second one predicting it to be 0. Can we also see the probability with which it is predicting all those things? Will I also be able to see the probability for that? Is it possible? So answer is yes, because it is using those probabilities to finally convert them into zeros and ones. So it is possible to see the probabilities also. Let me show you how. So you have to say logreg dot predict proba. Yes, there is a function for that known as predict proba. And here we need to mention our X test scaled, and it will give me the probabilities. Now let me show you the probabilities. Sorry, probabilities. Notice this. So this is the column of 0 and this is the column of 1. Right. For the first testing row, what it is saying that the first testing row has 99.18% probability of being 0 and this much probability of 1. So definitely the probability of 0 is higher. That is why finally converted to 0. So we have a cutoff of 0.5. So 0 is more than this cutoff. Means in simple words, you see the probability of 0 is high. That is what our model is predicting. So it got converted to 0. Second row, you see the probability of the second testing data being 0. The probability of output of the second testing row 0 is 93.43%. And of it being 1 is just 6.5%. So it finally converted to 0. Third one. So third testing output is 8% probability of 0 and 92% probability of 1. So converted to 1. So you see, it is calculating the probabilities of each testing row, what is its output should be, and then whichever has the higher probability, it is finally converting into that. Right? I hope this is giving you the idea. Perfect. So one last thing for you now, how we have calculated this. See, so we have something called as a confusion matrix, which is this. And on the basis of confusion matrix, we get the accuracy score. So if I have got an accuracy score of 83%, how did I get that? Is this. We have Y test and we have the Y pred. Right. So we were comparing Y test and Y pred. Suppose in my Y test, we have values like 1, 0, 0, 1, 1, 1, 0, 0, 0, 1. Let's say these are my Y test. These my model has to predict correctly. The more it corrects correctly, the better is the performance of the model. The better is the accuracy. Now what my model has predicted is 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 0. Okay, so my model should have predicted these with its learning that it has done, but it has predicted these. So something it will predict right, something it will predict wrong, but we want the wrong predictions to be as low as possible. Now, on the basis of this comparison, we can write these four values, just 5 minutes, and you will understand this. This diagram in front of you is known as a confusion matrix. So you see on the left side, we have the actual. Actual means Y test. And positive means 1, negative means 0, negative means 0, positive means 1. Predicted means Y pred. So now you see what is it here. When your actual output is 0 and you are predicting also that to be 0 correctly, this is known as true negative. TN, true negative. Negative means 0. So you are correctly predicting the negative, which is this. Actual output is 0 and our model is also predicting 0. This is known as true negative. Okay, negative predicted negative correctly. Negative does not means minus. Negative we are representing to 0. The second one, when your actual output is 0, but you're predicting that to be 1, actual output is 0, you are predicting that to be 1. This is known as false positive. It is actually negative, but you're falsely predicting it to be positive. False positive. Third one is positive 1. The actual output is 1, but you are wrongly predicting it to be 0. This is what? Actual is 1, actual is positive, but you're predicting it to be negative. So that scenario is this one. Yes, this one if you see. My actual is 1, predicting 0. So actual it is positive, we are falsely predicting it to be negative. That's why false negative. And then the last one, actual is 1, predicting to be 1. Means true positive. Actual is positive and we are correctly predicting that to be positive, true positive. Now we have to write the count of these things that we have written. So by the comparison of the Y test and Y pred, how many TN cases we have? How many true negative cases we have in our data? Just last few things. How many true negative cases that? Yes. So true negative cases are 0 and 0 both. 1, 2, 3, 4, and 5. 5 cases are there of true negative. So count of true negative in this is 5. Count of false positive. Count of false positive here. Just 2 more minutes. Count of false positive is 2. Means actual is 0, predicted to be 1. So actual is 0, predicted to be 1. Actual is 0, predicted to be 1. These two cases are there. 2. Correct. Now the count of Fn. where the actual is 1 predicted to be 0. There is this case, and then there is this case. 1 0, 1 0. And is there any other third case also? No, I think 2. And then the count of TP, true positive, where actual is also 1 and predicted also 1, 5. Right. So total we have 14 rows in this, means 14 y-test value, and we have 14 predictions. So the formula of accuracy is TP plus TN divided by TP plus TN plus FP plus FN. The formula of accuracy score is all the true predictions, all the correct predictions divided by all the predictions. So these both are our correct predictions and these two are our wrong predictions, the mistakes that we have done. So accuracy score is nothing but all the correct predictions divided by all the predictions. So out of 14, 5 plus 5, 10 we have predicted correctly and 14 we have predicted overall. Right. So 10 by 14, when you solve this, it will give you your accuracy score. Right. So this in front of you is known as confusion matrix. In the confusion matrix, we will find out these 4 things, and using these 4 values, we will be calculating the measures of classification, means the performance metrics. I have shown you today accuracy score, but the upcoming sessions, we will talk about other metrics also, which is precision score, recall score, F1 score. We will be talking about other metrics also here. Right. Like in the regression, R2 score was our main metric to show the overall performance, but RMS was basically extra information you get. Same way in classification also, accuracy score is your main metric, which shows you the overall performance. But we have to check at other scores also, precision score, recall score, to get more information, in-depth information about the performance of the model. We will discuss about this. Just I have given you an initial idea for now to understand this much.
We will be working on a concept called as decision trees. We worked on linear regression and logistic regression. We saw some of the theoretical aspect of that, and we saw some bit of practical. But now we are going to move forward and we'll work on few other concepts that is going to be little more powerful compared to what algorithms you have seen till now, right? So without wasting much time, let's get started and let us see how this concept works. Okay, now, so the name of the algorithm is decision tree classifier. So decision tree is the main one of the main algorithm of classification, but now there are some updations done in decision tree. Because of that, decision trees can be applied on regression also. So by default, or mainly, it was a classification algorithm, but now it has been made to work on regression also. So we will try to see the examples of both. How can you apply trees on classification and regression both, right? First, let's focus on the classification part. How does it work? And if you understood the working of it, then very small changes we have to make it work on the regression also. So now let's get started and let me explain a few things to you. Now, suppose we have some data set here. So what I'm doing now, I'm just taking a data set of classification and I'm plotting that. When I plot a classification data, suppose the data looks like this. Now, every dot here represents one row, right? And if this is a data set for heart disease classification, so I'm saying that, let's say this is the blood pressure, right? This is the blood pressure, and this is the chest pain level, CPL, chest pain level we have on y-axis. So every dot that you see is representing one person whose blood pressure we know and whose chest pain level we know, that how much chest pain they were suffering or they were facing when they came to hospital for the checkup for the first time. Now, the hospital has collected this data about every person who came to them for the checkup, and this is the information you see. So all the dots are representing one person, one patient or a healthy person, but one person. But how have I colored these points?
So the dots that I create, it is on the basis of input, right? Input rows or input data points, the information which is present in input columns only, we use that to make the dots, input data. But how have I colored that? So on the basis of the output column, I am able to color the dots, telling that which was a healthy person, which was a heart disease person. I have given two different colors because I know which data point is representing a healthy person or a heart disease patient, right? Now, what is the task of a classification? In the classification, what is the main thing that we focus on? So you have seen already that the main thing that we focus on is creating a decision boundary, right? We have to make a decision boundary. That is what we do. And you can see that some points are above that, some points are below that. That is the thing. And let us say that these are all healthy people. These are all healthy people. And these are all the heart disease patients, right? Healthy people, heart disease patients. So all of these are heart disease patients. Why? Because you can see that if you pick any data point here, their blood pressure is also little high and their chest pain level is also high. So that is why they were uh, found to be a heart disease patient when they came to hospital. So this is what we do in classification overall. Take the data points, plot it, and we have to make a decision boundary to separate the data point. In regression, what we do? In regression, we pass a line through the data points so that all the data points are close to this line. We always pass a line through the data in regression. But in classification, we don't do that. We try to make a line which can separate the data points into multiple sections. So here, if I have to create one decision boundary, I can use logistic regression for that you have already studied. So logistic regression is very good enough for making a single decision boundary wherever it has to be created. That is good for that. But now let me show you another situation that if you take a data and if you plot it, and if you saw a situation like this, that some of the data points are here, some of the data points are here, some of the data points are here, and some of the data points are here. Now, in this case, can you make a single decision boundary to separate the data points into their particular sections? Because what we have to do, we have to put these data points into separate sections so that there is a very little mixture of the data points. They should have a very clarity in whichever section it is put. We should have a clarity, right? So here, if you see that above the decision boundary, we have all the green points. So in future, if any points come here, then I will say that since it is above this line, so then this dot will also represent a heart disease patient because it is above this decision boundary line. And if there is any point which is below this decision boundary line, I'll say that this person is going to be a healthy person uh, because all the other people in this area have been healthy, right? Now, so we have a clarity of that answer that we can make that prediction. But in this, is it possible to make a single decision boundary to separate that? So the answer is obviously no. If I try to do this, or if I try to do this, or if I try to do this, whatever I do, can you separate it with a single decision boundary? Of course not. It is not possible, right? So then what we should do in this case? One is not possible, then what I should do? See, one I can create here, or you can say, let's make one decision boundary here. And let us say we will make one decision boundary here. Now, in this situation, I have to use two decision boundaries to separate the data point into particular sections. I have to do that. I have to make the separations possible using two decision boundaries. But the thing is that logistic regression cannot do that, right? Logistic regression cannot build, logistic regression can't build more than one decision boundary if required, right? So logistic regression can't build, even if it is required to build more decision boundaries, it cannot do that. So that is why we are now going to study a bit more advanced algorithm, which is compared to logistic regression, little more powerful. And that algorithm has the option to, or has the capability of making multiple decision boundaries required. How many? Infinite. If you require 10 decision boundary, 100 decision boundary, 1000 decision boundaries, that this algorithm can make any number of that we are going to study today, decision trees, right? So before we started, I have given you a small idea that what is the limitation of a logistic regression and why we need to move forward to another algorithm, and we should know about that, right? So let us see the working of decision trees. Now, suppose we have a data like this. We have a bunch of data points that I've plotted here. How did I plot this? In this case, I'm taking another data where one column is income of a person and one column is age of the person, and the last one is our target or the output column. So in this, let's say there is a first person whose income is something, age is something, and they were defaulter. Defaulter means that a bank has this data set identifying that in the past, who has taken the loan from us and who was able to pay it back and who was not able to pay it back. Because you know that every bank has to earn money through the loans. That is very profitable for them. When they give the loan to someone, they give it at a very high interest rate and they are able to make good amount of money from that. So they have given lot of loans in the past, and they know that which person defaulted means they were not able to return the loan back, and who was non-defaulter. Non-defaulter means the person who was able to pay the loan back. Correct. So now we have 0, then 1, we have 2, then we have 3. You can see that I am just taking 2 input columns for now, because if I take 2 input columns, I can make a 2D graph. And if I take more than 2 columns, it will make a 3D, 4D, which I cannot visualize. I cannot show to you. So here we have 0, 1, 2, 3. Let's say we have this defaulter, non-defaulter. Then this is also non-defaulter. Let's say this person was a defaulter. So we know the income and age, and we know that who was defaulter or not defaulter. So the dots that we make here, the pink color dots and the blue color dots that you see, the dots will be created on the basis of these input columns only. Because if I have put a dot here, how did I put a dot here? Because there was a person in my data whose income was this much and whose age was this much. It was present in the data. Particular age or particular income, I have plotted that person with a dot here, that row with a dot here. But how did I color that with blue or pink color? So I said that if I make a dot and the label of that dot was a defaulter, I am going to color that in pink color because it is of one category. It is one type of people. And the other one, I'm able to color in blue color. So those rows, if I have made a dot of this particular row, let's say this is a dot representing this row. I know that this person was a non-defaulter in the past because it is given in my data set. It was non-defaulter, so I colored that into blue color to represent that as non-defaulter, right? So whenever I plot the data, right? So whenever we plot the data, then what happens in that? You have to see that you will be plotting the data and you will be doing the coloring of the dots on the basis of that, on the basis of output column. So in this example, I've taken 2 input column and output column. So using input columns, we make the dots, and using the output column, we color that, right? Now, so what you have to understand is that will we have just 2 input columns? If a bank has to make this model, this machine learning model, and the bank has to identify these things, will the bank only consider the income and age of the people to make this model and to do all of these things? Will the bank just use this 2 column? No, of course not, right? So apart from that, we can use lot more other inputs also, such as the number of dependents of the person, and then are they employed, not employed, or you can say, do they have any existing loans? What is their CIBIL score? What is um, how many years they have been working for, means what is their employment age? That is the thing, right? So when any bank has to decide this thing, that how the model will be built, logistic, decision tree, whatever, so we use lot more columns. But here we are taking 2 columns so that I can plot it. I have already discussed this thing, right? That I can take 2 columns, then I can represent that as a graph. Otherwise, for 3 column, it will become 3D. If you remember, I have shown you one graph which was in higher dimension. where we have seen a plane instead of a line. And I told you that in when we have multiple columns, then we have a very high dimension, right? You remember that. And I cannot plot it because it's a very high dimension. It is not possible to plot that. So for the example purpose, we are taking two columns to understand it. Now say that I have plotted this data and we are looking at it, right? So now the thing about the decision tree you have to understand that decision trees can work on a very large data. You can take a data which has 200 input columns, 500 input columns, 1000 input columns also. Decision trees are very capable on working of that on any size of data. Compared to logistic regression, they are much more powerful and they can work on a variety of data and very big size data also. And generally, whenever we are working on decision trees, we take a very large data to work on that because decision trees are so much capable. So we try to use that on large data to properly use its power, its capability. Correct. But now see, for this example, I've plotted the data. What is decision tree going to do for us? One thing you have to remember, decision tree basically will help us to make multiple decision boundaries, which is not possible using the logistic regression. Logistic will take any data and it will just say that I can make only one decision boundary on that. It cannot make more than one. But in real life situations, the data will be so much complicated in many situations that one decision boundary will not be enough for that. And you will get a very bad accuracy if you use use logistic regression on that data. So here comes the concept of decision trees, where what you will do, you will take a data and you can make multiple decision boundaries to separate the data points. Okay, now, so what you see here, just take an example for now. I will explain that here. Take this example. In this example, I have taken a data and I have made multiple lines here, right? This line, and this line. We have made 3 lines here. And these are 3 decision boundaries that I have created. And I have separated the data points into their particular sections. So is it doing a good task? So we say, yes, it is doing a good enough task. It is not 100% accurate. It does not have to be, but it is doing a good enough task to identify that. Now, once we make multiple decision boundaries here, we convert this structure to this kind of structure, which is called as a tree. This structure that you see in front of you is called as a tree. So how this tree will be built? This tree will be built using this concept. First, I have to take a data. I have to make multiple decision boundaries. Where exactly we are making a decision boundary, at what place, using what value. Using that, I will be able to build a structure like this. And this structure will be more understandable to us. Correct? Why 2 things we are making? So this structure is for us. If I have to understand how the decision tree is working, I will print this structure for us, right? For human understanding purpose. But when the model has to use this thing for future prediction, the model will use this kind of structure for its understanding. Because this is more understandable to the model because it's a mathematical concept, but it will become little difficult for us to understand. In comparison to that, we will be making this structure. So what you have to understand that both the structures will be created. This will be created in the background and it will be used by the algorithm. Where in the background? When I apply this decision tree classifier algorithm on a data set. So this is what is going to be created in the background as a model, but it will not be shown to us, right? This structure cannot be shown to us because if you have 50 columns, input column, let us say, then the graph will be 50 dimension and that 50 dimension graph cannot be shown to us. So this kind of graph is created in the background, but it is not shown to us. It is not possible to display that. So instead of that, what we say, okay, no problem. Represent that as a tree. This is a tree structure. This tree can be printed for any dimension of data. If you have 50 input columns or 500 input columns, you can print a tree anytime from the model and you can understand this. You can look at this and work on this. So how it is getting created, let us get into details of that. And let me explain that to you in a very simplified way. How are we going to create these structures? Let us see. For that purpose, let me just take the data. Okay, right. So looking at this data, what we have to now think is, should I apply logistic regression on this or should I apply decision trees on this? So if I apply logistic regression on this, then what I will be able to do is I will be able to make a straight line which will separate this data point, one single line. So I can say that if I'm making a line something like this, so is that enough? Is it dividing my data points into two sections good enough? Not saying it has to do this for 100% accurately, right? Correct? We have to do this. But the thing is, can I use a better approach where I use more than one decision boundary to make it work even better? Can we do that? So you see that if I'm using logistic regression on this data, then it is working comfortably good, right? It is good enough because only 3 points are in the wrong section, and here these 2 points are in wrong section. It is okay, no problem. Whenever we are making this decision boundary, then it will not happen that all the points are in just one section which are of the same type. It will not happen. There will be some points which will go in the other section. It is not a problem. Just what I have to make sure that most of the points in one section should be of the same type, right? As high as possible, there should be more clarity in one section of one type of data. Correct. So this is working well enough. But now, if I say that, okay, this is working good enough, but suppose I have a data set in which one line was not enough. So there we would make multiple lines. So let me show you that if in the same data set, if instead of making one decision boundary, if I try to make multiple decision boundaries using decision trees, how will I do that? What is the approach I'm going to take to make proper decision boundaries in that? Right. So now, what is the concept here? That how do I decide where exactly the line has to be created? Let me show you the first line I'm going to make somewhere. So the first line that I'm going to make is going to be here. Let us say I have started with this income parameter, right? First line that I have made here is at this particular value, which is on the basis of income. So what I'm doing now, I'm dividing my entire data into two parts, here and here. And on the left side, we have one type of data, and in the other side, we have another data points. But you see, I'm dividing all these people, all these data points on the basis of income. Let us say that this income value is 21K. So I'm saying that let's divide the data on the basis of income in two parts. The people who are having income less than 21K and the people who are having income more than 21K. But you would say that why did I make a line here? What was the purpose of that? What was the need of that? What was the motivation behind it? So we have to make lines which bring or which makes my data more homogeneous, right? In the start, we had all the mixture of data point in that. Before I have made any line, so we had mixture of data points, right? If you see, if I say that I won't make this line, so what will happen here? If you take, let's say, any future data points, let's say this is a person who you don't know will default or not. You have just plotted it here, and you have just plotted it here, taking this person's income and age. Let's say in future, this person comes and you are able to note down its income because you can ask that person and you ask their age. Correct. So here, the thing is that when you take this data point, would you be able to identify? So when you take this data point, then what happens is, take a look. Would you be able to tell whether this person is going to be a defaulter or not defaulter in the future? If you take a look at this data point, I don't have any decision boundary as of now. So will you be able to tell clearly or with confidence that this person will default or not? Can you tell that? I don't have any decision boundaries at this point. I've just taken the data and I'm representing one of the person in future, that this person is coming to the bank and they are saying that my income is this much and my age is this much. I want a loan. So should the bank give this person a loan? Is the bank confident that this person will default or not default? Are they able to identify? So see, the bank will not be able to decide this. Why the bank will not be able to decide? You see, because in the entire structure, we have lot of red points also, we have lot of blue points also. Means in this data set, the data set the bank has, lot of people have defaulted in the past and lot of people have not defaulted in the past. So just by looking at the credentials of a person, they won't be able to just tell directly whether this person will default or not default, right? They won't be able to tell that, or they won't be able to identify that. So here, there will be a person who will have to sit down to do these things manually. Maybe after a person spend 2 days, 3 days, and they do a very extensive study of that, maybe they will be able to tell, right? Maybe they will be able to tell. So the problem is that it will take a very long time if I have to do this manually. Correct? It will take a very long time. So instead of that, what we do now is I'm saying that we are going to now make decision boundaries first, and we are going to separate all the data points on the basis of something. So what I do, I will now start to make the decision boundaries. I am now bringing machine learning into the picture. So machine learning will learn the patterns present in the data, and then let us see that will the machine learning help us in identifying this data point or not. See, so the first line that I'm making is, let's say here, which was on the basis of income 21K. Now, so here you have this line which you are using to separate the data points onto left and right side like this. But why did I make a line here? What was my motivation? You see, the motivation is that I have to make these sections more and more homogeneous. What do I mean by homogeneous? So the thing is that if I make a line here, am I getting one answer or a clear answer on at least one side? Right. By making this line, on right side, there is still a mixture, but at least on one side, are we able to make a homogeneous structure or homogeneous decision? So we say yes, because if you look at the left side of this line, we have all the customers here who have defaulted in the past. Red points are defaulters, blue points are non-defaulters. So we have this structure where you see that on left side, we have all the data points who have defaulted in the past. And how did I color these dots? I have explained that, right? Everyone understand this? I've explained that in detail properly. So here we have all the pink points, which are defaulters. So now, if I get any point in the future on this side, will I be able to predict very correctly at this point that what this person will do, right? If tomorrow a person comes and that person's income is this much and age is this much, will I be able to tell? Yes, in this case, now I will be able to tell, because we have learned this thing from the data that behind this or below this age, the people have defaulted in the past. So in the future also, if there is a customer like this whose age and income is behind this line, so they will also default, since that is the pattern that has happened in the past. So same thing will happen in the future also. That's the idea. But on the right side, you see, there is still a lot of mixture. So do I have to make more lines? Yes. The right side part is not yet sorted. I have to make more lines to make it little bit more sorted. So where will I make a next line? So let us see where I can make a next line to make the data more homogeneous, to bring more clarity where I should make the next line. So suppose now I decide to make a line somewhere here. As I make this line, am I bringing more clarity to the data? Earlier on right side, there was a lot of confusion, but is it helping it to bring more clarity, more homogeneousness in the data? Yes. So if you now see that, if I make a line here, on the bottom side, we have all the blue points. Means on the right side of this line and on the bottom of this line, in this section, most of the points are blue, just one red point is there. So you can see that we have a very clarity of the data point here. So in this case also, if tomorrow, let's say a person comes and their credentials are like this person's income is this much and this person's age is this much, this person will be considered a non-defaulter. The predicted value for this will be non-defaulter, because it has been observed that the people who have income more than 21K and the age less than what? So age is now on the basis of this value 40. So it has been observed in the past that someone who has the income of 20K, 21K, greater than 21K, and age of less than 40, they have not defaulted in the past. Mostly. One person was there who defaulted, who was not able to pay the loan back. But other people who have taken the loan, having this criteria, they have been able to pay the loan back. So since most of the people have behaved in a certain way, then we will predict that same thing, the majority value for this person also, that this person will also be non-defaulted. But now this section remains, right? Notice that what we have done, we have created two clear sections now, this one and this two. Two sections now I have, but now I am still remaining with this. In this section, still there is a lot of confusion at this point. So where should I create a line now? Should I create a vertical line or should I create a horizontal line next? In this section, I have to decide now. Not between 50 to 60. No. Income 50 to 60 is not correct. At some other place I have to make, not at 50 to 60. You see, if I make a line between 50 to 60, what am I achieving? Nothing I'm achieving. On this side, we have all the mixtures. I'm not achieving anything at all. So it is not at all correct. Where should we make a line? So in this section, you see, in this section, I can make horizontal lines like that, or I can make a vertical lines like that, right? Yes. So where should I make a line here? Will it be correct to make a line at this place, right? Is it good that if I'm making a line here, does it look good? That on this side now, we have section number 3, in which most of the data points are red and just one point is blue. So is this a good split that I have done of the data, a section I've created? Yes, we can say yes, definitely looks better. And we should go through that. Now this remains. In this one, still we have a lot of mixtures, right? We have still a lot of mixtures here. So what I need to do, I have to make one more decision boundary I have to make here at this point. So I have now a section number 4 and a section number 5. Is it now sorted? You see that now we have these 5 sections I have created in the data. So does it look better? Of course, it looks better compared to what we started with. We had all the data points scattered and we did not know that what I should do with that. So in the classification, we have to make decision boundaries to separate the data point into particular sections, right? So the thing is that I have made decision boundary 1, decision boundary 2, decision boundary 3, and decision boundary 4. It required me 4 decision boundaries to properly separate these data points here into particular sections. And because of the 4 decision boundaries, I'm able to get 5 sections if you see here. Now, in this case, if I suppose take a new person, right? Let's say someone comes in future and then they are asking for a loan. Right. So bank will have to decide whether this person will default or not default. So what I do now, I take a person whose income is, let's say, 53K and their age is 42. What will I tell about this person according to this graph that we have created, according to all the sections and decision boundaries we have created? What will be predicted value of this? So first, I'll try to represent this person as a dot, right? 53K, income 53K and 42. So in this section, somewhere here, you will have a cross representing that this person has income 53K and has an age of 42. I will make it here. But now where is this person falling? Now, see that. So this 53K and 42 is a person whose cross is being represented here. In which section this cross is falling? In section number 4. In section number 4, you see that these all people have been non-defaulters in the past. When these people have taken loan in the past, they have returned the loan back to the bank and they were non-defaulters, right? They were non-defaulters. So what will the bank predict for that? Or what will this model predict for this person? That this person is also going to be non-defaulter. There are very high chances. We cannot say for sure. But from the historical data, from the past data, we can say that this person is not going to be a defaulter. That is what we can predict for now, according to the past. So this person will be given a loan because we have predicted that this person will return the loan back. This person will not be a defaulter. Correct? Now this structure we have created, as you can see. Here I have taken 2 input columns only, income and age. Because when I take 2 input columns, I make a 2D graph. And this is a 2D graph that you are seeing. I can plot that and I can show that to you. But if there is 50 columns, then there will be a 50 dimension graph. And in the real world, obviously, you will be working with 50 input column, 70 input column, you are not going to work with 2, 3, or 1 input columns. You'll be working with a very high amount of input columns to do all of these things. So if a graph is 50 dimension, we cannot visualize anything above 3D. Means if a data set has more than 3 columns, I cannot visualize that. It is not possible at all in the real world. Whatever you do, never you can visualize that. We don't have any technology to visualize any data further from or higher or having higher dimension as opposed to 3D, more than 3D. We cannot visualize, not possible. So I won't be able to see this kind of graph, correct? I won't be able to see because it is going to be 50 dimension. It will be created in the background by the mathematics, by the algorithm, but it cannot show that to us. So let us build a tree which I can see, right? Let's create or convert this structure into another structure which I can visualize anytime. It does not depend upon or it is not limited by the dimension. It can be built, it can be seen anytime, no matter whatever amount of input columns are there. So I have to make a structure like a tree. Let me show you what is a tree structure. A decision tree structure. Let me show that to you. Yes. Now, have a look at it. So the tree is called like this. You know that tree has a root, branches, leaves. That is what the terms we will be using here also to understand that. So tree is a structure where we start with a single value, single point, and then we go on multiple sides. So if I go on this side, then we have another point here. Then we go on this side, then we go on this side, then we go on the right side, then we have one point here, then we go on this side, then we go on this side. From here, we are going even further like that. So basically, it has a structure like this, that we have this, then you are breaking it down further, you are breaking it down further, then you are breaking it down further, you're breaking it down further, like that. This kind of structure we have, correct? And when you look at the structure, then there are few terms you have to know in the case of decision trees. What are those terms? These dark blue colors that you see, these dark blue color boxes that you see, this one and this one and this one and this one. These are called as decision nodes. Okay, these are called as decision nodes. So if from a box, if you're going further and you are continuing the tree further, see, as I started from here and I'm continuing the tree further, I'm building further things on top of that. So those boxes are called as decision nodes. But there are few boxes you see here, this one, this one, this one, this one, and this one. We are not building any tree from anything after that. From here also, we are not building anything. From here also, from here also, from here also, from here also. These are final boxes that we have, after which we are not building anything. We are not continuing the tree further. But you see, after this, we are continuing that. After this, we are continuing that. After this, we are continuing that. After this also, we are continuing that. So from a point where we make the further tree, those points are called as decision nodes. We have taken some decision there, and on the basis of that, I made further tree, right? Now, what are these leaf nodes? Why are we not making anything further from that? Why did we stop the tree here? Or why did we stop the tree here? Why did we stop the tree here? The leaf nodes are the points in a decision tree where we get the final answer, and we have got the final predicted value here of defaulter, not defaulter, yes or no. That is why we don't build the tree further from that, because I've already got the predicted value from at this point. So leaf nodes are our final points where we get our answer, the predicted value that we are supposed to get. Leaf nodes are those points in a tree that gives us the answer. And decision nodes are nothing but all the decision nodes are going to be built on the basis of a decision boundary. So I made one decision boundary like this. So it will create one decision node. I made another decision boundary. It will make one more decision node. I make one more decision boundary. It will make one more decision node. I make one more decision boundary. It will make one more decision nodes. So all the decision nodes that I'm going to make is going to represent a particular decision boundary that I have created in my data. So whatever amount of decision boundary, that many decision nodes will be created for you. And when we get the answer, that is our final node. After that, nothing will move forward. So every point here is called as a node, but some of them are called as decision nodes and some of them are leaf nodes. So leaf nodes are our final points. But you see, the first decision nodes where this entire structure is starting to build, that is given a special name called as root node. This is a decision node, but this decision node is a special decision node, and that is why it is called as a root node. Only this one, because the tree structure is starting from here. So from where you see the starting of a tree, in real life also you see that the tree has a root, which is the base of that tree. From there, the tree has started to build itself. So from the first point where we started to build the tree, that is called as a special decision node, and it is known as root node. Rest of them will be called as normal decision nodes, and the final one will be called as a leaf nodes, where we are getting the answer. Now, in the tree, there would be multiple subtrees that you can take. Like here, if you take, what is this? This is a branch. This is a branch. That in the tree, if the tree is going like that, you see that this is branch, this is one branch, then you have further branches, further branches, further branches, further branches. Like that, it is going to build all of these things. So when you see the structure here, it is starting from here, then it is going in two different directions. So this is one branch and this is one branch. It is like broken into two different sides. It is going to two different sides, branches. Then if you see here, can I consider this much part as a small tree inside a bigger tree? Can we consider this branch as a small tree inside the bigger tree? Yes, we can say, right? In a simplified terms, we can say that all the branches that we have, if this branch is very big, I can say that it is a tree in itself. It is a sub-tree inside the main tree, right? We refer to these things like that. So same way in the decision tree also, this much part of the tree can be considered as a tree in itself, a sub-tree in itself, and it will be called as a sub-tree because the main tree is the entire tree. So it is a sub-tree, a small tree inside the bigger tree. And why am I considering it as a subtree? Because you see that a tree has what? Start from the decision node, end at a leaf node. Is it starting at a decision node and ending at a leaf node? Yes. So this can be considered as a small tree inside the bigger tree. Then we can consider this also as one tree because starting decision node, ending at leaf node, ending at leaf node. Can this also be considered as a small tree in itself, this much? So we say yes, this also can be considered as a subtree, starting at decision node, ending at leaf node, right? So we have multiple subtrees inside a tree. We can have that. And what we are doing here, when we are going into multiple directions, these are branches of a tree. That from a point we are moving into two different directions, two different branches are separating from a tree. So this is the structure we have. And now in the tree structure, when the tree becomes very large, so sometime we have to cut down one of the branches. Let us say the tree became very large and you see that it is becoming very, very large. But now the point is that this branch was created, let us say, this branch was built or it grew into the tree. But because of this one branch, it is now so much heavy that the tree is tilting on one side because of that. And there are chances that this tree will break because it is tilted for 24 hours. It is tilted on one side because of that. It is heavy. So to protect our tree, we can cut down this branch, just this branch. If it is extra, if it is too big, and because of that, if there is any problem in the tree, I can cut down few branches. Same way, in the concept of decision trees also, the decision trees will create some extra branches unnecessarily. And why will that happen? I'll explain that to you. But it will make some branches unnecessarily, and we have to cut down that branch sometime. So what I will do, I will cut down this entire branch, not here, here. So when I cut down this entire branch, this entire thing will be gone. It will be deleted from the tree, and I will not be using that part to make the final prediction. Now, why we will cut down? How do I know that this branch was a problem? Why I did not cut this? How do I know all of these things? I'll explain everything here. That how to decide what will be written here, what will be written here, what will be written here, what will be written here. Everything I'm going to show you within just few minutes. Those are very simple concepts. But first, you have to understand the structure of a tree, right? So to simplify that, again, I'll show you in the circular manner that will make it simple. You see. So whatever I've shown you just now, it was like this. That will be a little easy for you to understand, right? So in this structure, this is our decision node. 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 This is our decision node, right? So from where we are, if we are moving forward from any point, that is a decision node. But you see, we did not move forward from this. We stopped here. So which means that it is a leaf node because we are not building the tree further from this point. It's a leaf node because we got some answer here. The output we got here, that is why we are not building further. Because we have to get the output, we got the output, then we stopped. Then this is also leaf node. This is also a leaf node. This is also a leaf node. This is also a leaf node. And this is also a leaf node from a point where we are not moving forward. So this decision node is a special decision node, which is called as root node. And these are called as branches because it is splitting my tree into different parts. It is taking me there. So these are branches, these are branches, these are branches of a tree, which is taking you in different sites. Now, we have all of these things. And apart from that, we see that I can cut down some branch. This process of cutting down some branch is called as pruning. But on what basis I'm going to cut it? How am I even going to identify that? We will see. Everything I'll show you, I'll make it 100% clear to you that how all of these things will be done. So we can cut down some branches, and cutting down some branches is called as pruning process, which is a very important process in the decision tree. If I don't cut these extra branches, it will create a very big issue in my prediction. It will create a lot of wrong predictions in my model if I don't cut down some branches. And why am I cutting these branches? Because these were created unnecessarily. They were not supposed to be built, but my decision tree has made them unnecessarily. So how do I identify all of these things? We will see. Okay, so I hope the structure is clear of the decision tree. Let us now convert this one into a tree that we have just now built. Right? I hope all of you got the fundamental idea. Now let me show you how to build a tree using this. Then you will be even more clear. It's a very simple concept. So how will I make my decision node? Right? The first decision node which was there, which was root node. How do I build that? What is the concept used to build the first decision node, which is my root node? So it is nothing but on what basis did I make my first decision tree? You see, a decision boundary. The first decision boundary is this one, which is built on the income value, right? So either I will make a line on the basis of age, or I will make a line on the basis of income. The first line I have created in this case on the basis of income. You see, this line is touching the income line. It is not touching the age line. So it is touching the income line, and the first boundary was created on the basis of income. So I said that a boundary gets converted to a decision node. So the first one I will mention is the income. So decision nodes will be nothing but it will be name of the input columns that you have in your data. All the decision nodes will be the name of some input column that you have taken to make the tree. So income is the first one. But what I have to do, I have to then go into two directions. Why two directions? Because if you see, this line has broken my data into two sections, one left of it, one right of it. If it has broken down my data into three sides, then I would have made three branches here for three sides. But in this case, it is splitting my data into two sides, one left of this income and one right side of this income. So on the left side of this income, what we have? See, so one is less than 21K and one is greater than equal to 21K. Why I have taken this 21K? Because this income value is 21K here that I am using as a branch value. So income less than 21K, more than 21K, I have these two branches that we have created. So on this side, when I have income less than 21K, do I have any answer here? So we say yes. At this point, we have an answer. Correct? We have an answer. So what is happening on this side? We have to create that these people were found to be defaulters, right? These people were found to be defaulters. So directly you see that as I started building the tree, in this case, I got one answer directly. Means if someone has income less than 21K, you don't even have to check anything. Their age, their CIBIL score, their number of dependents. Just understand this thing that we are saying that on the basis of income itself, we have found from the past that they were defaulters if they have an income less than this. Does not matter what was their age, does not matter what was their CIBIL score. It is observed that in the past, the people who had income of less than 21K per month, they were defaulters, right? They were defaulters. On right side, when I'm talking about greater than equal to 21K, what section I'm talking about? So greater than 21K, this entire section I'm talking about, this entire thing on the right side of the first decision boundary. So on the right side of the first decision boundary, do we have an answer here? No, we don't have the answer directly. On the right side, we have built multiple decision boundaries. So which was the second one? You see, the second one is this. On the right side, we have built this as the first one, which you see as line number 2, boundary number 2. On what basis it is built, right? On the right side, the first decision boundary that I have built is this one. And on what basis I have built that? What was the criteria for that? Age, right? So age equal to 40, I have built that too, right? So here I will mention another decision boundary, which is going to be age. And I will say that it is more than 40, means one side less than 40, one side more than 40. So I am splitting my data into two parts like this. Age, I'll say again, let's go into two sides, less than 40 and more than equal to 40. So when the income, you see, how are we reaching here at this point? So the person whose income is more than 21K and age is less than 40. Do we have an answer at this point? So the people who have income more than 21K and age less than 40, which section I'm talking about? Section number 2. And in section number 2, we have most of the points are non-defaulters. Because you see in section number 2, most of the points are blue ones, non-defaulter. So here at this point, we have another answer that this people will be non-defaulters. Then moving forward, so someone's income is more than 21K and age is more than 40. Do I have an answer here? Or what section I'm talking about? Income more than 21K, age more than 40. So now I'm talking about this entire section from here to here. Do we have a direct answer at this point? No, I have to continue the tree further because I have no answer at this point directly. So which is the next one that I have to build? Income. Yes. The third one, you see, the third line that I have. So third line is on the basis of this income, somewhere around 39K, or it is not exactly touching 40. It is somewhat less than that. Let's say 39K, right? 39K. So here I will take this, and what I will do now is I will make another parameter income. And this is my another decision node. So someone's income was more than 21K, age more than 40, and income, again, what? You see, income less than this and more than this. 39K, less than 39, more than 39. Right. So here, income less than 39K and income more than equal to 39K. So someone whose income is more than 21, age is more than 40, but income is less than 39. Means income is more than 21, but less than 39, and age is more than 40. Do I have an answer here? So if you see now that this is leading us to this section number 3. This section number 3 is the people whose age is more than 21K, age is more than 40, and the income again is less than 39K. Income more than 21, less than 39, and age is more than 40. So this is leading to a section number 3 in which we have defaulters, right? So here I will mention these people were defaulters in the past. But on the right side, we still don't have the answer. So I'll build the tree further. On the right side, we don't have the answer at this point. So we say income, age, income. I have taken what I need to do next. So one more I think is required. The decision boundary 4, right? One more is required, decision boundary 4. So this section is still not clear. The section where the age is more than 40 and income is more than 39K, still we have to identify, means one more boundary has to be created in this section. So 4.1. So 4 is on the basis of age, and you see that it is touching somewhat 58, 59, I will say. So age more than 51, less than 51. So here I have again the age, and I'll say less than 59 and more than equal to 59. So less than 59, which people? Less than 59, these people who were non-defaulters, and on this side we have the people who were defaulters, right? So now, are you understanding this structure, how we have been able to create this tree using this graph that I have? Easily you can make that, right? Few things you have to keep in mind, that this structure is for the algorithm. It will build it in the background and it will see that. This structure will not be shown to us because if this structure is 50 dimension, 100 dimension, this structure cannot be shown to us. So instead of that, we try to print this structure. This structure can be seen by us for any dimension. It is not limited by the dimension. Tree I can print for any data, any dimension. It is not limited. So this is for us. Now see, is this structure easy to read for you, or is this structure easy to read for you? Because in this structure, you see that so much hodgepodge is there, and it is so much messed up after creating so many sections and lines. But this is very easy. It looks refreshing and it looks very easy for me to read. Suppose I have a person whose income was 53K and age was 42. Will it be easy for me to predict the value for this person using this structure or this structure? So I'll say that for us, this will be definitely easy, because you see that 53K that I take. So first income, more than 21K, I move in this side. Age 42, I move in this side. Income was 53K, I move in this side. Age is 42, I move in this side. What is this person? Non-defaulter. So from that graph also, I will get the non-defaulter. From this tree also, I'll get the same information, because tree is built on the graph itself, on that concept itself. So this is the structure which is easily understandable by us humans. So that this is what we print for ourselves. And how we will print that, I'll show you the code for that also. Everything we'll see. Now, going to this, also another point you have to remember, we have 4 decision boundaries. 1, 2, 3, 4, 4 decision boundaries are there. And you can see that how many decision nodes are there? 1, 2, 3, 4. The amount of decision boundaries decide how many decision nodes will be created. That is always going to be the case. This relationship will always be there. So one decision boundary, extra branch will be added into my tree, right? That is the thing. So now we have got the structure and we are able to see. And these are all my leaf nodes. This one, this one, this one leaf node, and this one, and this one. These are all my leaf nodes. Because here I'm getting the final predicted output and I'm not building anything from further from that. That is my leaf nodes, right? So we have built that. Now the thing is, we did everything. But now a question that comes to your mind is, why did we not start with age? The first decision tree that I have made was vertical and was on the basis of income. I started everything income. How did I decide that? Why did I not start with age? Right? So the thing is that we will start with income. We will try to build one tree with that. And then we will take age also. We will start with the age and we will build one more tree. Then we will compare which tree is better. The one which is starting with income as the root node, or the one which is starting with the age as the root node. Is that one better or is this one better? Now the tree that we have built here is one of the tree that can be built on this data. So on any data, we can build multiple trees. So on this one, which has 2 input column, I can build 2 type of trees, which is very suitable. And I have to decide out of those 2 trees, which is better. So what we have done in the past, that if I have a linear regression, so in linear regression, we can make multiple lines passing through the data, but only one of that is best. All the lines I will not be using for making the prediction. Otherwise, they will give different predictions. So only one line is best out of multiple lines in linear regression. Same way in the decision trees also, there can be multiple trees on our data and only one of that is going to be best. And we have to identify that Let me first build the second tree and then tell you how do we compare that. What is the point of comparison? Let's take a look. So this is a structure that you see where in the previous case, I started with the first line somewhere here on the basis of this income 21. I started with this, but I will not start my first line from on the basis of income, but I will start it with the age parameter. So when I start with age, where should I start it with? So I will say, let's say it looks better if I make the line here, right? Okay. Also, this is better, means you can start here because if you start here, you are getting some clarity very clearly, right? Let's say somewhere here, I have to move it little up. Yes. Let's say that we have a line here. Now, this is on the basis of age 60 and above. So above 60, you can observe that you have a clarity of the answer here, that on one side, above 60, the people were defaulter. No matter what was their income, above 60, we have observed in the past that they were defaulter. So here, if I start here, this is my section number 1 that we have created. And on the bottom, there are still a lot of confusions, but at least on the above part, it is sorted. That these are the people who were defaulters in the past. Now, talking about the bottom part, if you look, where should I build the next line? So I think that if I make a line somewhere here, it will be good, right? If I make a line somewhere here, it will be good, right? So if I do that, then I will be making this section number 2. Then this section number 2 is also having all the defaulters in that. Section 1 above 60, section 2 is below 60 and income less than 21K. So this is section number 2 I built. Now this is remaining where I will make the next line. So I will make the next line on the basis of age somewhere here. That will be better. And this is going to be giving me the section number 3, let us say. Then if I make a line here, this is going to give me section number 4, and this is going to give me section number 5, right? So I have got 5 sections here also. And this is my decision boundary 1. This is my decision boundary 2. This is my decision boundary 3. And this is my decision boundary 4. So 4 I'm building here also. 4 I built in that previous case also when I started with income. So in this case, our starting point is age. That is the difference here. So let us convert that into a tree structure and then see what is happening. So if I start with this age is my root node because I started with that. So age, when I divided my data into 2 parts, below 60, above 60. That is what we did. So I will go on 2 side, less than 60 and more than equal to 60. When I'm above 60, right? When we are above 60, so you can see that we have red points directly, right? So above 60 it is sorted. So I'll try to make it little on the right side because I think this tree is going to be going to grow on the left. So if I take age here, it is greater than equal to 60 and less than 60. So on the greater than 60 side, I have a very clear answer of these defaulters, and I can just finish it up here that these are defaulters. There's nothing I'm going to build after that. So whatever will be built on the left side of the tree, now it is going to be built. Now age less than 60 that I see, right? Age less than 60 that I see, what is the next boundary that I have built? Means in this entire area, which is below the line number 1, in that area, what was the next line that I built? 2, right? 2, which was on the basis of income around 21K. It is not exactly 20, it is little higher than that. So let's assume that it is 21.5, suppose. So line number 2 is built vertically somewhere at 21.5K, let us say, because it is little higher than 21. So now the next point is the income value, and this is less than 25, more than 25. So I will say less than 21.5K and I have greater than equal to 21.5K. I took this and I took this. Now what is happening in less than 21.5K? So if you observe that in less than 21.5K, we have the structure, which is defaulters. So age less than 60 and income less than 21.5K, we are falling into this section 2, which is defaulters. So here I will mention defaulter as the predicted value, defaulter. Then for age less than 60, but income more than 21.5K, now we are talking about this entire section, right? On the right side of 2 and at the bottom of 1 in between that. So next one that I built was third one. Third was on the basis of age. Age somewhere around 38, I think, that this age I've taken 38. So here I don't have any answer. I have to make one more point, age, which is less than 38 and more than equal to 38. Now, in less than 38, do I have an answer here? So if you see that age less than 38 is this section and age more than 38 is this entire section. So in age less than 38, you can see we are falling into section number 3, which is for defaulters. This is for non-defaulters, sorry. This is for non-defaulters, right? Non-defaulters. This one, non-defaulter. And age more than 38, what we are now seeing, that for age more than 38, we are talking about this section. This section is remaining. In this section, I made one more decision boundary, fourth one, which was on the basis of income somewhat 40. So let's consider this as income of 40K. So here I have made one more part of income, and it is now being broken into less than 40K and more than equal to 40K. Right. And if you see less than 40K, what is happening? So less than 40K, we are falling into this section number 4, which is defaulters, right? These were the people who were defaulter and these were the people who were non-defaulters. Now, so I have built this tree structure at this point. Let me take it and put it on the right side. Now, so you can see that as I changed my starting point, earlier the starting point was income. But now in this case, I changed my starting point to be age. I made my root node as the age. So you can observe that the entire structure of the tree changed. In this case, it was a little longer tree where I started with income. And in this case, when I started with the age parameter, then this tree is short and is having a very different structure. But is it predicting the same thing for the value that we have taken? For a person whose income is 53K and age 42, let us see what this tree is predicting for that, right? So now 42, if you now notice, then 42 is going on this side, then income 53 on this side, then age 42 on this side, then income 53 on this side. We have non-defaulter. So both of the tree has predicted non-defaulter for this person, both of the trees. But it will not happen always. The trees will give some different predictions for a singular input value. These trees may give different predictions at many of the points. Here, both of them are predicted same, but they can change also because the structure is different. Now, the question is that on the same data, I have shown you that you can build two different trees just by changing the root node. So first thing, root node is the most important feature or most important part of the tree. Because just by changing the root node, I'm changing the entire structure of the tree. This is how powerful it is. So root node is the most important point of this entire tree, the starting point, root node. So the question is, which tree is better? Is this one better? Is this one better? How do I decide that? Right? How do we decide that? So for that particular purpose, we are going to study this thing now, which we have here. So in this file itself, I have given this particular point here, which is called as finding the best split. Means, should I split the data in this way or that way? How do I decide the best way to split my data? What we were doing, we were taking all the data and splitting it into multiple sections by using the decision boundary. One on left side, one on right side, one on top, one at bottom. So we were splitting our data into multiple sections. So what are the approaches? What are the methods using which we can identify which is better? So there are two commonly used approaches in the industry. One is called as ID3 algorithm and one is called as CART algorithm. So to decide which tree is better, which tree is more efficient, and I should use that, to decide that we have two different algorithms called as ID3 and one is called as CART. So what are these? Let me show you. The first one, which is ID3. ID3 algorithm, and second one is the CART algorithm. So if you remember in linear regression, we have used a formula to decide which tree is which line is a best fit line. We have used a formula. What was the formula we used in linear regression to decide a best fit line? So that formula was cost function, if you remember. So cost function was nothing but a modified version of total error. We took the total error, then from the total error we built MSE, mean squared error, and from the MSE we converted that to cost function. So cost function was nothing but a modified version of total error, and whichever line had the least cost function, we were able to tell that since this line has the least cost function compared to other lines, this is our best fit line. We were able to say that. Same way in the decision trees. So basically for decision tree, we have two different algorithms that we use. For linear, one algorithm is there. For logistic, one algorithm is there. The same way it will work. But for decision trees, multiple people have tried to implement decision trees in their own way. So there are two research papers. In one research paper, this concept of making a decision tree was discussed. And in one research paper, this is the concept of making decision tree was discussed. This method is old. So for making a decision tree, we can use either ID3 algorithm or I can use a CART algorithm. So if I use ID3 algorithm, it is old. Means it will take little extra time to make the best tree because it is old. It has such type of formula which will make it little slow. I'll show you that formula also. But this CART algorithm is a new algorithm which is little fast and a better version of making a tree. But now the thing is, old does not mean that it is bad. It is just that in the old one, there are the measures which are shown or the concept which is shown to make a tree. Both are similar, but they use different formulas. And because of different formulas, there are little extra calculations that happen in ID3 and less calculations happen in CART. So the CART is able to give us a decision tree, the best one, fast compared to the ID3. So both of that we are going to use because in the real world, in the industry also, you will try both of them on a given data. And then whichever is working well for you, you keep that and remove the other one. So means we are going to use both of them on any data set. We will build the tree using both of them and we'll see which one is building the tree better for us. Now, I will explain the concept using CART because it is a new one. When you go to interview, you will be using this to explain since it is a new one. It will be expected from you. And once you knew the working of the CART, just formula changes there and everything will be same in the ID3. Just the formula change will be there. So once you understand one of these, you will understand the other one automatically. So what I'm saying is to make a decision tree, to identify what will be the root node, what will be the decision node, what should be my starting point, to decide everything, we have two different algorithms, ID3 algorithm and CART algorithm. ID3 is old, CART is new. Now, in both of them, there is only one basic difference of formula change. What is that? So ID3 algorithm basically uses two formulas inside of that, entropy and information gain. It basically uses these two formulas to build an efficient structure of decision tree. And when I talk about the CART algorithm, so CART algorithm uses only one formula, which is the Gini impurity. Gini impurity, or this is also called as Gini index. So if you see any of these names, they refer to the same thing, Gini impurity or Gini index. So since CART is just using one formula to make this all the calculation, it will be little fast compared to this, where we are using two formulas to identify the good tree structure. So now the benefit of using CART. CART is a new algorithm. CART means the full form of CART is classification and regression trees. Okay. So CART algorithm has this concept that it can be applied on the regression data also, and it can be applied on the classification data also. But ID3 is specially just limited to the classification data. So since CART is a new method, someone has tried to update this entire concept of decision tree in such a way that it can be also applied on the regression data. And we can use this for both of the concepts. So it will be even better for us. If I know one algorithm, I can apply it on the regression also, classification also, good for us. So I will give you an explanation about this one because this is most used or preferred, new, easy to understand. We will talk about this one. You don't need to know both. Just if you know one of that, same, you will understand exactly the other one. Let me show you what is this concept. It's a small mathematical thing. I'll just try to give you an idea about. Okay, now. So there is a concept of impurity or homogeneousness that we talk about. When we have to decide that should I use the income as the root node or should I use the age as the root node? Where exactly should I make another decision boundary at the income of 25K or at the income of 36K? Where exactly should I make that decision boundary? That all depends on the concept of impurity. What do I mean by impurity? It's a simple concept to understand that. Let's say that you have a data like this. And in this one, suppose you have 2 points here and you have 2 points here, right? So the thing is that I can make a decision boundary here, like this also. I can start it with this or I can start it with this. So first you have to decide that should you make the decision boundary on the basis of this input column C1 or should you make the first decision boundary on the basis of C2, which will be efficient for you. So the thing is, if I make the decision boundary on the basis of C1, column 1, wherever I make that, I make it here, 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 anywhere I make it, will it do a correct prediction for you? Is it uh, making a homogeneousness in the data? It is bringing clarity in the data or not? If I make on the basis of C1 as the starting one, so we'll say no. If I'm starting with C1, you see that this type of data points are similar and these are similar. So there are two different types of data points. So if I make any line vertically here, then on this side, we are not getting clarity. Or if I make a line somewhere here, on this side, left side, we have nothing. So it won't make any line here because on the right side, we have all the data point. So if I start with C1, I'm not getting any clarity. It is still impure. We are not getting purity. But if I make on the basis of C2, are we doing a good task? So we'll say, yes, we are splitting the data into two sections, 1 and 2, and both of the side, we have perfect clarity. A simple purity is there, and we will be able to decide anything very, very clearly without any doubt, without any confusion. Correct? So first thing you have to define or you have to identify which is that column I should take. That is the first decision I have to make. So there is column 1, column 2, input column 3, input column 4, input column 5, input column 50, 60. If 60 different input columns are there, then how to decide which is going to be the first one? Correct. So what we try to do, we try to take all the columns. So now the thing is that we have the C1 here and we have a C2 here, we have a C3 here, we have a C4 here, we have a C5 here. Like that, let's say multiple columns are there. So what happens if you have multiple columns? How do you decide which one is best? So we do a calculation of these columns. So I'll take all these columns and I'll say that if I make these columns as the root node one by one. So one structure I'll make where I'll make the C1 as the root node. One structure I'll make where I make the C2 as the root node. One structure I make where I make the C3 as the root node. And what will I do? That when I put the C1, C2, C3, C4 as a root node one by one in different examples, I will try to check the Gini impurity of this one, the Gini impurity of this one, the Gini impurity of this one. I'll try to calculate the Gini impurity of all the structures where the root nodes are different. And whichever structure is giving the least Gini impurity, that is the structure I will move forward with. So suppose this structure where the input column C2 is better, this gave us the lowest Gini impurity compared to other columns which I made as the root node. So I made the C1 as the root node, C2 as the root node, C3 as the root node, C4 as the root node. So first, when I took each column as the root node in different examples, I checked, I calculated the Gini impurity of that structure. And whichever structure gave me the smallest Gini impurity, the lowest Gini impurity, then what happened with that? I will say that this is the good structure, the root node as a C2 is the best compared to the other one, because C2 is bringing more clarity into the data compared to the other things which we have, right? So let's say C1 is my income. I will not be making entire tree. If I make 500 trees entirely, then it will be taking too much time. So we don't make the entire tree. We are just saying that if I take the income and if I split it into two parts, if I'm splitting my data into two parts on the basis of income, is it bringing more clarity? Or if I'm breaking on the basis of age into two parts, is this bringing more clarity, or is the income one bringing more clarity? So we don't build the entire tree at any point. We just decide one by one. So first, I will say that if I took my income, like if I go back to the data here, so first I have to decide what the first decision boundary, where it should be made. So what did I do now? As I took this data here, and first I said that I have some points like this, and then some points here, and then some points here, and then some points here, let's say. So I am doing what? I am first making the decision boundary. So should I make my first decision boundary like this? Or should I make my first decision boundary like this? Or should I make my first decision boundary something like this? So if I see that when I made my first decision boundary like that, on one side, I'm bringing a very big clarity into my data. But as opposed to that, if I'm making the horizontal one, anywhere if I make the horizontal, will it do a better clarity, or will it bring better clarity as compared to the vertical one? Will it help us anyway, the horizontal one as the starting one? No, it is not bringing that much clarity compared to by making the first line vertically. So this is suppose my income and this is suppose my age. So if I'm making my first decision boundary on the basis of income, it is bringing better clarity into my data by just taking this as the root node. So since it is splitting my data into two parts, at least one side is becoming very clear. I don't have to make everything clear in the first line itself. You know, we have to make multiple boundaries. So at least the first line is bringing more clarity compared to a line which I would have taken as age. So on this basis, I will just make the first line and I will say that my root node is income, which is splitting my data into two parts. One is income less than 35K and one is income more than 35K. I will just make this much as of now. Then I will say that, is it better? Or if I'm taking age with the value of less than 28 and more than 28, is this better? Which one is better? So I found out that income with these particular values is better. That I was able to identify. Now, the first thing you have to understand is the first thing we decide is what column should we take. And after that, I have to decide what, for that column, what value should be used. So a combination of this and a combination of this will be taken, right? Now see, so what is the first thing? See, I have decided that, okay, on the basis of income, if I make the first line, it is working better. But where on the income? Because on the basis of income, I can make the line here also, here also, here also, here also, and here also, here also, here also, here also. So I can pick any income value. Which is that income value which is best? So first you have to identify the column, that out of all the columns, which is better. Second thing that you have to decide is, you have to identify is what value of that column is suitable. Is it 35K? Is it 28K? Is it 42K? Is it 53K? What is that value of income where that line is best, which is giving more clarity? So are you getting these two combinations we have to identify together, not just the name of the column, but also along with that, what is the value of that column I should take to make the split? So understand what your entire tree structure will do. This CART algorithm will do for us. It will take income and it will split that on the basis of, let's say, 28K and more than 28K. Then it will take income and it will now split that on 35K, 35K. At less than 35, more than equal to 35. Then it will take income and then it will take 42K, less than 42K and more than 42K. So what it will do now, for single column, it will try multiple variations. Is this better? Means income with 42 is better, or income with 35K is better, or income with 28K is better, or age with 26 is better, or age with 37 is better, or age with you can say 60 is better. So what I'm trying to tell you is that tree will try multiple combinations of different columns. So if I take income as one of the column as the root node, so for income, should it be 28K? Should it be 35K? Should it be 42K? Where exactly for income? So is this combination good? Is this combination good for income? Or are all of these bad? But I should check age, and age with this is better, and these two are not better. So out of all the 6 combinations I have built, which one of these 6 combination is best, has been found to be best? And how are we going to decide that? So whichever of these combination is going to bring more clarity as the first decision boundary, that will be my starting point. And who will decide that? This Gini impurity formula or concept I was talking about, that Gini impurity will tell us that which root node, means which column as a root node is better, and what value of that root node should be taken, which is better. The combination will be found by the Gini impurity by trying multiple combinations like that. Are you getting the point? What I was trying to say? Because once you understood this, then everything is sorted. This is the main complicated part of this. That to find out what is the root node, first we have to take that column. But for that column, what value exactly is better, we have to identify that also. So decision tree will try what? Decision tree will try multiple of these variations where it will take a column as the root node. And for that column as a root node, it will try multiple values, multiple numbers. For income, it will try multiple values. For age, it will try multiple values. For CIBIL score, it will try multiple values. So then it will find out that the income with this value is better than any other combination that we have tried. So it might try 400 combinations like this, 500 combinations like this, maybe 1000 combination like this it will try if you have a lot more input columns. So out of that, it will find out the best one. This column and this value is the best out of all. And that it will continue forward with. I hope you are getting this much point. Perfect. So this is as simple as I can make. It will be a little complicated for now, but I hope you're getting the overall perspective. And as you revise this concept once again, it will become 100% clear to you. I can guarantee that. So let us talk about the working of this. Apart from this CART and ID3, there have been a CHAID, this algorithm also, ID 4.5 also, ID 1.1 also, ID 2.3 also, like that. Means there have been different algorithms for decision tree. But now only these two are used in the industry because these two were found to be better than any other option that existed in the past. So there were multiple variations, means different people, different researchers have created different methods of making the of finding out these trees or making the trees. But out of that, only these two is now used. These are not used because they were old and they were not as powerful as these two concepts that we use now. I'll discuss with you just one small concept, right? So let me show you one problem. There is a big problem with the decision tree. Decision trees are powerful, very, very powerful. Why they are powerful? Because they have the capability to make infinite number of decision boundaries. So since they have a capability of making infinite decision boundary, they can understand any data. They can understand the pattern from any data much better than logistic regression. Now, I'm not saying logistic regression is always bad. In some cases, logistic regression might perform better than decision tree. But for most of the cases, if I use decision tree on a classification data, it will perform better than logistic regression because it is so much powerful. It has limitless possibilities of making the decision boundaries. But because of that, since it is so powerful, it tends to create a problem for itself. And that is a problem of overlearning, right? Overlearning, and that is called as a concept of overfitting. That is called as overfitting in technical terms. So overfitting means that your decision tree might do over learning something. The learning which was not required, it still did that. So how do I identify the over learning? How does it look like? Let's go back to our data. And in the data here, let me show you one example. Yeah, let me take this. Suppose this section number 5, if you see, this is my section number 5. Now in this section number 5, let's say there is this one data point here, which is this pink one. In the section number 5, most of the points are blue, but just one point is red. So now the concept of decision tree says that I will not stop until I have classified every data point correctly, right? So there should be no mixture at all in any of the section until I have classified everything perfectly, then I will stop. But the problem with that is in this section number 4, when it will see that there is this red point, it will try to make one more section for that, section number 6, just for this one single data point. Then it will go into section number 3. You see that there is one red point in section number 3. So it will try to make one more section, section 7 for that. And then when it goes to section 4, in section 4, there is one blue point. It will make a separate section for that. It will do that because it has no limitation of making the decision boundary, right? It can make infinite number of decision boundary. So it makes lot of unnecessary decision boundary. Now tell me, was it required to make a separate section for this just one data point? Was it required? Or to make a separate section for this, or to make a separate section for this? Is it required? No, right? No, these are not outliers. No. These are not outliers. These are just a data point which is present in another section. Outlier is what? Outlier is a point which is very far away from these normal data points like that. These are your outliers. These points which you see are not outlier. See, what is this data point? If I have a pink data point here in among these blue ones, what is it telling? That in this section, most of the people have returned the loan. But there was one person whose income was greater than this and age was less than this, but this person was a defaulter. So out of all the people who have taken loan, whose characteristics were these, like age, income was more than this and less than this age. So most of them were able to pay the loan back. Just one customer was there who did not pay the loan back. So it is not an outlier. It is just that one person behaved differently in that section, right? That is the thing. So for one or two data points, I should not make a separate section. There is no problem with me having one pink point among these blue points because I am very sure that since most of the points, since 99% of the points are blue, if 1% is red, no problem. I am very confident. I'm very sure that if 99% people were non-defaulter, then any new person will also be non-defaulter. There are very high chances of that. So I should not be making extra decision boundaries just for one or 2 points. And that this is called as over-learning. That the decision tree, if left to work, then it will try to make these extra unnecessary boundaries. And that is called as over-learning, overfitting, which was not required. And also I told you that because of every decision boundary, a branch will be added into my tree. So one branch according to this, one branch for this, and one branch for this. 3 new branches will be added into my tree, which was totally unnecessary. And because those branches are created in my tree, it will make lot of my predictions wrong because of those branches. Because now those branches will be also used for prediction purpose. So now your answers will become wrong because of these branches that is getting added into your tree. To give you that, why it will be wrong? If I suppose have a new person here. See, if I have one person which is in this area, this person has this much of income and this much of age. What should have been predicted for this person? Right, before we did the overlearning, what should have been predicted for this person? So this person would have fallen into this section 5, and this person would have been called non-defaulter, right? If I did not have this extra boundary, then in this section 5, most of the blue points are there and one red point is there. So I would have said that the predicted value for this is non-defaulter. Would that have been correct? Yes, that would have been correct. because I can see that in section, most of the points were non-defaulter. So I would have been correct to say that this person would be non-defaulter. But if my model does overlearning, if the decision tree does overlearning, it will make one more decision boundary here. And now it will be section 6. And in the section 6, you have one red point. And if I have 1 point here in the section 6, because there is only one red point, it is defaulter. So this person will be considered as a defaulter. So now, because of overlearning, what is happening? Your predictions is becoming wrong. And it will reduce the accuracy of the overall model because of these extra decision boundaries that will be made. So this is the biggest problem. The last thing for today is, this is the biggest problem of decision tree, because since it is capable of making unlimited decision boundaries, it makes lot of decision boundaries which were not required at all. And I have to control that. I have to stop it from making these extra boundaries. Okay. Right. I hope you got the problem of this decision boundary, this decision trees. Okay.
Just a quick info, guys. Intellipaat offers an advanced certification in machine learning and AI in collaboration with Microsoft. Through this course, you can learn all the important concepts of Python, machine learning, deep learning, NLP, computer vision, and much more. The course features live classes with IIT faculty and industry experts, campus immersion at iHub IIT Roorkee, and includes certification from both Intellipaat, Microsoft, and iHub Divya Sampark IIT Roorkee. With this course, we have already helped thousands of professionals successfully transition into careers in AI, ML, and data science. You can check out the testimonials on our Achievers channel. The link is given in the description below. With the 24/7 support, placement assistance, and EMI payment options, this course can definitely set your career on the right track in the field of machine learning and AI. So visit our course page link given in the below description and take the first step towards your career growth in ML and AI.